Chapter 1 Introduction. The total eclipse of the sun in India of the X-1/8 of August 1868 was an event which, it will be remembered, excited extreme interest in the scientific world, and led to a large expenditure of money and labor in order that a new method of investigation, spectrum analysis, might be applied to those mysterious phenomena, invariably present at a total solar eclipse, the nature and character of which the unassisted powers of the telescope had proved themselves inadequate to reveal. The brilliant results obtained at this eclipse were fully confirmed by the more recent observations made in North America during the total eclipse of the 7th of August 1869, and the records of those eclipses laid before the various scientific societies clearly assert the triumph of spectrum analysis. On this account, the new method of investigation has excited great interest in all cultivated circles, and therefore a familiar and comprehensive exposition of the details of spectrum analysis, in which is shown the great value of this method of research in every department of physical science, seems not uncalled for. By spectrum is not understood in physics a specter or ghostly apparition, as the verbal interpretation of the word might well lead one to suppose, but that beautiful image, brilliant with all the colors of the rainbow, which is obtained when the light of the sun or any other brilliant object is allowed to pass through a triangular piece of glass, a prism. The unassisted eye can perceive no difference in the light from the heavenly bodies, and that from various artificial sources, beyond a variation in color and brilliancy. But it is quite otherwise when the light is viewed through a prism. There are then formed very beautiful colored images or spectra, the constitution and appearance of which depend upon the nature of the substance emitting the light. The different appearances presented by these colored images are so entirely characteristic that to every substance, when luminous in a gaseous form, there corresponds a peculiar spectrum which belongs only to that particular substance. It follows, therefore, that when the spectra of different substances have been determined once for all by previous researches, and have been recorded in maps or impressed upon the memory, it is easy in any future investigation to recognize at once, from the form of the spectrum which a body of unknown constitution presents, the individual substances of which it is composed. This statement presents in general terms the nature of spectrum analysis. It analyzes bodies into their constituent parts, not as the chemist with alembics and retorts, with reagents and precipitates, but by means of the spectra which these substances give when in a state of intense luminosity. Spectrum analysis in no way supplants the methods of chemical analysis hitherto in use, for its function is neither to decompose nor to combine bodies, but rather to reconnoiter an unknown territory, and to stand sentinel and signalize to the physicist, the chemist, and the astronomer the presence of any substance brought beneath its scrutiny. With what acuteness, with what delicacy does spectrum analysis accomplish this task? When the balance, the microscope, and every other means of research at the command of the physicist and the chemist utterly fail, one look in the spectroscope is sufficient in most cases to reveal the presence of a substance. If a pound of common salt be divided into 500 equal parts, the weight of one of these portions is called a milligram. The chemist is able, by the use of the most delicate scales and the application of special skill, to determine the weight of such a particle, but in doing so he comes close upon the limits of his power of detecting by chemical means the presence of sodium, the chief element in common salt. But if that small milligram be subdivided into 3,000,000 parts, we arrive at so minute a particle that all power of discerning it fails. And yet even this excessively small quantity is sufficient to be recognized with certainty in a spectroscope. We have but to strike together the pages of an old dusty book in order to perceive immediately in a spectroscope placed at some distance. The flash of a line of yellow light, which we shall presently learn, is an unfailing sign of the presence of sodium. It was to be expected that so sensitive a means of investigation, from which no known substance can escape, would very soon lead to the tracking out and discovery of new elements which, till then, had remained unknown, either because they are scattered very sparingly in nature, or stand out with so little that is characteristic from some other substances. that the imperfect chemical methods hitherto in use have not been able to distinguish them. This expectation was brilliantly realized even by the first steps taken in this direction. The two Heidelberg professors, Bunsen and Kirchhoff, to whom we are indebted for the discovery of spectrum analysis and its application to practical science, very soon discovered with their new instrument two new metals, cesium and rubidium, to which two others, thallium and indium, have been since added, but all the brilliant and astounding results which spectrum analysis has furnished in the provinces of physics and chemistry have been far surpassed by its performances in that of astronomy. Newton's law of gravitation has given us the means of calculating the courses of the heavenly bodies, of projecting the orbits of the earth, the planets and comets, and of predicting their relative positions in these orbits, together with the accompanying phenomena of the ebb and flow of the tides and the eclipses and occultations of the heavenly bodies. But this same gravitation chains man to the earth and forbids him to leave it. It is therefore only on the wings of light that news reaches him of the existence of those numberless worlds by which he is surrounded. The light alone which proceeds from these stars is the winged messenger which can bring him in information of their being and nature. Spectrum analysis has made this light into a ladder on which the human mind can rise billions and billions of miles, far into immeasurable space, in order to investigate the chemical constitution of the stars and study their physical conditions. Until within a few years, the telescope was the only means by which these investigations could be carried on, and the intelligence derived from this source concerning the stars and nebulae was very scant, being confined to but partial information of their outward form, size, and color. Since the year 1859, spectrum analysis has entered the service of astronomy, and its performances for the short space of 11 years are, in the most widely differing ways, perfectly astounding. It is possible, by means of a prism, to decompose into its component parts the light of the sun, the planets, the fixed stars, comets, and nebulae, and thus obtain their spectra in the same way as that of earthly luminous substances. By a careful comparison of the spectra of the stars with the well-known spectra of terrestrial substances, it can be determined from their complete agreement or disagreement, with a certainty almost amounting to mathematical precision, whether these substances do or do not exist in those remote heavenly bodies. The foregoing statements present in general terms the essence and scope of spectrum analysis. Its starting point is the spectrum of each individual substance, and in order to obtain this, it is requisite that the substance should not only be luminous, but should emit a sufficient quantity of light. Dark bodies are not available for spectrum analysis. If they are to be submitted to its scrutiny, they must first be brought into a state of vivid luminosity. To avoid later interruptions and repetitions, it will be desirable, before entering upon the subject of spectrum analysis, to review with brevity the means afforded by chemistry and physics for rendering luminous all substances gaseous and non-gaseous, and even the least fusible metals. Chapter 2. The luminous power of flame, the immediate cause of the luminosity of flame, has not yet been fully ascertained, notwithstanding the many investigations that have been made with this object. If a glass receiver, figure I, be filled with oxygen, and a lighted piece of phosphorus be plunged into it from above, the phosphorus will burn with great energy and give out a dazzling light. In the same manner, most metals previously raised to a glowing heat, as for instance a steel watch spring, will burn in pure oxygen with the development of an intense light. If, on the contrary, a stream of gas issuing from a reservoir of hydrogen be ignited in free air, it will burn with a scarcely perceptible flame. The flame produced by oil, petroleum, and coal gas is very brilliant, while that from spirits of wine is faint. What occasions this difference? The chemical process of the combustion of phosphorus and of hydrogen is the same, namely, the combination of these substances with oxygen. The amount of heat evolved is also not very dissimilar. The difference, therefore, appears to lie only in the nature of the products of combustion. In the case of phosphorus, this product appears as a solid body in the form of a dense white cloud, phosphoric acid, In the case of hydrogen gas, the product of combustion is invisible because it is water in a gaseous form, that is to say, steam. This remark applies, with few exceptions, to all combustion which takes place at very high temperatures. A flame which contains neither solid matter as a product of combustion, nor yet a foreign solid body in a state of incandescence, is as a rule but little luminous, even when the temperature of combustion is very high. Therefore, at a similarly high temperature, glowing solid or liquid bodies emit far more light than gaseous substances do. The fewer solid particles there are in a flame, the less brilliant will be its light. The scarcely perceptible flame of burning hydrogen gas will immediately become luminous if any solid body be heated in it to incandescence. If a spiral of platinum wire be held in the flame, it shines brightly. The glowing wire is clearly seen, and conveys the impression that the light is not due to the hydrogen flame, but to the glowing white-hot metal. The heat generated by the chemical combination of the hydrogen gas with the oxygen of the air renders the platinum incandescent. And it is the glowing platinum wire, not the flame, which emits the intense light. If a grain of common salt be dropped into the dull flame, it flashes up brightly with a yellow light. The salt is dispersed into 1,000,000 of the smallest particles, all of which, glowing in the flame, can no longer singly be distinguished. They thus give the appearance to the hydrogen flame as if it shone of itself. For the illustration of this point, it is unnecessary to make any artificial experiments, since the flame of common gas, which, owing to its great brilliancy and is universally employed for domestic and other uses, is well suited to the purpose. Coal gas is a chemical compound of hydrogen gas and carbon, though it is often contaminated to a more than necessary extent with other substances. Carbon, after oxygen, certainly the most precious of all substances. Alike valuable in its crystal form of diamond, as in its dirty black form of coal, is not distinguishable in common gas, for through its combination with hydrogen, it has lost its brilliant sparkle as well as its black color, and it then appears as a transparent gas, not indeed as an independent body, but in the most intimate chemical combination with hydrogen as carbureted hydrogen gas. If this gas be ignited as it streams out of an ordinary burner, in contact with the atmospheric air, the greater part of its oxygen is taken up by the hydrogen in the gas, and a considerable quantity of carbon, for which there is not sufficient oxygen present, is thrown down. Combustion takes place almost entirely near the edge of the flame, where it is in contact with the oxygen of the air. In the middle, the gas is merely decomposed by the heat of the combustion, and in this heat the very finely separated particles of carbon which have been precipitated, are in a state of brilliant incandescence. It is to these glowing particles that the gas flame owes its illuminating power. In order to see them, it is only necessary to hold a cold substance, such as a china saucer, in the brilliant part of the flame. The disengaged carbon covers the saucer in the form of the finest soot. The same thing occurs in the burning of tallow, styrene, oil, or petroleum. In the lighting of candles or lamps, the combustible substance is first decomposed, and then by the heat of combustion, combinations of carbureted hydrogen arise in the form of gas. When the oxygen is insufficient, only a small portion of carbon is immediately burnt, and that at the edge of the flame where a great development of heat takes place. Here the product of combustion is a gas, carbonic acid, and therefore the edge of the flame gives but little light. In the inner part, however, where there is of oxygen, the solid particles of carbon attain a white heat, and only as they escape out of the flame burn by the high temperature of the edge. It is, therefore, the incandescent solid particles of carbon that give to the flame its illuminating power. Easy, therefore, as it is to give brilliancy to a non-luminous flame, it is no less easy to deprive a brilliant gas flame of its luminosity. All that is required is to mix such a quantity of oxygen or atmospheric air with the gas before it is burnt, that the oxygen penetrates into the inner part of the flame and burns all the carbon present in the gas. When this happens, the flame instantly ceases to be luminous and is found nearly under the same conditions as the flame of pure hydrogen gas. With a sufficient quantity of oxygen, The combustion of the hydrogen, as well as of the carbon, goes on with unusual rapidity in all parts of the flame at once. The natural consequence of this is that, on account of the incomparably greater development of heat, the non-luminous gas flame is much hotter than the luminous one. It is now a heat flame and a source of heat instead of light. In opposition to these facts, there are others which prove that the presence of solid particles in a flame is by no means necessary in order to give it luminosity. Franklin has shown that when hydrogen is burnt in oxygen under a pressure gradually increasing up to 20 atmospheres, the feeble luminosity of the flame becomes gradually augmented, until at a pressure of 10 atmospheres. It is bright enough to allow a newspaper being read at the distance of 2 feet from the flame. A similar increase of brilliancy is observed in the combustion of carbonic oxide gas and oxygen under pressure, and under similar conditions, sulfide of carbon burns in oxygen or in nitric oxide gas with an intense light, though no solid particles are present in the flame. Franklin maintains, therefore, that the luminosity of a coal gas flame is not due to the presence of solid particles of incandescent carbon, and that the soot deposited on a porcelain saucer from a gas flame is not solid carbon, but a conglomerate of the densest light-giving hydrocarbons. He has proved that the very clear flame of coal gas is perfectly transparent, from the fact that he sent the intense electric light through such a flame onto a screen, without the least trace being perceived of any solid incandescent particles of carbon, while Franklin considers the luminosity of the flame to depend mainly on the density of the burning gas. St. Claire de Ville ascribes it chiefly to the temperature of the combustion, which is dependent upon the density of the gas. Whatever may be the cause of luminosity in an incandescent body, this fact is certain that incandescent, solid, and liquid bodies possess a much greater brilliancy and emit a much more intense light than gases do when rendered luminous under ordinary pressure, and that the luminous power of gases increases in proportion to the pressure to which they are subjected, by which their density is increased, and they approach more nearly the condition of fluids. Chapter 3. The Bunsen burner, the correctness of the foregoing statements, may be easily shown by a lamp of Bunsen's construction, Figure 2, which is absolutely required in all researches with spectrum analysis. This burner causes a rapid combustion of the particles of carbon in coal gas, and so generates a high degree of heat. And this is accomplished by allowing the gas which enters the lower part of the lamp to mix plentifully with atmospheric air before passing up the tube to feed the burner. For this purpose, the lower chamber S is perforated so that the outer air enters freely while the gas is burning. The gas takes up here a sufficient quantity of air, and then rises with it to the top of the tube AA. The flame gives no light, but its heat is very considerable. If the supply of outer air be intercepted by closing with the fingers the openings to the mixing chamber, the flame immediately becomes luminous and throws down particles of carbon in abundance, which was not the case before, as no soot whatever is deposited on a china saucer by the non-luminous heat flame, if the burner be contrived, as is very desirable when working with the spectroscope, so that the entrance of air to the gas can be shut off at will, either entirely or partially, which is easily effected by turning round a perforated ring. Then the same burner serves to give alternately a luminous or a heat flame. When the ring cuts off the supply of air to the gas by closing the openings to the mixing chamber, the flame shines brightly, like any ordinary gas flame. When, on the contrary, the ring is turned to allow the air to pass into the mixing chamber, the luminosity ceases and the flame becomes a heat flame. The heat of this flame is so intense that it is capable of converting many substances which it may be desirable to examine by spectrum analysis into a gaseous condition, causing them to emit sufficient light to yield a clearly perceptible spectrum. But a far greater heat may be attained if the atmospheric air, instead of being left to mix itself with the gas, be forced in by means of a powerful blowpipe. A contrivance of this kind is seen in the gas blowpipe, Figure 3. The gas from the pipe G enters a wide tube A, which is closed at the lower end by a stopcock, and is made to turn on a pivot round the stand. The gas passes through and escapes at the further end. In the middle of this tube runs a second, narrower tube BB, through which the atmospheric air is forced into the stream of gas by means of a bellows and an elastic tube. The gas flame receives so much oxygen in this way, not only around the edge, but also in the center, that an enormous quantity of heat is generated by the complete combustion of the hydrogen and carbon. Over the escape end, a tube slides up and down, and partly by this means and partly by the cocks, the degree of heat in the flame can be regulated at will. The greater the quantity of gas which can be burnt in a given space, and the greater the energy and the rapidity of the combustion, the greater also will be the amount of heat evolved. For this reason, in the great laboratories, the atmospheric air is forced by a special air pump into a strong iron receiver of the capacity of several quarts, where it is subjected to a pressure of 1.5 or 2 atmospheres. If this compressed air be allowed to escape along with a copious stream of gas from a common tube, in the same manner as we have just described, the flame becomes one of such intense heat, owing to the rapid and complete combustion of so large a quantity of carburetted hydrogen, that it has power to melt in a few minutes considerable quantities of the least fusible metals, as, for example, a couple of pounds of platinum. Chapter 4. The magnesium light. There are some substances, such as potassium, sodium, etc., which have so great an affinity for oxygen that they wrest it even out of its most intimate combinations in order to form with it a new substance. A process accompanied by a development of both light and heat. Among these substances, magnesium is especially distinguished for the extraordinary amount of heat and light which it thus produces. This metal is white like silver and of remarkable metallic brilliancy. It is very light, but somewhat heavier than water, so that it will not float upon its surface. When heated in the air up to a certain temperature, it ignites and burns, at the expense of the atmospheric oxygen, with a white and dazzling light on which, when near, the eye cannot bear to look. Magnesium burns with great rapidity, and the solid product of combustion, solid incandescent magnesia, emits a very intense light. It partly rises in the air in the form of white smoke, and partly falls as white powder to the ground. Though the luminous power of the sun be 524 times greater than that of the magnesium light, the activity of its chemical rays is only about 5 times as great. This light is therefore peculiarly adapted for the photographic representation of objects which are badly lighted, of works of art in dark palaces and churches, of underground buildings, and of small landscape pictures, such as representations of moonlight, etc. It is well known that the Roman catacombs and the dark tomb chambers in the interior of the pyramids have afforded fine photographic pictures by the aid of the magnesium light. Unfortunately, the price of this costly metal is still high and stands now at 20s per ounce. It may be assumed that the ordinary magnesium wire burns about 1.5 grains in a minute, in value about a halfpenny, and evolves a light which in intensity is equal to 74 stearine candles, of which 5 go to the pound. From these experimental data, it may easily be calculated that the unit of light in the combustion of magnesium does not cost much more than its equivalent in stearine candles. For the magnesium light to be of practical use, the combustion must be under control, and the light so arranged that its concentrated rays can be thrown in any direction. The lamp constructed by Grant and Solomon accomplishes this object with tolerable success. It consists, Fig. 4, of a clock movement enclosed in a case, which when wound up by the key C and set in motion turns 2 small cylinders placed one over the other. The magnesium wire enters the case from a coil at 0, where it passes between the cylinders, and is pushed forward at a uniform speed through the small brass tube PQ. The orifice Q of this tube is in the focus of a silvered concave mirror, so that when the wired Q is ignited, all its light is thrown forward. By means of the handle B, the lamp can be turned in any direction. The adjustable fan R serves to accelerate or retard the speed of the clock. The works are set in motion by pressing down the button A and stopped by pressing the button in the contrary direction. In order to carry away rapidly the magnesia formed by the burning magnesium, an artificial draft is arranged, which, as the front of the lamp is enclosed by a glass door, escapes into a chimney above, through the space between it and the reflector. While the outer atmospheric air is allowed a free entrance by an opening beneath, The magnesium vapor rises up the chimney, and thus the reflecting mirror and the room in which the combustion takes place escape contamination from the fumes. Another excellent lamp of this kind, contrived by Professor Morton of Philadelphia, is represented in Figure 5. The clockwork is placed at the lower part of the case at the back, above which stand 2 reels of magnesium wire. In the front part of the case are fixed the 2 cylinders through which, by means of clockwork, the bands of magnesium are pushed beneath the chimney towards the opening in front, where they are ignited. The atmospheric air is allowed a free entrance to the place of combustion, both in front and at the sides, so that a powerful draft is created, by which the fumes of magnesia are carried up the chimney, in the lower part of the chimney. Below the light work eccentric cutters, by which the ashes formed by the combustion are removed from time to time. Above the chimney is placed a bent tin tube of rum from 3 to 6 feet in height, over which is fastened a bag of gauze or muslin, which, without presenting any perceptible hindrance to the current of air, prevents the magnesia dust from escaping. By this contrivance the light is preserved from the prejudicial influence of the vapors. It exceeds in brilliancy that of the lamp described above, and burns with steadiness and regularity. We have dwelt the longer on this light since magnesium plays so important a part in spectrum analysis. But the heat which its combustion generates cannot be used for volatilizing other substances and rendering them luminous, as its brilliancy is so great as to completely overpower their light. Under these circumstances we must seek for a flame, which, with the least possible luminosity, shall yet evolve sufficient heat to fuse most metals. Such a flame chemistry furnishes us in the oxyhydrogen blowpipe. Chapter 5. The oxyhydrogen flame in the Bunsen burner. The combustion of coal gas ensues slowly and incompletely. Slowly, because the oxyhydrogen flame, and which appear to belong to volatilized magnesia. The light of magnesium burning in air seems to have a threefold source: luminous vapor of magnesium, luminous vapor of magnesia, but chiefly incandescent solid magnesia from the combination of the metal with the oxygen of the air. Hydrogen in combination with carbon is supplied only in small quantities, incompletely, because the gases are not mixed in due proportions, and the nitrogen of the air presents a hindrance. If, on the contrary, pure hydrogen gas be previously mixed with as much pure oxygen as will ensure its complete combustion, 2 volumes of hydrogen with 1 of oxygen with 1 of oxygen with 1 of oxygen, oxyhydrogen gas is obtained, which when ignited explodes with a fearful noise and occasions sometimes the destruction of the strongest vessels. The heat evolved by this combustion is the greatest which can, at present, be produced by chemical means, and it is sufficient to accomplish the fusion of substances which have borne unchanged the action of the hottest furnaces. To make use of the intense heat of this flame without encountering the danger of an explosion, the gases must not be mixed before ignition, nor allowed to flow out of the same common reservoir, as in that case the flame would spread into the interior and cause the ignition of the whole quantity. It is necessary so to arrange the apparatus that the gases shall reach the emission tube from separate vessels and be allowed to mix only immediately before escaping from the burner. The simplest arrangement of this kind is similar to that of the gas blowpipe in Figure 3, but with this difference, that the section of the 2 tubes should bear more nearly the relation of 2 to 1. The gases are stored in 2 separate gas bags, Figure 6, whence they reach the lamp by means of pressure. The outer wide tube of the lamp must be placed in connection with the hydrogen reservoir, and the inner narrow one with that containing oxygen. Both the tubes should be fitted with a fine brass wire netting to prevent the flame retreating into the inside, or the gas extending from one tube to the other from any cause, such as the diminution of pressure in the reservoirs. A very convenient arrangement for such an oxyhydrogen lamp or blowpipe is made by fixing onto a stand the burner C Figure 7 with its 2 tubes as in W conveying oxygen and hydrogen, the upper part of the tube C being inclined sideways, and so connected with its lower portion that kept with safety but a very short time are the wrought iron vessels which may be purchased of Mr. Ladd, Beach Street, London, filled with the gases condensed to about 20 atmospheres. These iron bottles contain sufficient gas to maintain an ordinary oxyhydrogen light for from 6 to 8 hours. They can be refilled with condensed gas at a small expense, such as a socket, pincers, a small plate, etc., and further if a screw with rackwork be so applied that the whole upper oxyhydrogen blowpipe. Drummond's limelight. Part E may be moved up and down. We obtain an apparatus which can be used for heat as well as light, and which, on account of its being so easily manipulated, may be employed for many practical purposes. To produce the oxyhydrogen flame, it is necessary to open first the cock W and allow the hydrogen to flow out for a few seconds before igniting it, that it may expel the atmospheric air remaining in the elastic tube. The hydrogen burns. Under the pressure of the weight lying upon the bag of gas, 100 pounds, in a long, faintly luminous flame, the oxygen cocks may now be carefully opened. The entrance of oxygen into the hydrogen flame being generally announced by a very faint explosion. And on gradually fully opening the tap, the flame becomes shorter and more pointed, until its luminosity almost entirely ceases. If the excess of hydrogen gas be now shut off by turning the cock W, there will be immediately formed the small, pointed, non-luminous flame of the oxyhydrogen blowpipe. It would carry us too far from our present purpose were we to describe the range of wonderful experiments in combustion which are made with the oxyhydrogen blowpipe in the lecture rooms of chemists. 2 of these will suffice to show the powerful heat produced by this flame. If a thick wire of platinum, a metal very difficult to fuse, be held in the flame, it melts immediately like wax. If a bundle of steel wires be placed in the flame, the iron sputters about in 1,000 brilliant sparks like a shower of fire, and great molten drops of the glowing metal fall to the ground from time to time, and run about in all directions. Chapter 6. Drummond's limelight, in order to make the oxyhydrogen flame a source of intense light, a cylinder. D. Figure 7 of well-burnt lime is placed upon the socket of the lamp, and the flame directed against its upper part. It begins at once to glow and throws out a dazzling light. The oxyhydrogen light, or Drummond's limelight, as it is sometimes called, after its discoverer, attains a still higher intensity. If a piece of magnesium or zirconia be substituted for the cylinder of lime, an arrangement that has often been adopted in the public illuminations in Paris, while the lime cylinder slowly consumes in the oxyhydrogen lamp, so that fresh surfaces must be constantly presented to the flame, the piece of zirconia does not waste, and remains unchanged, in spite of the most intense incandescence, as the heat as well as the light of the oxyhydrogen flame depends upon the quantity of the burning gases. It is difficult to estimate the temperature with accuracy. In a lamp in which the diameter of the outer tube, hydrogen, is 4/10 of an inch, and that of the inner one, oxygen, 1/5 of an inch, the strength of the light is at least equal to that of stearine candle. The temperature at which platinum melts is about 1470 degrees Celsius to 678 degrees Fahrenheit. But the heat of this flame under ordinary pressure is estimated by Bunsen to be 2800 degrees Celsius, 570 degrees Fahrenheit. As the oxyhydrogen light and the magnesium light are employed in a variety of ways, not only in public illuminations, but also in theatrical displays, in the exhibition of dissolving views, and in the gas microscope. So the non-luminous flame renders important service to spectrum analysis on account of its extraordinary heat, in which many substances may be rendered luminous in a state of vapor. The facility with which oxygen gas can now be produced in large quantities, and the possibility of employing ordinary coal gas in place of pure hydrogen gas combine to render the oxyhydrogen flame a cheap mode of developing an extraordinary degree of heat and light, easy and safe to manage, and sufficient in most cases to exhibit, even to a 3 degrees large audience, the physical principles of spectrum analysis and its various methods of application. Chapter 7. The electric spark to attain, however, the greatest amount of heat and light which can at present be produced, we must leave the province of chemistry, with its processes of combustion, and turn to that of electricity, where we are encountered by a host of phenomena, accompanied by an intense degree of light and heat. When the electric spark flashes from the thundercloud to the earth, it illuminates the country around with a blinding light. It ignites and melts on its way the least fusible materials. In lightning, we have the greatest heat and the most intense light which the powers of our earth are able in general to produce. But we can make no use of this electric discharge. We are scarcely even able to escape its destructive influence and to prescribe to the lightning its appointed path from the cloud to the earth. We must therefore, under such circumstances, confine ourselves to the electric discharge as produced by artificial means. Besides the well-known machines which excite electricity through the friction of a glass disc, there has been added of late a contrivance called an induction machine, which yields a rich supply of electric force and gives a spark of intense brilliancy. In all electrical motors arranged for exhibiting light, sparks are formed between two metallic poles or pieces of wire, figure 8, which are placed in contact with those parts of the machine which collect the positive and negative electricity. By the mutual attraction of the two electricities and the struggle for union, there ensues a tension of electricity at the end of the metal poles, when they are separated from each other. If this be so strong that the obstacle presented by the stratum of air between the metallic conductors is overcome by it, then the electricities are instantly united, and the union takes place in that form of light and heat which is called the electric spark. The amount of heat thus generated depends upon the degree of tension and the quantities of electricity by the union of which it is produced. But in most cases it is so great that small particles of the metal poles are volatilized and become luminous. The glowing metallic vapor affects the color of the spark, which therefore appears with various kinds of light according to the nature of the conductors. These phenomena afford us, in aid of our researches with spectrum analysis, a very simple method of volatilizing and raising to a high degree of luminosity most of the metals and other substances which are conductors of electricity. To obtain the same result with liquids, it is only necessary, as will hereafter be more fully described, to place one of the metal poles in the liquid to be examined, and to bring the other sufficiently near the surface for the spark to pass from it to the liquid. By the heat of the spark, a small portion of the liquid is volatilized and made luminous. If the spark supplied by these machines be insufficient, and a higher degree of heat be desired, an intensifying apparatus, such as a Leyden jar, or a condenser, must be placed between the two metal conductors A, B, figure 9. The spark passes between A and B only when the condenser has become charged, and the heat evolved is in proportion to the amount of electricity collected in the condenser. Gases can also be made luminous by the electric spark if enclosed in glass tubes and the spark sent through them. The discharge then takes a different color according to the nature of the gas. In hydrogen gas, it appears a purple-red; in chlorine, green; in nitrogen, violet; in oxygen, white. But this method is not advisable in general, because the heat of the spark is insufficient at the ordinary pressure to render a large quantity of gas luminous. It will presently be seen how this object may be attained by rarefying the gas. Chapter 8. The induction coil, among the most powerful motors of electricity, is that apparatus which, by means of a comparatively weak electric current acting on every part of a thin wire many thousand feet in length, and completely insulated, produces electric sparks of such length and tension that they may bear comparison even with lightning. The small instruments of this kind, which are frequently employed in medical practice, are known by the name of induction coils. Those of larger size are called, after their inventor, Ruhmkorff's induction coils, and are now so constructed that with moderate dimensions they give sparks from 12 to 16 inches in length. If a long strip of gummed paper be strewed with copper filings and brought when dry in connection with the poles of the induction coil, the current runs over the whole path of the file, and passes from one particle to another with such rapidity as to give to the chain of successive sparks the appearance of one long stream of lightning. In this way sparks can be formed of from 12 to 16 feet in length, which by their form, brilliancy, and loud report bear the closest resemblance to lightning, for most purposes of spectrum analysis. An induction coil of moderate strength is sufficient. The poles are constructed of platinum, because this metal is able to withstand the heat of the sparks, which, when the instrument is in operation, pass between them with a loud crackling noise, and follow each other in such quick succession that they appear as one continuous stream of light of intense brilliancy. As the induction coil, when once set to work, is self-acting, it is much more suited to the requirements of spectrum analysis than those machines which supply electricity only so long as their glass discs are in revolution. Chapter 9. Luminosity of Gases. Geissler's tubes' fine condition are good conductors of electricity, while they are without exception bad conductors when in a state of greater density. At the time when Bunsen and Kirchhoff first introduced spectrum analysis into science, it was known that in an egg-shaped glass vessel, figure 10, in which the air had been rarefied by an ordinary air pump to a pressure of from 1 to of an inch of mercury, the electric current would pass with the greatest readiness. In the form of a luminous arch between the metal knobs enclosed in the airtight vessel, even when the knobs were 8 or 10 inches apart, an envelope of blue light surrounding the ball by which the negative current entered, and a brush of reddish light being emitted from the positive ball. If small quantities of the vapors of certain substances, such as alcohol, phosphorus, or turpentine, be introduced into the glass vessel before rarefying the air, the spray of light will not merely be electric egg, colored according to the nature of these vapors, but there will be also a series of dark stripes breaking crossways through the light, which therefore, as it disperses from the metal knobs, will no longer be continuous, but be interrupted by dark strata. The study of these phenomena has been simplified and considerably extended since Dr. Geissler of Bonn, by a new method of rarefying air, succeeded in producing a vacuum in glass tubes, in which the gases to be investigated could be enclosed in a state of extreme attenuation, and which by means of 2 platinum wires soldered at the end of the tubes could be brought into connection with the poles of an induction coil. These phenomena vary exceedingly according to the form and composition of the glass of which each portion of the tube is composed, but especially according to the nature of the gas enclosed and its degree of tenuity. Figure 1.1 shows a compound Geissler's tube of this kind when in contact with the poles of the induction coil and the gas rendered luminous by the passage of the electric current, those portions of the Geissler's tube which are filled with rarefied atmospheric air or nitrogen, emit a beautiful red light. Carbonic acid and carburetted hydrogens give green and white tints. In a dark room, these tubes present a splendid spectacle by the alternate strata of dark and brilliant parts, the purity of the colors, and the variety of forms into which the glass has been manufactured. Geissler's tubes furnish a very convenient means for rendering any gas luminous, but the intensity of the light emitted by the gases when enclosed in these tubes is for the most part too small for the purposes of spectrum analysis. For the spectrum of such a tube can be examined only when every other light is withdrawn. Professor Plicker of Bonn, who among the various scientific men distinguished for their labors in the development of spectrum analysis, holds a foremost place, and whose researches on the spectra of gases are of the highest value, concentrated this faint light by causing Plicker's tube. The electricity to pass through rarefied gas confined in a very small space, and this he successfully accomplished by substituting very narrow capillary tubes for the wider ones previously used. Let us examine a series of Plicker's tubes as prepared for the purposes of spectrum analysis. The first of these is almost reduced to a vacuum. At least the small amount of gas in it does not produce a greater pressure than of an inch of mercury. The second tube, figure 12, where the central portion, a B, is capillary, encloses extremely rarefied hydrogen gas, the third nitrogen, the others oxygen, chlorine, carbonic acid, and minute traces of the vapors of iodine, sulfur, quicksilver, selenium, etc., if these tubes be brought singly into connection with an induction coil, in order that the current may pass between the platinum wires A and B, and render the gas enclosed luminous. The first tube shows no appearance of light, although the wires are barely separated of an inch, and the spark could be discharged in air at the distance of 2 or 3 inches. It therefore follows that the electric current requires a material conductor for its transmission from one wire to the other, and that it cannot pass where there is no trace of either gas or vapor, that is to say, in vacuum. In the other tubes, however, the light passes through the narrow portion of B with considerable intensity, and is visible at some distance as a sharply defined line, bearing a very decided color peculiar to the luminous gas. These tubes therefore supply a means of rendering gases and vapors luminous. They emit under the influence of the electric current a brilliant line of light which is well adapted for observations of the spectrum of the enclosed gas. Chapter 10. The voltaic arc, the electric light. It will be well now to turn our attention for a short time to that source of electricity which is able to evolve the highest degree of heat with the most intense light, namely the voltaic arc, or the electric light. When the poles CZ of a powerful voltaic battery, such as a Bunsen battery of 50 or 60 elements, figure 13, are connected by means of two metal wires with two pieces of carbon AB, figure 14, and these brought into contact, the electricity generated by the battery is discharged between them through the carbon, which is nearly as good a conductor as the metal. If these pieces of carbon be pointed at the ends, an extraordinarily intense light is emitted on the passage of the current at the points of contact, and they may be separated 1 or 2/10 of an inch without interrupting the discharge. If the copper wires K, Z from the poles of the battery be connected with the metal rods AB, in which the carbon points AB are fixed, the electric current cannot break through the stratum of air between these points so long as they are not in contact, though this would easily be effected were the electricity of high tension from an electrical machine or an induction coil. If the upper metal rod A, which carries the negative carbon, be brought down so as to bring the 2 points in contact, there starts out at the same instant a bright point of light, which, in proportion as the poles are separated 1/10 of an inch or more, increases in extent and power, filling a large space with its brilliancy. The light is suddenly extinguished if the carbon points are still further separated. If by pushing down the movable rod A the points are again brought into contact, reproducing the light, then separated a little, and the machine left to itself, it will be seen after a while by the use of a dark glass that the distance between the points increases and that their form is constantly changing. After a short time, the light goes out of itself, because the distance between the points has become so great that the electric current can no longer overcome the resistance of the intervening stratum of air. It is not prudent to expose the eye to a near inspection of this dazzling light, and dark glasses prevent the delicate changes which are taking place from being observed with sufficient distinctness. It is therefore advisable, after the example of Leroux, to throw upon a white screen an enlarged image of the glowing carbons by means of a magnifying glass, when the appearance of the incandescent carbons and the intervening arc of flame may be observed from a distance without injury to the eyes. 4. For this purpose the room must be darkened, and a somewhat different arrangement employed for holding the carbon points in the lamp. Figure 15, this apparatus is provided like a magic lantern with a lens L of suitable focal distance, placed in front, and a concave reflecting mirror S behind. A diaphragm is placed before the lens, in which an opening of medium size, about 1/8 of an inch, is selected, the electric current allowed to enter, and the lens pushed backwards and forwards until the magnified image of the carbon points is quite distinct on the white paper screen P, placed about 13 feet, the carbon points of the electric light, from the lamp. With this image, figure 16, in which the carbon points are magnified 100 times and made to appear the length of 6 feet, the slight changes going on in them can be easily observed. It will be noticed at the first glance that the intense light is emitted by the incandescent carbon, and that the arc of flame flickering between the points, called the voltaic arc, is comparatively little luminous. It will be remarked also that one of the carbon points begins to increase at the expense of the other. That which first loses its point and wastes the fastest is always the one which is in connection with the positive pole, the carbon pole of the battery. Very intensely bright particles pass from time to time from the positive to the negative carbon, Little globules are to be seen running about on the surface of the carbon, globules of melted silica, a substance always to be found even in the purest carbon. These are the enemies of the electric light, for they give by their motion a certain irregularity to the arc of flame. And as they are much less brilliant than the carbon, they considerably abate the intensity of the light. Should these globules, by their restless movements, reach the hottest part of the points, where the strongest light is emitted, their rapid motion is made known by a hissing noise, but unfortunately also by a sudden diminution of the light. When the carbon points have become so separated that the voltaic current has difficulty in passing, by means of the incandescent particles, through the air from one pole to the other, the strength of the current suddenly diminishes, and in like proportion the light begins to wane. This is at last extinguished because the electric current can no longer build itself a bridge out of the glowing particles on account of the distance of perhaps half an inch by which the points are then separated. It is evident from what has been stated that the electric light is certainly very intense, but also very uncertain, and that a special contrivance is required to make the electric arc a source of continuous and steady light. In order to adapt it to optical purposes, such as projecting an image on a screen to be seen by a number of spectators in the same way as sunlight or Drummond's limelight is employed, a further contrivance must be added to ensure the fixed position of the light by keeping the carbon points not only at the same distance from each other, but also in the same position relatively to the lenses forming the image, notwithstanding the continual consumption of the carbon. Chapter 11. How thereby the electric lamp, the ingenuity of scientific and practical men, has succeeded in overcoming most of these difficulties by the construction of various kinds of apparatus by which the point of light between the carbons may be kept steadily in the same place for hours together, provided the carbon employed be quite pure, and the strength of the battery tolerably uniform. But all of these lamps, among which those of Foucault and Sarin hold the first place, are extremely complicated, and require constant watching while in use, on account of the extreme difficulty in procuring carbon of the requisite purity and hardness. The electric lamp constructed by Dubosc at Paris, on Foucault's plan, figure 17, is a masterpiece of mechanism, and is in every way suitable for the combustion of metals and the exhibition of spectra. Without entering into all its mechanical details, it is sufficient here to remark that the works are regulated by the magnetic power of the voltaic current in such a way that, in proportion as the carbon points are separated by the waste of combustion, the carriers G and H are again made to approach. The wires from the battery are connected with the lamp by the binding screws YZ, and so arranged that the current must pass through the coil of the electromagnet E to reach the carbon holders G, H. It is easy by means of the screw wheel. So to regulate the armature A of the electromagnet with its spring R, that it shall remain drawn down when the carbon points are at the proper distance, about 1/10 of an inch. By the drawing down of the armature, the rod K lays hold of a portion of the wheelwork, and holds it still. When, in consequence of the combustion of the carbon, the distance between the points increases, the strength of the voltaic current diminishes, and the magnet E, becoming weaker in the same proportion, lets loose the armature A before the points have become so far separated as to break the current. The rod K by this movement is pushed aside, and sets the clockwork free, which, beginning to act, pushes the two racks G and Jol, which latter is movable up and down the tube M, carrying the holders G and H at a different rate of motion in opposite direction, so that the rod G, connected with the positive pole, is moved nearly twice as fast upwards as the rod door is sent downwards. The carbon points have scarcely again approached, when the voltaic current and the power of the electromagnet are raised to their original strength, the armature is attracted, and the clockwork stopped. By this mechanism, the carbon points can never be so far separated as to cause the extinction of the light, for the holders are moved at a rate proportional to that at which the waste of carbon takes place, the lower positive carbon being consumed twice as quickly as the upper negative one, and therefore the light is not only made continuous by this mechanism, but is kept immovably at one and the same place, By means of the screw D, the racks G and L can be moved independently of the clock, and by a third screw, to be found on the opposite side of the instrument, the upper rack can be also moved by itself. In this way, the experimenter has the power, before applying the electric current to the lamp, to place the arc of light in that position in the apparatus which the lens may require. The second function of the clock is to separate. Without the interference of the experimenter, the carbon points, which must be brought into close contact in order that the voltaic arc may be formed between them and the carbon attain its highest incandescence. The separation is accomplished by the racks G and Dwar, which before move forwards being made to go backwards by means of two connected cogwheels, which can work them in either direction. A contrivance which helps to make the electric lamp one of the most complicated, but at the same time one of the most ingenious and complete instruments employed in the illustration of physical science. The intensity of the heat and light from the voltaic arc depends upon certain circumstances, but principally upon the amount of electricity generated, and therefore on the number and nature of the elements employed, and on the purity of the carbon points. With a medium-sized battery, consisting of 50 or 60 of Bunsen's or Grove's elements, the light varies from that of 400 to 10 stearine candles, according to the purity of the carbon points, and their distance from one another. Fizeau and Foucault have compared the chemical power of the electric light with that of the sun by means of iodized silver plates, and found that the electric light from a Bunsen battery of 46 elements could be expressed by the number 235. Supposing sunlight at noon on an August day to be represented, the light from a Bunsen battery of 100 elements produces much discomfort to the eyes. According to Desprez, a single glance, even with the naked eye, is sufficient when 600 elements are employed to occasion considerable injury to the eye and a long-continued headache. Even when only 60 elements are used, it is desirable to avoid looking directly at the naked light and to protect the eyes with deep blue spectacles during the experiments. We are now in possession of all the sources of light and heat requisite for a complete exhibition of the laws and phenomena which relate to the spectrum analysis of terrestrial substances and the heavenly bodies. We shall employ in our illustrations. According to the nature of the subject, sometimes the Bunsen burner, sometimes the oxyhydrogen or the Drummond light, sometimes the induction coil and Geissler's and Plicker's tubes, and also frequently the electric light. The phenomena of spectrum analysis can be easily shown with simple means to a small circle of spectators, where everyone can approach the apparatus and the experimenter's table. But their exhibition before a large audience numbering many hundred persons requires extraordinary means of demonstration, and the use of the strongest light and the most powerful heat that can be produced by artificial means. Chapter 12. Light. Although the theory of light is now so completely understood that we are able to explain the most complicated optical phenomena, yet an elementary reply to the question, what is the nature of light, still presents some difficulty. We perceive the operation of this power of nature in all directions and in the most manifold ways. The sun, as it stands in full splendor in the heavens, pours forth but a single tone of color over the earth. And yet the individual objects in the landscape appear in the most varied and glorious tints. What then are these colors? How are they developed out of the white light which the sun and other luminous bodies emit? We need not seek to avoid answering this question if we can succeed in giving a clearer insight into the phenomena of spectrum analysis. For we have already intimated that the world of color is the peculiar province of this new method of investigation. The approaches to science are frequently obstructed by strange propositions, discouraging and apparently contradictory, which seem to the uninitiated like those ghosts that haunted the way by which Dante and his heavenly guide descended to the realms of the departed. With a little courage, however, we may easily traverse this dreaded path, seize hold of harmless apparitions, and make friends first with one and then with another as we approach them. We will therefore boldly grasp the proposed inquiry. If the answer to it cannot be exhaustive, it will at least contain material enough to incite to further reflection, and perhaps also afford the necessary basis for a more easy comprehension of the elaborate theories which are enunciated in physical treatises. According to the theory generally received at present, the whole universe is an immeasurable sea of highly attenuated matter, imperceptible to the senses, in which the heavenly bodies move with scarcely any impediment. This fluid, which is called ether, fills the whole of space, fills the intervals between the heavenly bodies, as well as the pores or interstices between the atoms of a substance. The smallest particles of this subtle matter are in constant vibratory motion. When this motion is communicated to the retina of the eye, it produces, if the impression upon the nerves be sufficiently strong, a sensation which we call light. Every substance, therefore, which sets the ether in powerful vibration is luminous. Strong vibrations are perceived as intense light, and weak vibrations as faint light. But both of them proceed from the luminous object at the extraordinary speed of 186 miles in a second, and they necessarily diminish in strength in proportion as they spread themselves over a greater space. Light is not therefore a separate substance, but only the vibration of a substance, which according to its various forms of motion generates light, heat, or electricity. Chapter 13. Analogy between light and sound. This representation of the nature of light ceases to be surprising when we come to compare the vibrations of ether with those of atmospheric air, and draw a parallel between light and sound, between the eye and the ear. A string set in vibration causes a compression and rarefaction of the surrounding air. In front of it, the air is pushed together and condensed. Behind it, the vacuum it creates is filled up by the surrounding air, which thus becomes rarefied for the moment. This periodic movement of the air is transmitted to our ears at the rate of about 100 feet in a second. It strikes against the tympanum and occasions by its further impulse on the auditory nerves and brain the sensation we call sound. Air in motion, by its influence on the organs of hearing, is the cause of sound. Ether in motion, by its influence on the organs of sight, is the cause of light. Without air or some other medium whereby the vibration of bodies can be propagated to our ears, no sound is possible. As a sonorous body throws off no actual substance of sound, but only occasions a vibration of the air, so a luminous body sends out no substance of light, but only gives an impulse to the ether, and sets it in vibration, a musical sound. In contradistinction to mere noise, is produced only when the impulses of the air reach the ear at regular intervals. If the intervals between the impulses are not sufficiently regular, the ear is only conscious of a hissing, a rushing, or a humming noise. A musical sound requires perfect regularity in the succession of impulses. The pitch of a musical note depends on the number of impulses in a given time, as, for instance, in a second. The greater the number of vibrations in a second, the higher will be the note produced. When the single impulses are fewer than 16 or more than 40, in a second, the ear is no longer sensible of a musical sound. In the first case, it either perceives only an undefined deep hum, or else it distinguishes the individual strokes upon the tympanum and becomes sensible of them as distinct blows. In the latter case, there is an impression of a sharp but equally indefinite shrill or hissing noise. The limits of susceptibility of the ear for musical sounds lie between 16 and 40 impulses per second. The number of vibrations in a second given by a normal tuning fork was determined in the year 1859 to be 435 in a temperature of C. The truth of the foregoing statements may be easily proved in the following manner. A disc of zinc, A, figure 18, is fastened to an axis which can be set in rapid rotation by means of a cord working over a large wheel. The disc is perforated with 8 series of holes placed along 8 concentric circles, of which only 4 are given in the drawing. The holes are of the same size in each circle, and at equal distances from each other, so that their number increases in each ring from the center to the edge. When the disc, by means of the large wheel, is set in uniform motion at the rate of 1 revolution in a second, and 1 circle of the holes is blown upon with considerable force through a glass or metal tube, be it known as her, by blowing upon the next series higher, the note is of a higher pitch. A lower set of holes gives, on the contrary, so that if all the rings were blown upon in succession from the lowest upwards, the distinct notes of the complete octave would be heard. This apparatus has received the name of the siren. Her notes are not indeed ensnaring. Nor does she threaten philosophers with the dangers of the Homeric heroes by the seductive charm of her voice. On the contrary, she sings nothing but truth, if only a willing ear be lent to her song. What is it that here produces the sound? The mere revolution of the disc makes no noise. The motion of the air by the blowing through the tube first elicits the notes. When by the rotation of the disc the current of air strikes against an opening, it presses through it. Pushing the air before it and condensing it, this impulse reaches the ear at once and strikes upon the tympanum. The current of air immediately afterwards comes against the solid part between the holes, by which it is interrupted. If the circle blown upon contained 24 openings, the ear would receive 24 impulses at every revolution of the disc, and if the disc made 20 revolutions in a second, the ear would receive 20x24, 480 impulses in the same interval. The outside circle has twice as many openings as the innermost one. It therefore furnishes with the same speed of rotation 20x48 equals 960 impulses in a second. The ear cannot distinguish the individual impulses when they exceed 16 in a second. The impressions they then produce become blended together, the one following the other so instantly that the sensation in the ear is that of one continuous impulse or sound. The pitch of a note is thus seen to depend entirely upon the number of successive impulses following each other at the same uniform rate. Its strength upon the force of the impulse. With a stronger blast, the pitch of the note remains unchanged, but the tone becomes more piercing, while if a ring containing a greater number of holes be blown upon, the pitch rises till in the last circle, with double the number of openings. The octave of the same note is heard that was given by the innermost circle. It is true that the cause of sound is not the same in all musical instruments. Sometimes it is the vibration of strings or elastic prongs, sometimes stretched membranes, or again columns of air confined in tubes which create at regular periods a condensation and rarefaction of the air. But in every case a note can only be produced by similar impulses recurring at regular intervals, conveyed by the air to the organs of hearing. Savart exhibited the cause of sound in another way, which is not less instructive than the one just described. Instead of the perforated disc, he made use of a wheel provided with 600 teeth, which could be set in very rapid rotation in the same manner as the disc, and as the wheel revolved, the teeth were allowed to press against the edge of a card. To make this experiment, it is only necessary to substitute a toothed wheel for the perforated disc, as shown in the apparatus in Figure 19. And while the wheel is in rapid revolution, to hold a thin card or a piece of pasteboard against its toothed edge. The card is bent a little by each tooth as it goes by, and springs back to its first position as soon as it is released by the passing of the tooth. The motion of the card is communicated to the surrounding air, and reaches the ear in consequence of the regular revolution of the wheel, in the form of waves of air or of condensations and rarefactions of the air following each other at regular intervals. When the wheel is turned slowly, there is heard only a succession of taps or isolated impulses of the card, distinctly separable one from another, which do not as yet unite to form a musical sound. In proportion, however, as the rapidity of the rotation is increased, the number of impulses increases also, and they unite in the ear to produce musical notes, rising continually in pitch. A small recording apparatus fixed to the axle of the tooth wheel gives the number of revolutions in a second. If this number be multiplied by 600, the number of teeth on the wheel, the result gives the number of condensations of air striking the ear in a second. It is easy by this means to determine the number of vibrations the ear receives in a second from a note of any given pitch, and thus to verify the results obtained by the perforated disc. It will now be easier to understand the motion of ether and its mode of operation on the organs of sight. Ether as well as air can be set in regular vibrations, and even in such a manner that the phases of condensation and rarefaction are repeated at regular periods of time. The difference between the vibrations of the air and the ether is occasioned by the remarkable delicacy and elasticity of the latter, which not only permits a greater rapidity in the propagation of motion than is possible with the coarse and heavy particles of air, but also allows the number of vibrations per second to be immensely greater, so that their number has to be reckoned by billions. Chapter 14. Analogy between musical sounds and colors. Colors are to the eye what musical tones are to the ear. A certain number of ether impulses in a second against the retina of the eye are necessary to produce the sensation of light. If the number of these waves pass above or below a certain limit, the eye is no longer sensible of them as light. The first sensation of these vibrations on the part of the eye commences at about 450 billion impulses in a second, and the eye ceases to perceive them when they have reached double this number, or about 800 billion. In the first case, the impression produced is that of dark red, in the latter of deep violet. The greater the number of vibrations in any given time, the more rapidly must the single impulses succeed each other. It may be concluded, therefore, that the different colors are only produced by the different degrees of rapidity with which the ether vibrations recur, just as the various notes in music depend upon the rapidity of the succession of vibrations of air. The vibrations which recur most slowly, amounting, however, to at least 450 billion in a second, give the sensation of red. Those recurring more rapidly produce that of yellow. And if the rapidity with which the impulses succeed each other continue to increase, the sensation becomes in succession green, blue, and violet, with which last color the human eye becomes insensible to the ether motion, which, however, is still very far from having attained its limit of rapidity. The gradation of the colors from red through yellow, green, and blue to violet is to the eye what the gamut is to the ear, and it is therefore not without reason that we speak of the tone and harmony of color. To the physicist, the words color and tone are only different modes of expression for similar and closely allied phenomena. They express the perception of regular movements recurring in equal periods of time. In ether producing colors, in air musical sounds. In the former instance, by means of the organs of sight, in the latter, by the organs of hearing, movements of extreme rapidity in ether, of more moderate speed in air. But it will be asked what becomes of those vibrations which are above and below the limits of the eye's sensibility to light and color. Do they wander about purposeless and unnoticed? By no means. Forces are proved to exist in the rays of the sun and other intensely luminous bodies which cannot be perceived by the eye. Those slower vibrations which, though they are reckoned by billions in a second, do not yet amount to 450 billion, are made apparent to us in the sensation of heat, which is also the result of oscillatory movement, radiant heat being, like light, propagated without the aid of foreign bodies. On the other hand, which have a velocity greater than that by which deep violet is produced, at which color the eye's susceptibility to light ceases, reveal themselves by their powerful chemical action. They succeed each other too rapidly for the visual nerves to be any longer conscious of the impulses, but they have the power of working chemical changes, and the decomposition of various substances can be undoubtedly traced to the agency of these invisible rays. An English physicist has succeeded in moderating the excessive velocity of these vibrations by means of certain substances, and in this way has brought some of the invisible chemical rays within reach of the eye's susceptibility. Hashdove describes, in his own ingenious manner, the course of the vibrations as they produce successively sound, heat, and light as follows. In the middle of a large darkened room, let us suppose a rod, set in vibration and connected with a contrivance for continually augmenting the speed of its vibration. I enter the room at the moment when the rod is vibrating 4 times in a second. Neither eye nor ear tell me of the presence of the rod, only the hand, which feels the strokes when brought within their reach. The vibrations become more rapid, till when they reach the number of 32 in a second, a deep hum strikes my ear. The tone rises continually in pitch, and passes through all the intervening grades up to the highest, the shrillest note. Then all sinks again into the former grave-like silence, while full of astonishment at what I have heard, I feel suddenly by the increased velocity of quinine was observed by Sir John Herschel, and the colored light diffused from various vegetable solutions and essential oils was subsequently examined by Sir David Brewster. To Professor Stokes, however, is due the true explanation of these phenomena. He showed that the blue light of the solution of quinine consists of vibrations brought within the limits of the power of the eye, which were originally too rapid to be visible. If a fresh infusion of the bark of the horse chestnut be placed beyond the limits of the visible spectrum of sunlight, admitted through a slit into a dark room, it becomes beautifully luminous, in consequence of the power which it possesses to lower the invisible ultraviolet vibrations into light which can affect the eye. Vibrating rod, an agreeable warmth as from a fire diffusing itself from the spot whence the sound had proceeded. Still all is dark. The vibrations increase in rapidity, and a faint red light begins to glimmer. It gradually brightens till the rod assumes a vivid red glow. Then it turns to yellow and changes through the whole range of colors up to violet. When all again is swallowed up in night, thus nature speaks to the different senses in succession. At first, a gentle word audible only in immediate proximity, then a louder call from an ever-increasing distance, till finally her voice is borne on the wings of light from regions of immeasurable space. Chapter 15. Refraction of light. Light does not, like sound, require a ponderable material for its propagation. It comes to us from the remotest regions of space, and it penetrates the vacuum we may create in our laboratories with the greatest ease. But when light passes through a stratum of air, through water or glass, a portion of the ether motion appears to be destroyed, absorbed, and this absorption is so much the greater, the further the distance the light has to travel through these bodies. Thus objects are seen with perfect distinctness through a thin sheet of glass, while through a thick piece they are less clearly visible and are sometimes almost obliterated. So long as light passes through a completely homogeneous medium possessing the same density throughout, it is transmitted in a straight line. But it is quite otherwise when it passes from one medium to another of different constitution. When, for example, a ray of light coming through the air strikes upon the surface of water or upon a sheet of glass, and afterwards passes through these denser substances, it deviates from its straight course the moment it touches the new medium, excepting only when it falls perpendicularly to the surface separating the two media. This deviation of the ray of light from its straight course is called refraction. It occurs in all cases where light passes obliquely from one medium to another of different density or constitution. If a straight stick be held half in air and half in water, the portion that is in the water does not seem to be the straight continuation of the upper part. The rod appears as if it were bent at the surface of the water. The laws of refraction can be deduced with strict consistency and with mathematical precision from the theory of light which has been already enunciated. For our purpose, however, it will suffice to consider in detail only the most important of them. If, for example, the ray Ri, figure 20, pass from the air into water at I, it will pursue its path through the water, not in continuation of the straight line Ri, therefore not in the direction of I rho, but in that of S, which is nearer than I rho to the perpendicular IO erected on the surface of the water at the point I. The refracted ray as remains in the same plane, RRIQ, formed by the incident ray Ri with the perpendicular IQ. And in this plane, the angle RIO formed by the ray Ri with the perpendicular QP in the rare medium, air, is, with very few exceptions, greater than the angle SIP formed by the ray IS with the perpendicular QP in the denser medium, water glass, etc. On passing from a rarer into a denser medium, the ray is usually bent towards the perpendicular in the denser medium, and conversely, on passing out again from the denser into the rarer medium, it is bent from the perpendicular. The relative proportions of the two angles RIO and SIP may be ascertained by describing a circle with any radius from the point I and letting fall the perpendiculars TU and SP from the points of intersection T and S upon the line QP. These perpendiculars are called the sines of the angle which they enclose. Thus, TU is the sine of the angle of incidence TIU, and SP is the sine of the angle of refraction SIP. And the sines are subject to the following universal law of refraction. For the same two media, the proportion of the sines of the angles of incidence and refraction is a constant quantity, whatever the angle of inside is 7 is. SP is, for example, for air and water as 4:3, whence it follows that at whatever angle the ray Ri in the air may strike the surface of the water, the refracted rays will be so deflected that Tu shall be 2SP in the proportion of 4:3. This invariable ratio between the sines is called the index of refraction of the media. The index of refraction for air and water is therefore expressed by 4:3 or more accurately by 134. For air and glass by 3:2 or 153. As the index of refraction varies according to the nature of the medium, it will necessarily have a very unequal value for different kinds of glass. It is, for example, for air and crown glass 1534, while for air and dense flint glass it is 1 EA645. The refracting power, therefore, of flint glass is much greater than that of crown glass under similar conditions. If a ray of light, as SI in figure 2.1, be transmitted from the air through a medium MM with parallel sides, for example, through a plate of glass, then a simple construction deduced from the preceding law will show that the incident ray SI will be diverted at I towards the perpendicular ion in the direction IR, but that on its emergence from the glass at R, it will again deviate to an equal amount from the perpendicular R none, so that in whatever direction the incident ray SI may fall, the emergent ray R falls always remains parallel to it, would receive the incident ray SI in the direction RF, and would see the luminous point S, whence the ray SI emanated, in the direction R sun, so that this point would appear in a different place, sun, to that which it really occupies. Path of the rays through a medium with parallel sides. By the same principle can the daily phenomenon be explained that in looking through a window, though the rays pass from the air through the glass before reaching the eye, the outside objects do not appear either distorted or broken, as is the case with the stick held in water. Refraction does, in fact, occur in all those places where the line of sight is not perpendicular to the pane of glass. The objects are, notwithstanding, free from distortion because the incident and emergent rays are parallel, though they do not form continuous straight lines. Consequently, as the displacement of the rays is everywhere the same, the objects appear through the window in the same relative positions as when viewed without the interposition of the glass. It may be easily proved that the images of all objects seen through a window pane are really displaced and appear in a different position from the one they actually occupy, by comparing one part of them seen through air alone with another part seen through glass. As this displacement is but small through thin glass, it will be well in making the experiment to choose a piece of thicker glass and always to look at the objects obliquely. If a piece of thick glass, figure 22, be laid on any drawing so as only to cover one half in order that one part may be seen through air and another through glass, the displacement of the portion under the glass will be seen clearly when the drawing is looked at obliquely. The refraction of light may be demonstrated to a large audience in the following manner. By the use of the oxyhydrogen light, part 50, p28. The oxyhydrogen lamp is placed in the same lantern which was used for the representation of the electric light, part 50, figure 15. The rays emitted by the incandescent lime K are rendered parallel by the lens of figure 23. In the inside of the lantern, and in this form, they pass through the ring R across which is fixed a brass arrow. By means of another lens, LR, placed at the same height as the arrow, but at some distance from it, an enlarged inverted image, PP, of the arrow is obtained upon the screen, and the image may be made perfectly distinct by adjusting the lens. A rectangular parallelopipe bar of glass, AA, is then held against the arrow, so that the parallel rays of light passing through the ring are perpendicular to the sides of the glass. No change is perceived in the image of the arrow itself. Only the part where the glass bar depicts itself is somewhat less illuminated than the rest of the screen, which is caused by the absorption of a portion of the light in passing through the thick glass. It may be concluded, therefore, that those rays of light which pass through the glass perpendicularly to its sides have not been diverted from their straight course. If, however, the glass bar be held obliquely against the arrow, the rays of light proceed no longer in a straight course between it and the lens LJ, but are turned on one side, as may be seen in the corresponding piece of pipe. The image of the arrow B, which appears displaced sideways from the shaft. The same phenomenon is seen if instead of an opaque arrow, a disc, in which there is a narrow vertical slit, be inserted in front of the lantern. A B in figure 24 represents the enlarged image of the slit upon the screen, a bright sharp line. If the glass bar G be held flat against the disc, so that the rays of light passing through the slit are perpendicular to the surfaces of the glass, there appears only a slight dimness in the corresponding spot C of the image, in consequence of the partial absorption of the light by the glass. If, however, the glass be inclined against the slit, the corresponding portion of the image is displaced to the right or left according to the inclination of the glass bar, and the image of the slit appears broken. If the experiment were repeated with a cube of glass twice, the thickness in place of the half-inch glass projection of the slit and displacement of the rays by refraction bar, the absorption and displacement of the light would be much more strikingly exhibited. Chapter 16. Refraction of monochromatic light by a prism. Let us now consider what occurs when, with two media of unequal density, such as air and glass, the outside surfaces of one of them, instead of being parallel, form an angle with each other, as for instance in a three-sided glass prism, figure 25. For the convenient handling of such a prism, so that it may be turned about without the glass surfaces being touched, it is usually mounted on a brass stand. As shown in figure 26, when the edges where the surfaces unite can be placed at will in a horizontal or vertical direction. In order to follow the path of a ray of light through a prism, let ABC, figure 27, represent the section of a prism standing on its base, and let the ray DE fall in the plane of the section upon the surface of B. The ray on entering the glass is bent towards the perpendicular face in the direction at. After passing through the prism in a straight course, it is again bent at H on emerging into the air, and is permanently deflected from the perpendicular GH in the direction HE. The ray DE therefore takes the direction HE when a prism is interposed in its path, while were the prism removed, it would pursue its original course along the straight line D theta. It will thus be seen that the incident ray DE is deflected by the prism neither in a straight line nor in a parallel direction. Theory and experience have both established that in every case, the incident ray is diverted from its original straight course in such a manner that the emergent ray is bent towards that surface of the prism, the base, through which it does not pass. The edge opposite the base CB is called the refracting edge. The solid angle B is C, formed at that point. The refracting angle and the angle formed by the emergent ray is E, with the course DD of the incident ray is called the angle of deviation, or angle of refraction. Incident ray as I passes through the prism after its first refraction at I in the direction IE. It becomes refracted a second $10 as it emerges at E, and then proceeds in the direction ER. In all the three figures, the dotted lines and indeed none are drawn perpendicular to the surfaces of the glass. The ray is deflected in the denser medium of the glass toward this perpendicular, while it is bent away from it in the rarer medium of air, so that the angle it makes with the perpendicular is always greater in the air than in the glass. In the second figure, the incident rays, I passes unrefracted through the prism in the direction IE because SI is perpendicular to the surface of the prism. In the third figure, the incident ray as I and the emergent ray ER form the same angle with the surfaces of the prism, in which position there occurs the smallest divergence of the emergent ray, IR, from the direction of the incident ray, IS. And this is therefore called the position of minimum of deviation. A luminous point is seen, as is well known, in the direction in which the rays proceeding from it reach the eye. If, therefore, the rays from a candle, figure 29, are made to pass through a prism before reaching the eye, and the prism so placed that the rays are bent down towards the base, the eye sees the flame in the direction of the emergent rays, in a higher position than it really occupies. If, on the contrary, the prism be turned around, so that the base is uppermost, the rays of light will be bent upwards, and the eye, on receiving them, will see the flame in a lower position. Chapter 17. Refraction of the different colors by a prism. A prism. We have hitherto paid no attention to the nature of a ray of light, and have therefore only made divergence of the different colored rays in passing through a prism. Acquaintance with those phenomena of refraction which are common to rays of every description. Let us now consider the behavior of the different colored rays in their passage through a prism. For this purpose, let a diaphragm in which is a circular hole of about 1/8 of an inch in diameter be placed immediately in front of the lantern. A, figure 30, and the aperture covered with a thin piece of glass M, colored red with oxide of copper. By interposing the lens L, a small red circle AI, the image of the aperture A will be seen immediately opposite on the screen SS. If the glass prism NPO be inserted in the path of the ray between L and L in the place indicated in the figure, the red circle on the screen will move from AS to RRB. The light from a which fell upon the prism in the direction of B is thus considerably diverted from its straight course, all 9, so that the emergent ray CR has moved further away from the edge N, where the two refracting glass surfaces unite, and has approached the opposite surface PO, the base of the prism. If green light be examined by the interposition of a green glass, the ray emerging near C no longer falls upon the screen, which lies still nearer the base of the prism PO, from which it may be concluded that green light diverges more than red does from the original direction. If, finally, a violet glass be placed before the aperture, the violet ray is yet more refracted by its passage through the prism than the green was, for it strikes the screen at V. This experiment may be repeated with orange, yellow, blue, and other colored glass, and it will be found that the place of the image on the screen changes with every color, that the red light is the least and the violet the most refracted, and that the refrangibility of the different colors continues to increase from red through orange, yellow, green, and blue to violet. We are now able to tell beforehand what will happen if a ray of light composed of several colors be allowed to pass through a prism. The individual colors will be separated by the first refraction on entering the prism, and they will be much more widely dispersed as they leave it. The incident ray will be decomposed into as many colors as it consists of, and each color will follow its own particular path from the first entrance of the light into the prism. All the colored rays can be distinguished one from another upon the screen, as they group themselves according to the order already given. These simple experiments show that rays of light of different colors possess different degrees of refrangibility. Red light is not so much diverted from its straight course by refraction as violet is. The former, therefore, is less refrangible than the latter. This different behavior of red and violet light is, as is clearly shown by the undulatory theory, a necessary consequence of the unequal rapidity of the ether vibrations, which we have already recognized as the cause of the different colors. In red light, the number of vibrations striking the eye in a second is about 450 billion, in violet 800 billion, as deep and shrill musical sounds are propagated in the same medium with the same rapidity, so the different colors travel with the same velocity. JF, the latter, be taken at 42.0 German geographical miles, or 365 meters in a second. The length of each wave, that is to say, the distance between two succeeding condensations of ether of red light, will be 703 of a millimeter, and of violet light 395 of a millimeter. Different colored rays pass from one medium to another, as for instance from air to glass. The rays of shortest wavelength, namely the violet, are more easily influenced by the increased resistance which the glass offers to the passage of the light, and are consequently more refracted than those of greater wavelength, namely the blue, the green, the yellow, and the red rays. As each color has a length of wave peculiar to itself, so also has it a particular degree of refrangibility, and therefore a beam of light, which is composed of several colored rays, must be decomposed by refraction into its individual colors. Since each single ray is deflected or refracted in a different, the length of a wave of mean red light is about I/39th of an inch. That of a wave of mean violet light is about to 57,500 of an inch. the velocity of light being taken at 192 miles in a second. If we multiply this number by 39 we obtain the number of waves of red light in 192 miles. The product is 474, 439, 600. All these waves enter the eye in a second. In the same interval, 699,000 waves of violet light enter the eye. It must be remembered that the new determination of the value of the solar parallax by the observations of Mars, which agrees closely with the results of a redirection of the observations of the transit of Venus by Mr. Stone and Professor Newcomb, requires that the usually received velocity of light should be reduced by about 1/27th part, and may be taken at 185 miles per second. This velocity agrees nearly with the result obtained by Foucault from direct experiment, 6A degree. The mingled rays of light traveling along one common road, which appeared to the eye before refraction as a light of one color, are separated by its agency according to their several degrees of refrangibility, and afterwards proceeding in distinct paths, they are distinguished by the eye as separate colors. When a monochromatic ray, red for instance, passes through a prism, the amount of its dispersion does not depend merely on the rapidity of the ether vibrations or length of wave, but is also considerably influenced by the nature of the substance of which the prism is composed, and the angle formed by the two surfaces through which the light passes. There is, under similar circumstances, a greater amount of refraction in a prism of bisulfide of carbon than in one of glass. And the refractive power varies, as we have seen, with the kind of glass of which the prism is formed. For the purposes of spectrum analysis, prisms of dense flint glass with an angle of from 450 to 60 degrees are generally employed. But if the highly refractive properties of the substance, bisulfide of carbon, be required, it will be necessary to make use of a hollow prism, figure 31, formed of plain pieces of plate glass cemented together in which the liquid may be held. The question now presents itself as to how colorless, that is to say white light, is affected by its passage through a prism. It is well known that the light coming to us from the sun at noon in a clear sky is called pure white light. This light, however, is not always at our disposal, least of all in a public lecture room. We will therefore, before entering upon any experiments with artificial light, briefly review the results obtained by the prismalysis of the light of the sun. Chapter 18. The solar spectrum. If a ray of sunshine be allowed to pass through a small round hole in the window shutter of a darkened room, as is shown in figure 32, there will appear a round white spot of light, exactly in the direction of the ray, upon a screen placed opposite the opening, as will be seen indicated by the dotted lines in the figure. A very different appearance will be presented if the ray of light be made to fall upon a prism. The ray is at once deflected from its straight course upwards, that is to say, towards the base of the prism, and away from the sharp edge of the refracting surfaces, which, as represented in the drawing, are turned downwards. On its emergence from the prism, it no longer remains one single ray, as it entered the window shutter, but is separated into very many single-colored rays, which, as they continue to diverge, form upon the screen an elongated band of brilliant colors, instead of the former round white image of the sun. In this brilliant band, the individual colors blend gradually, one into the other, beginning at that end lying nearest the direction of the incident ray, the lowest end in the figure, with the least refrangible color, a dark and very beautiful red. This passes imperceptibly into orange, and an orange again into bright yellow. A pure green succeeds, which is shaded off into a brilliant blue, and this gives place to a rich, deep indigo. A delicate purple leads finally to a soft violet, by which the range of the visible rays is terminated. A faint picture of this magnificent solar image is given in Nover eye of the frontispiece. This is called the spectrum. In the above-mentioned colors of the solar spectrum, the eye discerns numberless gradations, which pass imperceptibly from one to another, and since language does not suffice to give separate names to each of these, we must content ourselves with designating only the 7 principal groups, which are known as the colors of the spectrum. This experiment furnishes conclusive evidence that white light is not simple and indivisible, but composed of innumerable colored rays, each of which possesses its own peculiar degree of refrangibility and therefore on refraction. Pursues a separate path. The prism analyzes white light. The result is the separation of all the colored rays of which it is composed, and the consequent formation of the colored image called the spectrum. The decomposition of sunlight by refraction is shown in various phenomena known to the ancients as well as ourselves, though they were not able, as we are, to trace them back to their true cause. The rainbow, with its pure but delicate colors, the sparkle of the cut jewel in its brilliant flashes, the play of color emitted by cut glass, and the prismatic facets of crystal lustres as the sun shines upon them. The glow of the clouds and high mountain peaks and the various colored light of the rising and setting sun, all these effects are occasioned by the decomposition of white light by its refraction on passing through glass in a prismatic form. Through drops of liquid or through vapor, the colors of the solar spectrum possess a purity and brilliancy to be met with nowhere else. They are all perfectly indivisible and cannot be further decomposed, as may be easily proved on attempting to analyze a colored ray by means of a second prism. If a small round hole be made in the screen in any portion of the image of the spectrum, the extreme red, for instance, figure 28, a red ray passes through it and appears upon the opposite wall as a round spot of red light, precisely in the same direction as the red ray has left the prism on the other side of the screen. If a second prism be interposed in the path of the ray that has passed through the screen, the ray will suffer a second refraction, and the image be thrown upon another place, higher up in the figure. On the wall, this new image, however, is simply red, like the incident ray, and by a careful adjustment of the prism shows no elongation, but appears perfectly round. Figure 33 shows this phenomenon with the central color of the spectrum. The ray falling on the prism S is decomposed into a colored spectrum at a B, and a small pencil of these colored rays will not be further decomposed by the second prism, but only diverted. The same thing occurs with all the colors of the spectrum without a single exception, which proves that the colors separated by the prism are not capable of further decomposition, and are therefore indivisible and homogeneous. The decomposition of white light into its colored rays is called dispersion. The dispersion of light is therefore to be clearly distinguished from refraction. The latter, as we have seen, varies in amount with every kind of color. It is greatest in the violet and smallest in the red rays. The amount of dispersion, to which we shall again refer in a closer analysis of the solar light, is determined by the length of the spectrum, or in other words, the distance between the extreme red and violet rays. As the nature of the refractive substance of a prism, for example, the kind of glass of which it is made, and its refracting angle each exert an influence upon the amount of refraction. In a similar manner, do the same conditions also affect the amount of dispersion or the length of the spectrum. It may, however, be remarked here that refraction and dispersion are not increased or diminished in equal proportion. The different colors are not present in the solar spectrum in the same proportions, and consequently they assume very unequal lengths in the spectrum. If the whole length of the solar spectrum be divided into IOA-UO equal parts, the proportions of the colors will be as follows: red 12, orange 7, yellow 13, green 17, blue 17, indigo 11, and violet 23. The unequal brilliancy of the different colors of the spectrum is apparent even to a superficial observer, and Fraunhofer found by careful measurements that if the greatest intensity of light which lies between yellow and green were expressed by 1,000, the light of orange would amount to 640, the middle red to 94, the outer red to only 32, the green to 480, blue to 170, between blue and violet to 31, and violet only to 6. Chapter 19. The spectra of the limelight and the electric light in the absence of sunlight, Drummond's limelight, Part 50, p28, may be analyzed by a prism in the following manner. Let the lantern L, figure 34, which has been already described, be placed on a pedestal F, and the limelight lamp introduced in front of which is inserted a diaphragm D. provided with a contrivance for allowing the light to pass out projection of the spectrum of the limelight of the lantern through a narrow slit. Opposite the lantern, at a distance of 12 or 15 feet, place two paper screens SX, 8 feet square, inclined to each other at a wide angle. Let the lime cylinders then be raised to incandescence by means of the oxyhydrogen gas, the room be completely darkened, and the table TT so turned that the tube D of the lantern be perpendicular to one of the screens. S. Then let a double convex lens of 4 inches diameter and about 12 inches focus be placed between the slit D and the screen S, at a distance of about 1-2 inches from the slit, so as to throw the rays issuing from the slit upon the screen as in the form of a sharp and magnified image. D% of the slit D close behind this lens, a flint glass prism P of 60 degrees, 2 inches high and 2 inches broad, must be placed in the direct path of the rays, when there will instantly appear on the second screen SX a magnificent spectrum about 3 feet long and 16 inches wide, exhibiting the whole range of colors as shown in number 1 frontispiece. Owing to the distance of the screen, the spectrum is displaced very considerably from the spot done, where the rays fell when unbroken by the prism. The red lies nearest to that straight line. The violet is the furthest removed from it. The former is therefore the least refracted, and the latter the most so. The individual colors succeed each other without the slightest interruption. Their limits are not sharply defined, they rather blend gradually one into the other, and thus form an unbroken or continuous spectrum. As the lantern L may obstruct the view of the screen S to some of the spectators, the top of it to throw the spectrum upon the screen S. Instead of turning the table, the colored rays as they leave the prism P might be received upon a flat mirror and thrown by reflection on to the second screen. But the spectrum would lose in intensity by this reflection, inasmuch as a reflected image is always fainter than the object. The table might even be turned further round still, and the prism be directed towards the spectators, when the rays could be thrown by means of the mirror to any part of the room in order to obtain a pure spectrum. The width of the slit must not exceed 1/16 of an inch. Were it widened, the spectrum would greatly increase in splendor and brilliancy. But it would be perceived on a careful examination that the colors in the middle were neither so pure nor so clearly separated one from another as before, and that in the center the light had become almost white. Instead of the spectrum being received upon the side of the paper screen fronting the audience, and reflected thence so as to be visible to the spectators, a transparent screen may be advantageously used, behind which is placed the lamp. By this means the screen is visible without interruption from the lantern or experimenter, and every arrangement much simplified. A very suitable material for such a screen is thin tracing paper, which may be had about 2 yards wide of any length, or fine white muslin, sewn together in breadths, and made transparent by damping before each experiment. By fastening the screen to a roller, it may be easily moved out of the way when the attention of the audience is to be directed to the lantern or prism. The spectrum of the electric light may be thrown upon the screen in the same manner as that described for Drummond's limelight. The electric lamp, as described before Part 1, P46, is substituted for the oxyhydrogen gas lamp in the lantern, connected by copper wires with an electric battery of 50 Bunsen's of gross large elements. As soon as the current passes through the carbon poles, the electric arc is formed and the white light pouring through the slit produces by means of the lens, figure 34, a well-defined image of the slit upon the screen. If the flint glass prism P be again placed in the path of the rays behind the lens, the wonderfully beautiful spectrum of the electric light appears thrown sideways on the screen, in place of the white image of the slit. By slightly increasing the width of the slit, the spectrum gains considerably in brilliancy, and the colors are so clear and brilliant that the spectrum would still be bright, were the light spread over a surface even 2 or 3 times its large. It will be desirable to enter somewhat further into this experiment, because practically it is often necessary to produce a great dispersion of light, and thus obtain a very extended spectrum, in order that its various details may be examined with sufficient minuteness. For this purpose, the flint glass prism is replaced by one of bisulfide of carbon, figure 35, which produces a spectrum of the same breadth, but of almost double the length of the former one. Immediately in front of this prism, P figure 36, is placed the prism of flint glass PX, so arranged as to throw the rays upon the second prism P in a manner similar to that in which it had itself received the light from the lens, the prisms forming an angle of about 0 degrees with each other. In this way, the spectrum is extended to the length of about 8 feet, and diverted more than 90 degrees to one side. The colors, however, though still very visible and easily distinguishable one from another, have yet lost much of their original brilliancy. A combination of 2 prisms of bisulfide of carbon would extend the spectrum still further, but the brightness would be diminished in the same proportion. In many scientific investigations, not merely 2, but sometimes 4, and even as many as 8 prisms, with angles varying from 450 to 60 degrees are employed, according to the strength of the light. Chapter 20. Recombination of the colors of the spectrum. If white light be actually composed of the colors contained in the spectrum, then the recombination of the same colors must reproduce white light. The simplest method of collecting several rays of light into one point is by a convex lens or a burning glass. If the sun's rays fall perpendicularly on such a glass, the refraction they suffer in their passage through it causes them to converge to one point, the focus. To accomplish by this means the recombination of the colored rays of the spectrum of the electric light, a cylindrical lens must be interposed between the prism and the screen on which the spectrum of the small line of light issuing from the slit is extended to a length of some 6 feet. This lens is a convex lens of peculiar form, which possesses the property of recombining in a point all the rays issuing from each point of the line of light passing through the slit after dispersion by the prism, and therefore of 98. Spectrum analysis, representing the whole of the rays of that short line of light, again as a small line. When therefore this lens, figure 37, is placed at a proper distance behind the prism, the colors of the spectrum disappear from the screen, and are replaced by a short line of light some few inches in breadth, white in the middle, and slightly colored at the edges, as this color indicates that the large screen is not in the focus of the lens. A smaller one is placed nearer to it, upon which the image appears as a purely white, very narrow line of light, in which all the colored rays issuing from the prism have been recombined, and the white light reproduced out of which they originated. Chapter 21. Influence of the width of slit on the purity of the spectrum. The spectrum of white light is the richer and purer in color, the narrower the slit is made. The truth of this statement will be easily proved by the following considerations. The ray of white light at figure 38 falling on the prism P from the extreme end of the slit AB produces a complete spectrum RV, which contains between R and V, or red and violet, all the colors of the spectrum. In the same manner, the ray B9 proceeding from the other end of the slit B exhibits also a complete spectrum, or Z, with all its colors. Between these two ends A and B are many other points, emitting light, which increase in number according to the width of the slit. Out of these, let us select for consideration the point C, the ray from which CCX forms another spectrum, R2V2, between the two outer spectra, RV and the RZ-VEX, which it is evident falls partly over the two other spectra between the 2 points, R2, while in the portions VV. R2, there are parts of the pure spectra formed by the rays AX and BBX1. There are to be found in the portions V2R2 of the compound spectra VRX, the superposed colors due to the whole slit, and their colors being no longer influence of the width of slit on the purity of the spectrum, separately distinguishable, produce on the eye the impression of a confusion of tints, the spectrum of white light, therefore, emitted through a wide slit, is only pure or of one color at the extreme ends, in the red and in the violet rays. In the middle, a mingled light prevails composed of all possible groups of rays, and which, therefore, might be decomposed afresh into its constituent parts by a second prism. On this account, it is important to pay the greatest attention to the width of the slit in all practical applications of spectrum analysis. As a rule, it should never be wider than the intensity of the light to be examined absolutely requires. The contrivances for the regulation of the width of slit are mostly very simple. The purity of the spectrum, however, is not merely affected by the width of the slit, but also by the smoothness of its edges. Since a few particles of dust, even on the edges of the slit, are sufficient to produce a number of dark streaks along the whole length of the spectrum, which greatly impede observation. Chapter 22. The continuous spectra of solid and liquid bodies when the carbon points used for the production of the electric light are carefully prepared, and completely free from all extraneous substances, the light is purely white, being emitted exclusively by solid particles of carbon in a state of incandescence. The spectrum of this light is, therefore, continuous, like that of incandescent lime. It is unbroken by gaps in the colors or by sudden transitions from one color to another, and is uninterrupted by either dark or bright bands. All other incandescent bodies, whether solid or liquid, give a similar spectrum, the colors being distributed in the order represented in the frontispiece, no if instead of the limelight, the magnesium light, section 4. The light of an incandescent platinum wire, or the flame of coal gas in which light is produced by incandescent particles of carbon, be analyzed by the prism, continuous spectra are always obtained, but with this difference, that the various groups of color are not always distributed in exactly the same proportion in each individual spectrum. And therefore, according to the kind of light employed, sometimes red, sometimes yellow, and sometimes violet predominates. Only in very rare instances do incandescent solid substances emit with any preeminent strength an isolated set of colored rays, as is the case with the very rare substance erbiata. It may therefore be considered that, as a rule, where there is a continuous spectrum without gaps, and containing every shade of color, the light is derived from an incandescent solid or liquid body. Chapter 23. The spectra of vapors and gases, very different spectra, are obtained when the source of light is not an incandescent solid or liquid body, but a vapor or a gas in a glowing state. Instead of a continuous succession of colors, the spectrum then exhibits a series of distinct bright-colored bands, separated one from another by dark spaces, as gases and vapors in a luminous state undo solid bodies. The exhibition of their spectra on a screen before a large audience is restricted to those substances which give by their volatilization in the hydrogen flame or electric lamp a luminous vapor of sufficient brilliancy to form a spectrum clearly visible at some distance, notwithstanding the distance of the screen from the slit and the loss of light by its passage through the lens and the thick prism. For this purpose, the vapors of copper, zinc, brass, silver, cadmium, sodium, thallium, etc., are particularly suited, although the oxyhydrogen flame is adapted for these experiments, inasmuch as it emits scarcely any light. Yet the electric lamp is much more suited to the purpose because it generates a far greater degree of heat, therefore volatilizes more rapidly the above-named substances, and brings them to a higher state of luminosity. In order to exhibit these spectra, the apparatus described in section 19, and drawn in figure 35, is employed. The lower carbon pole of the lamp is replaced by a half-inch cylinder, figure 39 of pure carbon, the upper end of which is slightly hollowed, and it is fixed precisely in the focus of the lantern lens. In the hollowed end of the carbon is laid a piece of zinc the size of a pea, and the upper pole 0 is brought down until it comes in contact with it, when the electric current instantly passes through the carbon, and the intense heat produced quickly volatilizes the zinc. If the upper carbon pole 0 be now withdrawn to form an arc of flame, and it be raised somewhat higher than was the case during the former experiment, so that the carbon may glow less, and the light be almost exclusively that of the luminous zinc vapor, there will be seen on the screen not the spectrum of incandescent zinc, but that of the vapor of zinc which constitutes the arc of light seen between the carbon poles. It will be at once perceived that this spectrum differs essentially from the continuous spectrum already described. It consists, in fact, of only one red band and three very beautiful bright blue bands. The faintly colored band, which forms as it were a background to these bright stripes, is due to the glowing carbon, some of the white light of which reaches the screen on opening the lantern. The zinc vapor is seen rising in the form of a blue cloud. The carbon, which has become contaminated by the zinc, may be replaced by a fresh cylinder, in the cavity of which is laid a piece of copper, and electric current again allowed to pass. A spectrum of quite another kind appears on the screen, consisting of three bright bands which were not present in the zinc spectrum, while the red and blue stripes which characterize the latter have disappeared. Instead of the carbon cylinders, thick rods or wires of zinc, copper, etc. may be employed. The spectra are then more decided and brilliant, but are very evanescent, lasting only for a moment, because the metals burn away the instant there is contact, and the electric current is then interrupted. The inquiry now suggests itself whether the ether waves which produce the colors in the spectra of zinc and copper would suffer any reciprocal interference were the same experiment to be made with brass, a substance composed of zinc and copper, or whether each material in this alloy would emit independently its own peculiar colors, so that the spectrum of the compound substance would consist of the superposed spectra of the component metals. In order to obtain an answer to this question, it is only necessary to lay a piece of brass in the cavity of a fresh cylinder of carbon and apply the electric current. A magnificent spectrum meets the eye, in which can be recognized at once not only the red line and three bright blue bands of the zinc, but also the three green bands of the copper. The rays from the volatilized constituents of an alloy do not therefore interfere with each other. Each vapor, even when in combination with other vapors, emits its own system of colored rays, which, in passing through a prism separate from one another in consequence of their unequal refrangibility, and appear as a system of disunited columnar bands, form again interrupted or discontinuous spectrum. To avoid the tedious and troublesome operation of changing the lower carbon cylinder, Ruhmkorff of Paris has fitted to the lamp the contrivance shown in Figure 40, which will be easily understood by comparing it with Dubosc regulator, Figure 17. The clockwork is dispensed with, as during the few moments necessary for the volatilization of a small piece of metal. The arc of light between the upper carbon 0 and the lower carbon U is very slightly removed from the focal point of the lens, and by turning the screw A, the whole of the upper portion of the lamp may be raised and lowered at will, and the arc of light thus kept continuously in the focus of the lantern lens. 6 carbon cylinders, instead of one only as in Figure 39, are here employed, arranged in a circle upon a small plate, which by means of the carrier G is made to revolve, so that by simply turning the plate round, any one of them may be brought exactly under the carbon cylinder 0. This cylinder can be raised or lowered by means of the screw B, so that if before the experiment 6 different metals be placed upon the carbon cylinders, by merely turning the plate, and if necessary by turning the screws A and B, each metal may be volatilized in the arc of flames, and the spectrum of its glowing vapor obtained. The characteristic feature of spectra obtained from luminous vapors or gases is the want of continuity in the succession of the colors. Such a spectrum is composed of distinct colored bands, irregularly arranged with dark spaces between them, and is therefore called a discontinuous spectrum, a spectrum of bright lines, or a gas spectrum. The spectra of the vapors of sodium, lithium, caesium, and rubidium are represented in OS 2, 3, 4, and 5 of the frontispiece, while those of oxygen, hydrogen, and nitrogen gas are shown in 8. They exhibit at a glance the great difference which exists between the continuous spectrum, number 1, of incandescent solid and liquid bodies and the discontinuous spectra of gases. The vapor of sodium, number 2, under ordinary circumstances, and when not exposed to an extremely high temperature, gives a spectrum consisting only of one bright orange line, which, however, will be seen to be doubled by the use of sufficient dispersive power. The spectrum of luminous lithium vapor, number 3, consists only of 2 colored lines, or bands, one a brilliant red, and the other a faint yellow line. Much more complete is the spectrum of cesium. At a sufficiently high temperature, the luminous vapor exhibits from 10 to 13 clearly distinguishable lines, 3 of which are visible even at a low temperature. Of these 3 lines, 2 are blue and 1 yellow. The remaining yellow and green lines do not appear as individual bands until the temperature is sufficiently high to cause the glowing vapor to emit light of the requisite intensity. As before this heat is attained, they run one into the other so as to give a faint show of color in the manner of a continuous spectrum. It is desirable to supplement the observations previously made with the spectrum of brass by the 2 following experiments. Let a grain of sodium be laid upon the lower cylinder and the electric current allowed to pass through it to the upper carbon pole. The sodium is quickly volatilized in the arc of flame, and the spectrum already described, frontispiece number 2, appears on the screen, a single stripe of bright yellow. Let the current now be interrupted and 2 fresh carbon cylinders introduced, on the lowest of which is laid a grain of common salt, and the current reestablished. Common salt is a compound of chlorine and sodium, and it might be expected from the experiment with brass, the spectrum of which was made up of the combined spectra of its 2 components, zinc and copper, that the spectrum of salt would similarly consist of the spectrum of chlorine gas and that of the vapor of sodium. This, however, is evidently not the case, for only the same yellow bands appear which were given by the metallic sodium, occupying precisely their former position on the screen, while of chlorine, which, when isolated, gives a very characteristic spectrum, there is nothing whatever to be seen. The same thing occurs with other metals that combine with chlorine, as may be seen if a mixture of the chlorides of lithium, barium, magnesium, and thallium be placed on the upper surface of a somewhat wider cylinder of carbon. As the current passes from pole to pole, these substances are volatilized in the arc of flame, and on contracting the slit a little, a number of closely arranged colored bands are seen, some of which, as for instance, the red of the lithium and the bright green of the thallium, stand out with a special distinctness. If a second prism, figure 32, be interposed, so as to lengthen the spectrum to about 6 feet, the individual stripes appear less bright, but more sharply divided one from another. By widening the slit, the stripes increase a little in brilliancy. Those who are familiar with the simple spectra of lithium, barium, magnesium, and thallium will not find it difficult to recognize each separate substance in the compound spectrum produced by the mixture of these substances. Here again, however, the spectrum of chlorine is not present, at least it is not visible. If the various compounds of such metals as sodium, calcium, etc., for example, chloride of calcium, iodide of calcium, nitrate of lime, etc., be in the same way subjected to spectrum analysis, the spectrum of the metal is alone obtained, and never that of the other constituents. The spectra of the vapors of metals assert themselves with such marked prominence that the spectrum of any non-metallic substance with which they are in combination either does not appear at all, or else is so overpowered by the clear and brilliant lines of the spectrum of the metal as not to be perceived. Chapter 24. Spectrum apparatus, the thought is perhaps rising in the minds of many who have accompanied us thus far, that the production of the spectrum of a substance for the purposes of analytical examination is encumbered with great difficulties and many troublesome details involving too much labor to be available for the use of the chemist and the physicist. This is, however, not the case. If in our mode of illustration, a powerful galvanic battery and the electric lamp with its revolving table and large screen have been employed, it has been only to show how by the extraordinary heat and light of the voltaic arc, the simple phenomena on which spectrum analysis is based can be made visible to many hundred spectators at once in a large lecture room, when, however, the light from the heated vapors need not be greater than is required for a single observer. The whole electric apparatus may be dispensed with, and the simple Bunsen burner, figure 2, substituted. Indeed, in many cases, a powerful spirit flame is sufficient to exhibit the gas spectrum of a substance. The slit and the prism may then be reduced to small dimensions in place of the large screen of paper that reflected the light. The small sensitive screen of nerves, the retina of the human eye, becomes the surface on which the spectrum is received, and the whole cumbrous contrivance occupying so much space is replaced by a small spectrum apparatus as trustworthy as it is easy to manipulate. Every spectrum apparatus or spectroscope, exclusive of the source of light, is composed of an adjustable slit, a contrivance, collimating lens for rendering the rays parallel that have passed through the slit, and a prism, in order that the instrument may be used at any hour of the day. All light except that under examination must be excluded from the prism, and therefore the slit, lenses, and prism are enclosed in a tube. Or if the prism be too large, the latter is fitted. Phi TFTT separate, X cover B further, PFI, as the spectrum on emerging from the prism is but little longer than the width of the slit, and only becomes of some length as the distance from the prism increases. A magnifying glass is introduced, in order that the eye, though at but a small distance from the prism, may see the spectrum of a sufficiently large size, and the spectrum therefore is not observed with the naked eye, but through the medium of a telescope of moderate power. It has been already mentioned that the colored rays composing the spectrum form an angle with the incident rays as they enter the prism. It is therefore necessary, in observing the spectrum, that the tube of the telescope directed to the outer surface of the prism should be placed in a different direction to the tube carrying the slit and the lens. A spectroscope arranged in this way is shown in Figure 41. The light emitted from L after passing through the slit 5 in the collimating lens reaches the prism P in parallel rays. It is there diverted as well as decomposed, whereby the spectrum S is seen through the telescope F in a direction very different from that of the tube SL. This arrangement has the inconvenience that in conducting a research with spectrum analysis, the eye cannot be directed straight at the light, and therefore the spectrum can only be found, after some search for it, by moving the instrument backwards and forwards. A spectroscope would therefore be obviously more convenient if the slit, lens, prism, and telescope were all in a straight line, so that it would be only necessary, in observing with it, to direct the instrument like a telescope to the light to be examined, in order to observe the spectrum on reconsidering the action of a prism S. Figure 42, it will be easy to understand that the various colored rays receive a different amount of deviation according to the position of the prism. As regards the incident ray, it can be readily shown by calculation that of all the emergent rays, that one suffers the least deviation, which, as in ER Figure 28, makes the same angle with the prism as the incident ray aside makes with the surface upon which it falls. When a prism is so placed that the colored ray in the spectrum suffering least deviation is the one which possesses the mean wavelength, about 549 of a millimeter icicle P 82, which is situated between the yellow and the green, the prism is then said to be in the position of minimum deviation. Strictly speaking, however, the prism has a special position of minimum deviation for each colored ray. The angle formed by this central emergent ray with the incident ray is the measure of the refractive or deviating power of the prism, while the length of the spectrum is the measure of its decomposing or dispersive power. If two prisms, A and B, Figure 45, of similar composition and equal refracting angle, be placed in reversed positions, the incident ray E of white light will be refracted by the first prism A and decomposed into its colored rays, the second prism B, however, which refracts in an opposite direction, destroys the first divergence and reunites the incident colored rays into a single emergent ray Fe. If the ray F be received upon a screen, there will appear a white image, tinged at the upper edge with red, and at the lower with violet light, because at the extreme edges of the image the colors are not superposed. In this case, the second prism B has neutralized both the refraction and the dispersion of the first prism, and the action of this system of prisms is very nearly the same as that of a thick piece of glass with parallel sides. Now, if the dispersive power of a prism vary in the same proportion as its power of refraction, then whatever the kind of glass employed for the prisms placed, as in Figure 43, and whatever might be their refracting angles. When they were so placed as to neutralize refraction, their power of dispersion or capability of forming a spectrum would be likewise destroyed. In other words, the formation of a spectrum would always be connected with the deviation of light from its straight course, and it would not be possible by means of a system of prisms to receive the spectrum of a luminous object, for example. A phi or a star when viewed in a straight line. In reality, however, this is not the case. The dispersive power of various kinds of prisms is not in equal proportion to the refractive power. A flint glass prism, for instance, gives with an equal amount of refraction of the central rays a spectrum of much greater length than can be obtained from one of crown glass. It is therefore possible so to combine and place in reverse positions, as in figure 43. Two prisms of different refracting angles, one of flint and the other of crown glass, that the refraction of the incident rays shall be entirely counteracted, while the greater dispersive power of the flint glass shall only be partially destroyed by the crown glass, and consequently a spectrum formed by the remaining rays. If a bright object be looked at through such a system of prisms, in a rectilinear direction, its spectrum will be seen in the line of sight. The colors will, of course, not be so widely dispersed as would be the case were the object looked at in an oblique direction to the flint glass prism below. Compound prisms of this kind, or more especially systems of prisms which show a spectrum when held in a straight line between the source of light and the observer's eye, are called direct vision prisms. Such an arrangement of the spectroscope was approximately accomplished by Amici and II 160 by a judicious combination of two crown glass prisms, with a third prism of flint glass of 90 degrees interposed. By this construction, the rays of mean refrangibility suffer no divergence, so that a luminous object may be viewed in a rectilinear direction, and a spectrum be obtained, since the dispersion produced by the flint glass prism in one direction is greater than that produced by the two crown glass prisms in the opposite direction. Prism contrived by Professor A. Herschel for the observation of meteors. The ray of light E undergoes two total reflections from the inner surfaces of the prism before it emerges from it in the form of the spectrum F, in a direction parallel to E. The construction, however, of such a prism is surrounded with difficulties, since the action of each surface is required in the course of the rays, and it is exceedingly difficult to attain sufficient accuracy in the angles A and C. Browning, the optician, has overcome these difficulties by combining two such prisms. In the Herschel-Browning system of prisms, figure 46, the ray F, which emerges from the first prism A in a direction parallel to the incident ray E, is brought back again by the second prism B to the direction of the incident ray, so that the central emergent colored rays G form an exact prolongation of the incident ray E Janssen of Paris, adopting Amici's construction, has produced, with the help of the excellent optician Hoffmann, a direct vision spectroscope, which from the facility with which it can be used, its moderate price, and the great purity and length of the spectrum it produces, has become an instrument indispensable to the chemist, the physicist, and the astronomer. Janssen's direct vision spectroscope, figure 47, has the appearance of an ordinary telescope, and can either be held in the hand while in use or placed, when steadiness is required, upon a small revolving stand. The several parts are sketched in the drawing above the instrument in the same positions that they occupy within the tube. In front, at the end which is directed towards the source of light, is the slit S formed of two steel edges, which can be easily widened or contracted by means of the screw V and an opposing spring. At L, the collimating lens is inserted by which the rays diverging from the slits are rendered parallel, and thrown upon the 5 prisms P of these, which are drawn in detail in figure 48. The first, third, and fifth are of crown glass, while the second and fourth are of flint glass, and they form so perfect a system from the accurate adjustment of the angles of the prisms that the emergent central colored rays F have precisely the same direction as the incident rays E, and therefore pass in a straight line through the tube LGMO, in which the compound prisms occupy the space between L and G. The lenses A and a behind G form the object glass, 0, and in the small sliding tubo, the eyepiece of the telescope through which the spectrum is observed. Browning has manufactured another direct vision spectroscope with 7 prisms, which commends itself by the excellence of its performance, the facility of its use, the smallness of its dimensions, the purity of color, and its low price. A sketch out it is shown in figure 49. The slit is simply regulated by turning round a ring at the end of the tube, and the spectrum is observed direct without a telescope. The length of this admirable little instrument is only about 3 key inches, and is therefore very deservedly called the miniature or pocket spectroscope. Chapter 25, Mode of Measuring the Distances Between the Lines of the Spectrum, the Lines of the Spectrum. We have already seen that the spectra of luminous vapors consist of 1 or more colored bands, and that it is not difficult from the distribution of these lines in the spectrum to recognize the substance by which such a spectrum is produced. Experience teaches that the single lines forming the spectrum of any given substance never fall in the same places as those of another substance, the spectrum of which may be shown at the same time. But owing to the immense number of these lines in lawn, for example, according to Angstrom and Thallen, from 460 to 500, they approach each other so closely, especially when the spectrum is not much spread out, that it is necessary to have a contrivance in a spectrum apparatus for determining the relative places of the single lines, and for measuring with precision the amount of separation one from the other. The number and relative position of these lines is indeed always the same in a given apparatus for any one substance as long as the temperature remains the same. However, variously the substance may be combined with other bodies. But by the use of prisms of greater dispersive power, or of a larger number of prisms, or by increasing the refracting angle of the prisms of the size of the telescope, these positions are altered, so that the actual amount of separation between any 2 lines in the spectrum of any substance varies according to the arrangement of the spectrum apparatus. This alteration extends even to the relative distances of the various lines in one and the same spectrum, when the whole spectrum of a substance is by any means extended 2 or 3 times its original length. The single lines do not all separate one from the other in the same proportion. On this account, the same substance does not yield, in different spectroscopes, spectra identical throughout. The estimation of this difference is therefore one out of many reasons why it is requisite to have some means of measuring the distance of the individual lines one from the other, and of determining their relative positions. The simplest and most usual arrangement of this kind is illustrated in figure 50C, is again, as in figure 41, the tube enclosing the slit S and the collimating lens. P is the prism and F the telescope. To this is added a third tube S, which is with the others fastened to a stand and lies with them on a horizontal plane. At the extreme end of this tube is fixed a reduced millimeter scale M, photographed on glass of about 1/15th, the original dimensions which is provided, according to the size of the apparatus, with a larger or smaller number of fine divisions. The 2BS is inclined in such a manner towards the surface of the prism on which the telescope is directed, that its axis and that of the telescope form the same angle with the surface of the prism. Consequently, the scale M is, in obedience to the laws of light reflected by the outer polished surface of the prism, in the direction of the axis of the telescope, and its magnified image is seen in the telescope F at the same time as the spectrum to be observed. The scale M is bordered on both sides with tinfoil and illuminated from without by a candle, K, or a small gas flame, so that its image is seen with complete distinctness the whole length of the spectrum. And as its black divisions are parallel to the colored bands, the amount of separation between any 2 of these bands may easily be read off in parts of the graduated scale. In the direct vision spectroscope, figure 47, a small glass scale placed in the eyepiece of the telescope is seen projected upon the spectrum, and by means of this scale, the position of the lines of the spectrum may be measured. A contrivance preferable to any fixed scale is that by which a well-defined mark of some kind, as for instance a fine wire or cross wires or 2 points facing each other, or a line of light, etc., is made to move along the spectrum in the inside of the tube, and the amount of motion accurately measured externally by means of a micrometrical arrangement. This micrometer consists principally of a sliding plate A, figure 51, provided with a slit or fine metal wire, an underplate B to B on which the first plate travels, and an exceedingly fine screw D, the head C of which is engraved after the manner of a divided circle. This screw, which is held firmly at G, works into the screw plate D attached to the slide A, in which the mark is fixed, which it moves to the right or left upon the lower plate. In order to measure accurately the amount of motion, the value of a screw thread must be ascertained, and the screw head C be so divided as to mark off parts of an entire revolution. If, for instance, one revolution of the screw is 0.5 millimeter in value, and the circumference of the screw head C be divided into 50 equal parts, the displacement of the mark by a complete revolution of the screw amounts to 0.5 millimeter. Consequently, a displacement amounting to one division of the screw head is equivalent to only of 0.5 millimeter, or 2 of a millimeter. The screw head C works close to the sharp edge N by which parts of a revolution can be read off, while the number of complete revolutions are registered by means of the indicator on the slide, being brought over the divisions marked on the underplate BB. The micrometer is so connected with the eyepiece of the telescope in the spectrum apparatus that the slide A with its indicator is in the inside of the tube, while the screw head C and the divisions numbering the complete revolutions are visible on the outside. The micrometer mark is seen projected upon the spectrum in the head of the telescope and may be brought over any part of it by turning the screw. In this way, it is possible, by moving the indicator from one line of the spectrum to another, to determine accurately the distance between any two lines by the divisions marked on the screw head. Another mode of determining the relative positions of the lines of the spectrum consists of a telescope provided with cross wires, or a line of light which can be moved on an axis from one line to another, and the angle measured which is described by this motion. In this case, the distance between the lines is denoted by the angle. It will be seen at once that for any given instrument, it is easy to calculate the real distance between the lines from the angles measured. Professor Winlock contrived a form of instrument in which the positions of the observing telescope, when directed to different parts of the spectrum, are recorded by marks upon a plate of silvered copper. Description of the instrument taken by him to Oran. The short duration of the totality of the solar eclipse of December last led me to seek some method by which the positions of lines observed in the spectrum of the corona might be instantly registered without removing the eye from the instrument, so as to avoid the loss of time and fatigue to the eye of reading a micrometer head, or the distraction of the attention and other inconveniences of an illuminated scale. After consultation with the optician Mr. Grubb, it seemed that this object could be satisfactorily accomplished by fixing in the eyepiece of the spectroscope a pointer which could be moved along the spectrum by a quick motion screw, together with some arrangement by which the position of this pointer, when brought into coincidence with a line, could be instantly registered. I was furnished by Mr. Grubb with an instrument fulfilling these conditions, and also with a similar instrument with some modifications by Mr. Ladd, in time for the observation of the eclipse, unfortunately at my station at Oran. Heavy clouds at the time of totality prevented the use of these instruments on the corona, but they were found so convenient for the rapid registration of spectra that it appears probable that similar instruments might be of service for other spectrum observations. In these instruments, the small telescope of the spectroscope is fixed, and at its focus is a pointer which can be brought rapidly upon any part of the spectrum by a screw head outside the telescope. The spectrum and pointer are viewed by a positive eyepiece which slides in front of the telescope so that the part of the spectrum under observation can always be brought to the feet. Chapter 26. The compound spectroscope. The reader is now in a position to understand the use of the various parts of a complete spectrum apparatus, figure 52, especially the three tubes directed to the prism at different angles, as in that constructed middle of the field of view. The arm carrying the pointer is connected by a lever with a second arm, to the end of which are attached two needles, so that these move over about 2 inches when the pointer is made to traverse the spectrum from the red to the violet. Under the extremity of the arm, fitted with the needles, is a frame containing a card, firmly held in it by 2 pins which pierce the card. This frame containing the card can be moved forward so as to bring in succession 5 different portions of the card under the points of the needles. On each of these portions of the card, a spectrum can be registered. The mode of using the instrument is obvious. By means of the screw head at the side of the telescope, the pointer can be brought into coincidence with a line. A finger of the other hand is then pressed upon one of the needles at the end of the arm which traverses the card, and the position of the line is instantly recorded by a minute prick on the card. A bright line is distinguished from a dark line by pressing the finger on both needles, by which a second prick is made immediately below the other. In all cases, the position of the line is registered by the same needle, the second needle being used to denote that the line recorded is a bright one. It was found that from 10 to 12 Fraunhofer lines could be registered in about 12 seconds, and that when the same lines were recorded 5 times in succession on the same card, no sensible difference of position could be detected between the pricks registering the same line in the several spectra. It is obvious that by registering the spectra of different substances on the card, a ready method is obtained of comparing the relative positions of the lines of their spectra. Each spectroscope was furnished with a compound prism made by Mr. Grubb, which gave a dispersion equal to about 2 prisms of dense glass, with a refracting angle of 60 degrees by Kirchhoff and Bunsen. The eye of the observer is placed in the axis of the telescope, directed to that surface of the prism, from which the light emerges in the form of the spectrum. The opposite surface of the prism receives through the slit and collimating lens the light emitted from the object to be examined. At the side of the observer is the tube carrying the illuminated scale, or the micrometer screw, so that the mark coinciding with any division of the scale may be placed on any line of the spectrum. In most spectrum investigations, the dispersion obtained by a flint glass prism of 450 or 60 degrees is sufficient to show the chief characteristics of the spectrum. Should this not be the case, however, the dispersion must be increased by the use of several prisms, a method already explained in reference to Figure 36. Kirchhoff employed in his investigations on the solar spectrum an excellent apparatus constructed by Steinheil of Munich, in which, instead of only one prism of flint glass, 4 such prisms were employed, and a telescope possessing a magnifying power of 40, each of the 4 prisms, Figure 53, 3 of which had a refracting angle of 450, and the fourth of 60 degrees was cemented on to a small brass tripod, and could thus be easily placed in the right position on a horizontal iron table, the tube carried at the end directed towards the sun, the slit, and the prism for comparison, which will be described hereafter, Figure 57. The telescope B, which received the widely diverging rays of the solar spectrum from the last prism, could be moved by means of a micrometer screw R on a divided circle, so as to determine the distance between any of the dark lines in angular measure. This amount of elongation of the spectrum has been, however, surpassed. Thalen employed 6 flint glass prisms, each having an angle of 60 degrees. Gassio went as far as 8, Mers even to 11 prisms of glass, while Cook made use of as many as 9 prisms of bisulfide of carbon. Figure shows one of the largest spectroscopes yet made, constructed by Browning, and used by Gassio at the Kew Observatory for the investigation and delineation of the solar spectrum. The tube carries the collimating lens, the slit, and the prism for comparison. The 9 prisms rest, as in Kirchhoff's instrument, on small plates provided with leveling screws upon an iron table. B is a telescope of high magnifying power. C, a tube fitted with a scale. Compare Figure 50. The slender ray of light entering the first prism from the slit and collimator tube passes through the range of 9 prisms as shown in Figure 55, and finally emerges from the last prism and enters the telescope B in the form of a widely dispersed ray or an elongated spectrum. The power of the spectrum apparatus, however, does not depend alone upon the number of the prisms, but also quite as much upon the dispersive power of each prism. In the workshops of the celebrated optician Merz of Munich, prisms have been manufactured lately of the densest Lie glass, having a specific gravity of 475. One of these prisms with a refracting angle of 60 degrees is quite as efficient as the 4 prisms together employed in Kirchhoff's instrument, figure 53. Chapter 27. Browning's automatic spectroscope. Spectroscopes, consisting of several prisms, are usually adjusted by finding the minimum of deviation for the brightest rays. Those, for instance, situated between the yellow and the green. For each prism, which is then permanently secured to its supporting plate, there are, however, 2 objections to this arrangement. In the first place, only those rays for which the prisms are specially adjusted are seen under the most favorable circumstances, because they only pass through each prism in a line parallel to the base. In the second place, since the last prism is immovable, while the telescope travels in an arc from one end of the spectrum to the other, the object glass of the telescope receives the full light only when it is directed to the central part of the spectrum. And, on the contrary, only a part of the light falls on the object glass when the telescope is directed to one end of the spectrum, either the red or the violet. Now, it is easy to see that in observing the ends of the spectrum, it is most important that the object glass should receive the whole of the light, since it is just these terminal colors that have these brilliance. This can only be accomplished by the prisms being made adjustable for the minimum of deviation for those rays which are under examination. Bunsen and Kirchhoff, therefore, in their investigations of the solar spectrum, attached the prisms of their compound spectroscope, figure 53, to the ground plate by means of movable supports, and altered the position of the prisms for every color of the spectrum. It is needless to remark that such an arrangement involved much trouble and inconvenience. This inconvenience is removed in Browning's automatic spectroscope by so connecting the prisms with each other and the telescope, that on placing the instrument on any particular color, the prisms, without any interference from the observer, will be simultaneously and automatically adjusted for the minimum of deviation for that color. Parts of the automatic spectroscope. Of the prisms numbered from 1 to 6, the first only is fastened to the ground plate PP. The others are connected to each other by hinges at the corners of the triangular metal holders forming the base. A metal rod A, provided with a slit, is attached to the middle of this base, by means of which each prism can move round a central pin common to the whole set. The prisms are arranged in a circle round this pin, which again is fastened to a swallow-tailed movable bar, 5 to 5, about 2 inches in length, situated under the plate PP, if therefore the central pin be moved. The whole system of prisms moves with it, and the amount of motion communicated to each prism varies in proportion to its distance from the first prism, which is stationary, if, for instance, prism 2 moves I degrees. The third prism is moved 2 degrees, the fourth 30, the fifth 40, and the sixth 50. The tube of the telescope B is fastened to a lever H, which is connected by a hinge with the last prism, number 6. At the other end of this lever, or on the carrier of the telescope B, works the micrometer screw M, by turning which the tube B can be directed upon any part of the spectrum issuing from prism 6. This lever is so adjusted that, to whatever angle the telescope is turned, the amount of movement for the last prism shall be twice as great. The rays emerging from the middle of this last prism fall perpendicularly upon the center of the object glass of the telescope, the rays issuing from the collimator A and falling upon the first stationary prism 1, pass through the individual prisms in a line parallel to their base, and arrive finally on their emergence from the last prism 6 in the direction of the optical axis of the telescope. Whether it be directed upon the central or the terminal colors of the spectrum, the object glass is consequently always filled with light. As the tube B is turned towards any color of the spectrum, the lever H sets at the same time all the prisms in motion in such a manner that each adjusts itself to the minimum angle of deviation. The automatic spectroscope shows a great advance in the construction of compound spectroscopes, and has already been acknowledged as such by all authorities on this subject. The spectroscope, as exhibited, is in an unfinished state, having been sent to Mr. Huggins for arranging some small matters of convenience, such as the dividing of sector, reading microscope, etc. It consists of a combination of 4 compound prisms and 2 semi-compound prisms, all made use of twice the total power of the instrument, therefore being equal to 10 compound prisms, each having a dispersion of about 90. That is, a total dispersion of about 90 degrees, probably with the largest ever obtained. The observing and collimating telescopes are respectively 6 and 45 inches focus and 1 inch aperture, the section of pencil actually in use being 1 inch by 0.6 inch. This is perfectly constant from end to end of the spectrum, as the prisms are automatically worked. The prisms are 2 inches high, being just twice the height required for the section of the pencil. The lower half being made use of for the first course of rays, the upper for the backward course. Referring to the diagrams, the same letters of reference apply to both. The dotted lines represent those levers, etc., which are situated in a different plane, being at the back of the spectroscope. The right-angle prism of reflection, O, is applied only on the upper half of the first semi-compound prism, so that it does not interfere with the first course of the rays, which utilize only the lower half of the prisms. Chapter 28, Prism of Comparison, or reflecting prism by means of a careful examination of the spectrum lines of all known substances in which attend the parallel rays from the collimator enter the lower half of the first semi-compound prism without refraction. This prism, therefore, is stationary. They then pass through 4 entire compound prisms, 2, 3, 4, 5, and 1 semi-compound. 6. From which by 2 internal total reflections in the prism of reflection, 7, they are passed to the upper half of the prisms, by which they return through the 4 entire compounds and 2 semi-compounds, and are furally received, emerging from the first fixed semi-prism, by the right-angle prism of total reflection. And so passed to the observing telescope, which is placed at right angles to the collimator merely as a matter of preference. Any other position can be utilized if desired. The prisms in automatic arrangement are contained in an ion has not only been given to the brightness of the lines, but also to the exact measurement of airtight box. And both observing and collimating telescopes are stationary. Considerable advantages in such a powerful spectroscope, and allowing of great compactness. The several parts of the spectrum required to be examined are brought into the field by acting on the sector which carries the automatic arrangement, each line being exactly in minimum deviation when brought to the center of the field. The sector reading, by a vernier to 10 seconds of arc, divides the spectrum into about 20 zero parts. The mechanical arrangement of the automatic movement is that which we made a model of during Mr. Huggins' visit here last spring, and decided upon as giving the most constant and reliable results. The motion is given to the chain of prisms entirely by a 3S system of levers, which will be easily understood from the diagrams. The first 3 movable joints of chain, ABC, are connected by levers to the studs, G to 2BC, fixed in a circular disc which is rotated through 60 degrees by the tooth sector and pinion. The pins being fixed at their proper radii, the several prism tables through the required angle, the levers forming tangents in their mean position. The last 2 joints D and E were found geometrically to describe most accurately arcs of circles. J. They have their relative distances. Accurate drawings have been made of the spectra of various substances, some of which are given in the frontispiece and in the table, figure 61. If these tables be provided with a millimeter scale by which the distance between any 2 lines can be determined, they form a valuable standard of comparison in doubtful cases when examining the spectrum of an unknown substance. But in an ordinary spectroscope, no great dependence can be placed on the measures made with the photographic scale, for the breadth of the lines depends upon the width of the slit, and this may vary with each observer, the measurement too. And subsequent comparison of a spectrum with the spectra represented in the tables requires too much time, besides being laborious, therefore been attached to levers working on fixed centers, at back of spectroscope, shown in the drawing by dotted lines. The whole system of the automatic movement is composed of hardened steel pivots, working in hardened steel bearings, a system which can obviously be made to work with the greatest accuracy and constancy. The delicate steel parts of slit have been electrogilt to preserve them from oxidation. The jaws of gold plate are drawn asunder by a double wedge, acted upon by a screw, so as to preserve the axis of collimation. They are pulled together by a spring at the back. The micrometer head of screw is divided into 40 parts, each division being equivalent to each 11 inch of opening. The slots in the table of the spectroscope have nothing whatever to do with the guiding of the chain of prisms. They are merely to allow of the junction of the two systems of levers working in different planes. Monthly notices of R. Astronomical Society, Vol. 31, p. 36. The run is uncertain, while in many cases the spectrum to be examined is very evanescent, or perhaps appears under circumstances that make comparison with the tables either impracticable or quite untrustworthy in its results. In all such cases, it is well to employ a contrivance of Kirchhoff's by which only one half of the slit is employed for the spectrum to be examined, and the other half made use of for receiving a second spectrum from the incandescent vapor of the prism of comparison, or reflecting prism, a well-known substance which can then be compared directly with that under examination. For this purpose, the upper half of the slit remains free, and can, as shown in Figure 57, be made wider or narrower at will by means of the micrometer screw. In front of the lower half is placed a small equilateral glass prism, AB, which is movable and which cuts off from this portion of the slit all the rays of light falling directly in front of it. A reference to Figure 58, which gives a horizontal section of the vertical slit and prism of comparison, will easily explain its action. F is the source of light whence the rays pass straight through the upper half of the slit above the surface of the small prism, and form a spectrum according to the usual action of an invertant telescope in the lower half of the field of view. At one side, on a level with the prism, is placed the flame L, either a Bunsen burner or a spirit lamp, in which the substance is volatilized, the spectrum of which is needed for comparison with that formed by the light F. The rays from L falling at right angles on the surface DF will be totally reflected as by a mirror from the prism surface DC at the point R, and will emerge from the prism in the direction RS pass at 5 through CF, the prism of comparison, the lower half of the slit, and fall in the direction 5T on the lower half of the principal prism in the inside of the tube. In the same manner as the rays from F fell on the upper half, in this way the spectra 0 and U of the two flames F and L D light passing through each half of the slit is not restricted to the corresponding part of the prism, but since it consists of diverging rays, spreads itself over the collimating lens and then passes through the prism as a beam of parallel rays of the same diameter as the lens, or seen in juxtaposition in the same field of view as shown in Figure 59, where for greater clearness it is represented as it would appear if both images were thrown upon a screen. In reality, as the spectra 0 and U are seen through a telescope direct without a screen, their positions are reversed, so that the spectrum 0 from the upper half of the slit is seen below, and the spectrum U from the lower half is seen above. If the same substance be volatilized in the two flames F and L, the corresponding lines of one spectrum will fall in exact prolongation of those of the other. Because two pencils of rays of the same constitution will produce precisely similar spectra with the same width of slit, the same prism, and the same position of the telescope. If, therefore, the presence of a certain substance be suspected in one of the flames, for example in F, and from its spectrum received through the upper half of the slit, there remains some doubt as to its nature. A small quantity of the supposed substance is volatilized in the second flame L, and a comparison made between the juxtaposed spectra, if there be a complete coincidence between the lines of the upper and lower spectra. They both belong to one and the same substance, while in the case of want of coincidence, the body to be tested does not contain the same substance as that with which it is compared. From the extreme sensitiveness of the eye to the exact coincidence of two lines in two spectra produced under similar circumstances and observed at the same time. This mode of comparison forms one of the most important methods of spectrum analysis. Scope, figure 47, by means of the sliding ring C. It will be understood that instead of the second flame, the electric spark or one of Geissler's tubes filled with a known gas may be employed. The importance of this method. When applied to the spectrum investigations of the Sun, the fixed stars, nebulae, and comets can only be fully entered into when this part of the subject comes under discussion. For the ready comparison of various spectra, it is convenient to have always at hand the means of producing the spectra of known elements. For this purpose, small wax or tallow candles are prepared, the wick of which is impregnated with the various metallic compounds of chlorine, and they are employed as a secondary source of light in the manner above described. Chapter 29. Designation of the lines of the spectrum. Not only the number of the spectrum lines of a substance, but also the degree of their intensity is deserving of careful attention. As the brilliancy of the lines increases with the temperature, so, as a rule, it is those lines which are particularly prominent at a high degree of heat that are the first to appear at a low temperature. These prominent lines, therefore, are the most suited for the recognition of a substance, and on this ground are called the characteristic lines. Such lines, according to their degree of brightness, are designated in each substance by the letters of the Greek alphabet, A, SSY, A, etc., being affixed to the chemical sign denoting the substance. The spectrum of potassium, figure 61, number 1, has two characteristic lines, one red and one violet. The former, as the most intense, is therefore designated Ka, the latter by Ka-SS, the brilliant red line of lithium, figure 61. Number 3, frontispiece number 3 is called Li-A, the fainter orange line Li-SS. The characteristic lines of the spectrum of barium, number 6, are in the green. Those of cesium, number 8, frontispiece blue-violet, number 4, GS. A and CSS are blue. Those of rubidium, number 7, frontispiece, number 5, SS violet, and S7, dark red. The most intense line of hydrogen gas, frontispiece, number 7, is red and is designated by HG. The greenish-blue line nearly equal to it in brightness by HSS, and the much fainter violet line by H7, etc. The table in figure 61 exhibits the spectra observed by Kirchhoff and Bunsen as follows. 1. Potassium. 2. Sodium. 3. Lithium. 4. Strontium. 5. Calcium. 6. Barium. 7. Rubidium. 8. Cesium. 9. Thallium. 10. Indium collated for easy comparison with a statement of the color of the individual lines and a scale for determining their relative distances. The colors marked above number 1 represent the solar spectrum, in which the black lines, designated B up to H, will be hereafter explained. Chapter 30. Various methods for exhibiting the spectra of terrestrial substances. The spectra of incandescent solid and liquid bodies are continuous, and resemble each other so closely that only in a very few instances can they be distinguished. Spectra of this kind are therefore not suitable for the recognition of a substance, though they authorize the conclusion, as a rule, that the substance is either in a solid or liquid state. Only the discontinuous spectra, consisting of colored lines which are obtained from a gas or vapor, are sufficiently characteristic to enable the observer to pronounce with certainty by the number, position, and relative brightness of these lines the chemical constitution of the vapors by which the light has been emitted. It follows from this circumstance that spectrum analysis deals preeminently with the investigation of gas spectra, and that for the examination of a substance which does not exist in nature in the form of gas or vapor, the first step must be to place it in this condition. Use of the Bunsen burner. The temperature at which substances are volatilized varies greatly, while the heat of an ordinary spirit lamp is sufficient for many, such as potassium and sodium. For others, especially the heavy metals and their compounds, the great heat of the electric spark is requisite. In many cases, however, the temperature of the non-luminous flame of the Bunsen burner is sufficient to volatilize the substances intended for examination and to cause them to emit a light sufficiently intense to give a brilliant spectrum. A Bunsen burner, as shown in Figure 2, is therefore one of the necessary requisites for spectrum investigation. In using the lamp, the air is first shut off below in a pure continuous spectrum of the luminous flame, obtained by an accurate adjustment of the telescope and a careful setting of the slit. To prevent flickering, the lower part of the flame is surrounded, as shown in Figure 52, by a hollow cone of sheet iron. By the introduction of atmospheric air, the flame is then rendered non-luminous, and only the upper very hot point of the flame made use of, into which the substances to be tested are brought from the side by means of a thin wire of platinum, a metal on which this temperature has no influence. When the spectrum appears, the focus of the telescope must be adjusted immediately, and the slit narrowed sufficiently to ensure the bright-colored lines being sharply defined. In the Bunsen burner, spectra can only be obtained from the metals potassium, sodium, lithium, strontium, calcium, barium, caesium, rubidium, copper, manganese, thallium, and indium, and from these most readily when they are in combination with chloride, in which state they are most easily volatilized. Some time ago, Roscoe and Clifton investigated the different spectra presented by calcium, strontium, and barium, and they suggest that at the low temperature of the Bunsen flame, or a weak spark, the spectrum observed is produced by some compound, probably the oxide of the difficultly reducible metal, whereas at the enormously high temperature of the intense electric spark, these compounds are split up, and thus the true spectrum of the metal is obtained. In none of the spectra of the more reducible alkaline metals, potassium, sodium, lithium, can any deviation or disappearance of maxima of light be noticed on change of temperature. In a recent paper on the spectra of Erbia and some other Earths, Huggins, after describing the bright lines seen in the spectra of some Earths when incandescent in the oxyhydrogen flame, remarks, "The question presents itself as to the nature of the vapor to which the bright lines are due in the case of the Earths, lime, magnesia, strontia, and baryta. Is it the oxide volatilized, or is it the vapor of the metal reduced by the heat in the presence of the hydrogen of the flame?" The experiments show that the luminous vapor is the same as that produced by the exposure of the method of introducing the substances to be examined into the flame by means of a platinum wire has this drawback, that the spectrum is visible only for a very short time, and in many cases the bright lines flash out only to vanish again immediately. In order to observe the spectrum for a longer time, it is necessary, therefore, to be constantly introducing new material into the flame, a tedious and troublesome process. To overcome this difficulty and obtain and pur the chlorides of the metals to the heat of the Bunsen gas flame, the character common to these spectra of bands of some width, in most cases gradually shading off at the sides, is different from that which distinguishes the spectra of these metals when used as electrodes in the metallic state. As the experiments recorded in this paper show that the same spectra are produced by the exposure of the oxides to the oxyhydrogen flame. Roscoe and Clifton's suggestion that these spectra are due to the volatilization of the compound of the metal with oxygen is doubtless correct. The similar character of the spectrum of bright lines seen when Erbia is rendered incandescent would seem to suggest whether this earth may not be volatile in a small degree, as is the case with lime, magnesia, and some other earths. The peculiarity, however, of the bright lines of Erbia, observed by Barr and Bunsen, that they could not be seen in the flame beyond the limits of the solid Erbia, deserves attention. My own experiments to detect the lines in the Bunsen gas flame, even when a very thin of a wire was used, so as to allow the Erbia to attain nearly the heat of the flame, were unsuccessful. The bright line in the green appears indeed to rise to a very small extent beyond the continuous spectrum, but I was unable to assure myself whether this appearance might not be an effect of irradiation. It is perhaps worthy of remark that the chlorides of sodium mannate spectrum Mitscherlich has devised the following expedient. A solution of the substance to be examined is introduced into a small glass vessel at figure 62, closed at the top and bent round at the lower end, which terminates in a narrow tube beehive. In this opening is placed a bundle of very fine platinum wire C, tightly held together by a wire of platinum, and secured into the tube by the bent position of the wires. By capillary attraction, the liquid is continually drawn through the opening by potassium, lithium, cesium, and rubidium, give spectra of defined lines, which are not altered in character by the introduction of a Leyden jar, and which, in the case of sodium, potassium, and lithium, we know to resemble the spectra obtained when electrodes of the metals are used. Now all these metals belong to the monad group. It appeared therefore interesting to observe the behavior of the other metal belonging to this group. Chloride of silver, when introduced into the Bunsen flame, gave no lines. The chloride was then mixed with alumina, which had been found to give a continuous spectrum only, and exposed to the oxyhydrogen flame, but no lines were visible. When, however, the moistened chloride was placed on cotton and subjected to the induction spark without a jar, the true metallic spectrum was seen, as when silver electrodes are used. The behavior of silver, therefore, is similar to that of the other metals of the monad group. Now the difference in basic relations which is known to exist between the oxides of the monatomic and polyatomic metals would be in accordance with the distinction which the spectroscope shows to exist in the behavior of their chloride. The chlorides of the polyatomic metals would be more likely to split up in the presence of water into oxides and hydrochloric acid. In the case of some of the oxides and chlorides, one or more of the lines appeared to agree with corresponding lines in the metallic spectra. It may be, therefore, that under some circumstances, as in the case of magnesium burning in air, the metallic vapor and the volatilized oxide may be simultaneously present, the platinum wicked to the place of volatilization. A series of such tubes may be ranged round the circumference of a revolving table D, figure 63, so that the platinum wick of any one of them can be brought at will into the flame of the Bunsen burner placed near the edge of the table. An addition of acetate of ammonia to the solution assists the capillary action of the platinum wick, which, when rightly placed in the flame, allows of the spectrum being continuously observed for nearly 2 hours. Not less complete, and more generally applicable, is the following contrivance by Morton of Philadelphia, which, intended principally for the production of monochromatic homogeneous light on a large scale, is also employed in spectrum researches for bringing a continuous supply of greater quantities of the substances to be examined into the Bunsen flame. The apparatus consists of 4 or 5 ordinary non-luminous Bunsen lamps AB, figure 64, fixed into one common gas tube D and enclosed below, where the supply of air is received by a cover in G of tin CD. At one side of this case is a wide opening C, through which the point F of a disperser E supplies a stream of vapor by the heat of a spirit lamp, or else a stream of air is driven through the tube F by means of bellows or an Indian rubber ball. In the manner of an ordinary spray apparatus, close under the orifice of the pointed tube F is a glass tube which reaches down into a glass vessel containing a solution of the substance to be examined. The stream of air or vapor forces some of the liquid in the vessel G up the vertical glass tube and disperses it. The fine particles, mixed with a sufficient quantity of atmospheric air, are driven forcibly through the orifice C into the tin can, where they are mingled with the cold gas and are volatilized at the mouth of the burners. By this method, Morton has produced monochromatic light of various kinds on a large scale, especially the yellow light of sodium. By the use of a solution of common salt, which, with a suitable disposition of 60 such sets of burners, he employed for the production of magic effects on the stage. Application of the induction coil. When the heat of the Bunsen burner is not sufficient to volatilize the substance to be investigated, recourse must be had to those sources of still greater heat that have been already described: oxyhydrogen flame, T23, the voltaic arc P39, the induction coil, P33, among which the induction coil deserves the preference on account of its greater facility of management. The apparatus is employed in the usual manner by moistening the ends of the platinum wires. between which the spark passes with the substance to be investigated, and examining the spectrum of the spark, or, when this heat is insufficient, by intensifying the spark through the interposition of a special condensing apparatus. P33. In general, however, the effect of this method is to produce two different spectra, which are superposed, one of the gas in which the spark passes and the other of the metal forming the poles. If electrodes of different metals be employed and the spark be allowed to pass always through the same gas, the spectrum of the luminous gas appears as if it were a background upon which the more intense spectra of the metals are well relieved. The way in which a Leyden jar is interposed for intensifying the spark is easily understood by reference to Figure 65. M is the end of the induction coil, which, to ensure a discharge of some intensity, is supplied with electricity from a powerful Bunsen battery of from 6 to 8 elements, Figure 13. The extremities of the coil are fastened into the insulated binding screws 1 and 2. From the first of these pass two wires, one to the binding screw D and the other to the knob K, in connection with the inner coating of the intensifying jar. From the second also pass two wires, one to the binding screw A, and the other to O, where it is connected by means of the copper disc T with the outer coating of our car. B and D are wire holders for the reception of the metals, the spectra of which are to be examined, or for the insertion, when necessary, of platinum wires, the ends of which may be smeared with the substances to be investigated. The upper metallic arm, ABD, is insulated from the lower arm DD by the intervening piece of ebonite, so that the equalization of the opposite electricities accumulated in ion 2 can take place only through the wires B and D, and the spark can only pass when the quantity of electricity accumulated in the jar R is of such an intensity as to enable the discharge to break through the stratum of air between the wires B and D. Sparks produced in this way are shorter than those not intensified, but far more powerful. They are very bright and of so intense a heat that all metals may be raised to incandescence in them and volatilized. The spectra thus obtained are unfortunately not steadily visible, for owing to the discontinuous action of the machine, they flash out momentarily with every fresh spark, and by their inconstant light interrupt investigation. Hash browning has much improved and simplified this method of introducing a Leyden jar into the current of an induction coil by substituting plates of ebonite for the glass jar. When these are coated on both sides with tinfoil, they act like a Leyden jar. Browning places from 4 to 6 of such plates in layers entirely insulated one from another, enclosed in a case A, seen in Figure 66. By a simple mechanical contrivance inside the box, one or more of these intensifying plates can be used as required. The brass rod B, with the two ebonite holders CD for wire or glass, is screwed onto the lid of the case and is placed within the box when the condenser is not in requisition. The substances to be investigated, or the metal wires, are inserted between the platinum forceps 3 and 4, from the binding screws of which the conducting wires 1, 2 lead to the poles V, Y of the ebonite plates projecting from the box. The whole apparatus is by means of the same binding screws placed in connection with the wires 1, 2, Figure 65, of the induction machine. The ebonite holder D is fitted for the reception of glass tubes or other vessels provided with conducting wires, the details of which will be given hereafter, and by the help of a spring of Geissler's tubes, so that the spectrum of the substances they contain, whether in a liquid or gaseous condition, may be brought under examination. The first successful contrivance for the examination of the spectra of liquids and of substances in a state of solution is due to Siegen of Grenoble, whose plan has been greatly extended and variously applied by Becquerel. The contrivance, as arranged by Ruhmkorff and Browning for convenient use, consists of several glass vessels, BB2, Figure 67, 5 or 6 inches in height, and rather more than an inch in width, inserted in the small, while at the other they are closed by corks. A platinum wire fused into the lower end of the vessels, and projecting into the inside, places the liquids they contain in connection with the negative pole of the induction coil, while a second platinum wire fused into the narrow glass tubes, A all 9 A2, passes through the corks from above and projecting 1/20 of an inch from the small tubes, remains some tenth of an inch distant from the surface of the liquids. By connecting the binding screws 1, 2 on one side with the inductor and on the other side, as shown in the figure, with the platinum wire bead of the first vessel and a 2 of the last vessel, and by placing the other wires in connection, A with BZ, at with B2, etc., the electric current may be made to pass through all the liquids, and by the passage of the spark between the upper platinum wires, A2. The substances in solution may be volatilized in the heat, and their various spectra obtained at the same time. When the action of the induction coil is so regulated that the interruption of the current and consequent passage of the spark takes place in rapid succession, the spectrum remains almost perfectly free from disturbance, and the apparatus works for hours together like an intense heat lamp, constantly fed with the substances to be investigated. As, however, by the rapid succession of sparks, the liquids in the smaller glass tubes often become considerably heated, wider tubes should be employed when the apparatus is to be used for many consecutive hours. For these experiments, solutions of the various metallic compounds of chlorine in pure water are the most suitable. When in a concentrated form, they produce spectra of great intensity, but weak solutions will give spectra that are easily to be recognized. The spark is colored more or less intensely according to the nature of the metal held in solution. The following metals give great brilliancy to it: chloride of sodium, yellow; chloride of strontium, red; chloride of calcium; chloride of magnesium; chloride of copper, greenish blue; chloride of zinc, blue; but various other compounds of barium, potassium, antimony, manganese, silver, uranium, iron, etc., give also very remarkable colorings and corresponding characteristic spectra. It is one advantage of this method of investigation that the spark from platinum wires produces no direct spectrum of platinum, inasmuch as the heat is not sufficiently great to volatilize this metal completely. For the investigation of the spectra of gases, either Plucker's tubes, figure 12, may be employed, for which, besides the glass tubes provided with platinum or aluminium wires, a special quicksilver air pump is requisite. Or Angstrom's plan may be adopted, in which the electric discharge from a Leyden jar or induction machine is allowed to pass between 2 points of one and the same metal enclosed in glass tubes, which are filled with the gases to be examined. In the first case, the tube R, filled with highly rarefied gas, is placed within the spring clamp B, lined with cork, and movable upon the stand at figure 68. Which at the same time revolves upon its horizontal axis, and therefore serves to place the tubes vertically or horizontally as may be required. When the electric discharge passes through the tube, the enclosed gas becomes luminous and shines in the narrow part of the tube with an intense light. It is only necessary then to bring the slit of the spectroscope as near as possible to the tube in a position parallel to its length, to recognize at once a distinct spectrum of the gas in the other plan. Where the spark passes between 2 points of metal in the gas to be investigated, the gas or metal spectrum is more or less brilliant according to the distance of the points one from the other. The spectrum of the gas should therefore be observed in the middle between the metal points, where it is most distant for Plucker's tubes, distinctly marked and most easily distinguished from the discontinuous spectrum of the metal. Chapter 31. Influence of temperature and density on the spectra of gases. Bunsen and Kirchhoff have proved that the degree of heat of the flame in which a substance is volatilized and made luminous has no influence on the position of the colored lines of the spectrum, but that it affects considerably their number and brightness. As the brightness increases with the temperature of the flame, it often happens that bright lines will appear in the spectrum of the same substance at a high degree of heat, which were scarcely to be seen, or indeed were invisible, at a lower temperature. The spectrum of thallium, a metal recently discovered by spectrum analysis, consists of a single bright green line when volatilized in a Bunsen burner. But if the electric spark be allowed to pass between 2 thallium wires, many other lines become visible at the far higher temperature of the spark, among them a set of violet-colored bands at some distance from the bright green line. Lithium in a moderate temperature gives only the one magnificent red line already alluded to. At a higher temperature, a faint orange line makes its appearance, and at the small plate of glass held airtight over the opening by elastic band, an arrangement which permits of any deposit on the inside of the tube being easily removed. By this method, fresh portions of gas are constantly exposed to the spark, which is of importance when some compasses are under examination, and some sources of impurity, which are possible when the gas is collected, are avoided. Tremenit of the voltaic arc Tyndall was the first to notice, during a lecture at the Royal Institution, the further addition of a bright blue band. The principal red line, Ka of potassium, can be made to appear and disappear according as the temperature is increased or diminished, by the use of an ordinary Bunsen burner producing a moderately high temperature. This line is always apparent in the spectrum of potassium, but if the temperature be raised by the use of bellows, it immediately disappears. If a few grains of common salt be dropped into the flame of a Bunsen burner, there is emitted an intense light of one color, producing a spectrum of one single yellow line. If the temperature of the flame be raised by a further supply of oxygen, the brilliancy of this line is immediately augmented, and the number of colored lines so much increased as to approach somewhat to a continuous spectrum. If Debray's heating up ethylene, 1863, Huggins observed that when an induction spark is passed between electrodes of sodium, in addition to the well-known double line, 3 other pairs of lines in a nebulous band make their appearance in the spectrum. The 2 more prominent of these are not far from air lines, and with an instrument of insufficient dispersive power might easily be confounded with them. He showed that these lines really belong to sodium, and not to accidental impurities. Rhodas be made use of, and the sodium vapor raised to the temperature of 2,500 degrees Celsius. 45.3, 2 degrees. Far, the bright lines become so numerous that the different colors run one into the other, and produce a continuous spectrum. The former yellow sodium flame has become white, and contains rays of every degree of refrangibility. Plucker and Hitter have obtained similar results in their researches on the spectra of luminous gases and vapors, whereby they prove the existence of 2 different spectra of the first and the second order in hydrogen, nitrogen, oxygen, phosphorus, sulfur, selenium, etc. The spectrum of the first order is a continuous one with shaded bands. That of the second order consists of narrow bright lines on a dark background. The former appears with an electric discharge of moderate tension, while the latter belongs to a high temperature, such as can be produced in Geissler's tubes by the electric spark at a high tension. There is also at least one bright line between the well-known lines coincident with D. He describes his comparison of this spectrum of sodium with the solar spectrum thus: so numerous are the fine lines of the solar spectrum, and so difficult is it to be certain of absolute coincidence, that I hesitate to say more than that. The pair of lines 821 of the scale of the maps in Phil, 1864, appeared to agree in position with Kirchhoff's lines 864-1 and 867-1, and of the pair 1169 and 1174, one appears to coincide with a line sharply seen in the solar spectrum, but not marked in Kirchhoff's map, which would be about 1150 to 2 of his scale, and the other with Kirchhoff's line 1154 to 2. The other pair in the nebulous band acts too faint to admit of satisfactory comparison with solar lines. Still, however, in some cases where the same kind of electric discharge is employed, different spectra are obtained according to the degree of density given to the gas enclosed in the tubes. Wilner has followed out these investigations with hydrogen, oxygen, and nitrogen, and obtained, according to their degree of density, from 2 to 4 spectra for each of these gases. The following remarkable phenomena are exhibited by hydrogen with the use of one of Ruhmkorff's large induction machines, set in action by a battery of 6 of Grove's elements, and with the occasional introduction of a Leyden jar, figure 65. When the pressure to which the gas is subjected is much less than 1/20th of an inch of mercury, the spectrum is discontinuous, consisting of 6 groups of extremely bright lines in the green. When the density of the gas increases, there appears temporarily, by the use of a simple induction current not too strong, a spectrum of bands I ordered, figure 69, number 1, which, however, on the pressure of the gas amounting to 1/20th of an inch, soon changes into the spectrum of lines designated by Plücker as secondite order, figure 69, number 2, and consisting of the three lines HA, vivid red, HSS, bright green-blue, and high blue-violet and fainter than the others. Compare frontispiece number 7. When the pressure on the gas exceeds that of 1/10 of an inch, a bright light appears in the red and in two places in green, and with an increase of pressure, the spectrum assumes more and more the character of a spectrum of bands I order, extending from orange to blue, but still crossed by a series of bright lines between HEI and HSS. Up to a pressure of 8 inches, this spectrum retains its full brilliancy, but as the pressure increases to 16 inches, it gradually loses in intensity, without its general character being essentially altered, excepting that the individual lines, as was observed by Plücker, begin to widen. If the pressure be still further increased, the spectrum becomes brighter again. The yellow and the orange gradually reappear. The line HEI remains still very bright, but is somewhat indistinct at the edges. From this line, however, a completely continuous spectrum without bands extends from the orange to the violet, and is brightest where the line HSS was situated. With a further increase of density, the brightness of the spectrum is throughout much increased. Under a pressure of 29 inches, there is still a faint maximum of light perceptible at the spot HV, which at a pressure of 39 inches almost ceases to be visible. The spectrum is then completely continuous between HA and HSS, like that of an incandescent solid body. Only the brightness is somewhat differently distributed. The temperature of the tube is now raised so high by the heat of the gas that the sodium line appears as a bright orange line, which is occasioned by the vapor of sodium given out by the glass. With a pressure of 48 inches, the whole of the continuous spectrum is really dazzling. And even under a pressure of 52 inches, the electric discharge from the jar may still be passed through the tube, though it now takes place only by flashes. The changes, therefore, through which the spectrum of hydrogen gas successively passes when the density of the gas is gradually increased from the minimum up to the maximum pressure, at which the induction current ceases to pass, are as follows. The spectrum of 6 lines in the green. 2, the temporary spectrum of bands, I order. 3, the spectrum of 3 lines, 2 order. 4, the more permanent and complete spectrum of bands, I order. 5, the pure continuous spectrum. That the shaded spectrum of bands, figure 69, number 1, differs essentially from the unshaded continuous spectrum, is shown by Wöllner's observations with the Leyden jar. When the condenser was introduced, the shaded spectrum was not visible, but by an increase of pressure, the spectrum of the 3 lines, H, SS, H7, passed at once by a widening of the lines into the unshaded continuous spectrum. It is therefore incorrect to describe, as is often done, a spectrum of bands as a continuous spectrum of I order, and also to speak of 2 distinct continuous spectra. Oxygen exhibits nearly the same phenomena. Under slight pressure, there first appears a spectrum of bands. As the pressure increases, this spectrum gives place to what Plücker has designated a spectrum of lines, which loses in brilliancy as the density of the gas increases, till at a pressure of 8 inches it is scarcely visible. The brightness then augments, and at the same time there appears as a background an unshaded pure continuous spectrum, which becomes so brilliant in the red and yellow as to incorporate with itself the lines of the other spectrum, which are no longer distinguished by their greater brightness. In nitrogen, the change from the spectrum of bands, I order, to the pure continuous spectrum is very distinctly marked, since at a certain density of the gas, the spectrum of bands I order, figure 69, number 3, disappears and is replaced by the spectrum of line secunde, order upon a dark background. It is not till afterwards that the background becomes quite continuous and luminous. if it be conclusively established by these investigations of Wüllner that the various spectra of a gas are dependent upon its density, and that the continuous spectrum is formed at the greatest density and with the strongest induction current that can be made to pass. Yet the answer to the question as to the dependence of these spectra upon the temperature of the gas is still left to conjecture, since the connection between the kind of electric current and the temperature of the spark or of the glowing gas has not yet been ascertained. Everything, however, seems to point to the conclusion that the spectrum of bands high order is characteristic of the lowest temperature, a conclusion which seems to be borne out first of all by the early observation of Plücker and Heinrich, who always obtained a spectrum of batids with a simple induction current, but a spectrum of lines when a condenser was introduced, and secondly by the observations made by Wüllner on a great variety of gases. The spectrum of lines to be order is the result of a higher degree of heat, the continuous spectrum that of the highest temperature. The spectrum of 6 lines occurs at the minimum pressure under a similar condition of the electric discharge by flashes or impulses that took place with the maximum pressure. The temperature of the gas producing the spectrum is therefore in all cases higher than that by which a spectrum of bands is produced. In conformity with this view that the continuous spectrum appears only with the highest temperatures, such as are requisite to render luminous gas of great density, is the fact discovered by Frankland that as the yellow sodium flame becomes white when burning in a stream of oxygen, and then emits rays of every refrangibility, so also does the flame of hydrogen, usually so little luminous, become a white luminous flame in compressed oxygen gas by an increase of temperature when it emits a continuous spectrum. The doubt still left by these investigations as to whether the difference in the spectra of hydrogen is to be ascribed mainly to the influence of pressure or to the temperature conditional on that pressure must first be settled before it can be determined from the appearance of one or other spectrum what the amount of pressure is to which the gas is subjected. And this is rendered the more necessary by the investigations lately undertaken by Secchi concerning the various spectra of hydrogen, nitrogen, bromium, and chlorine. Secchi sent the electric spark from an ordinary friction machine through a tube filled with rarefied nitrogen, the tube being so constructed as to consist of 3 lengths of tubes of various calibers, the first portion a capillary tube, the second part 1/8 of an inch in diameter, and the third about 3/10 of an inch. When the conductor was placed in connection with one of the platinum wires from the tube, while the other wire communicated with the friction cushion, there was seen in the capillary tube only the spectrum of I in order, consisting of narrow connected stripes or bands, giving the appearance of grooves, figure 69, number 3. When, on the contrary, one of the platinum wires was connected with a metal knob, and a spark allowed to pass, while the other wire conducted to the earth, the spectrum changed according to the length of the spark. When the spark reached the length of 3/4 of an inch, the capillary tube shone with a green light, and gave a spectrum of lines, or that of 2 order, while the wider portions of the tube gave a spectrum of bands of I order. With a sufficient length of spark, therefore, 3 varieties of spectra may be seen at the same time. In the narrowest part of the tube, the spectrum of it, order with bright lines appears, and in the 2 wider parts of the tube are to be seen spectra of bands or stripes. One of these latter spectra is that described by Plücker as consisting of fine groove-like bands, and the other is composed of wider bands, which are so spread out that 3 of them are equal to 8 of the former. The same phenomena occur if instead of an electrical machine, a powerful induction coil be used, and a condenser introduced into the current. Similar results were obtained from bromine, chlorine, and hydrogen, which prove that in different actions of the same tube filled with gas of the same density, spectra of the various orders may be obtained at the same time. Now, the influence of the diameter of the tube upon the temperature of the enclosed gas is the same, no doubt, as that which occurs in the metal wires, in which it has been established that the heat increases in an inverse ratio to the square of the diameter. It therefore follows that the temperature of the gas is greatest in the capillary part of the tube, and that under an equal pressure of the gas, the spectrum of band's eye order corresponds to a lower temperature than the spectrum of lines to light. Order. The temperatures at which these spectra of the various orders are produced are not the same for all gases. In a tube containing both nitrogen and aqueous vapor, the lines of hydrogen, spectrum sucum, order, made their appearance at the same time as the spectrum of band's eye order of nitrogen, whence it follows that the lines of hydrogen are visible in a temperature in which the lines of nitrogen do not appear. Chapter 32. Influence of the temperature of gases on the width of the lines of the spectrum. The width of the lines of the spectrum. The width of the lines of the spectrum depends in general upon the width of the slit of the spectroscope. By widening the slit, these lines also widen, without their brilliancy being affected. This width, as a rule, is not less than that of the slit, but lines wider than the slit are often observed. An exception to this rule is found in some lines in the spectra of gases when they have been produced at different temperatures. The spectrum of hydrogen occupies so important a place in the investigations of the physical constitution of the sun and other heavenly bodies that it will be desirable here to mention the facts which relate to the widening and contracting of the three characteristic lines. Plicker and Hittorf were the first to observe that in a narrow tube filled with hydrogen, the three characteristic lines, Ha, H, SS high, frontispiece number 7, appeared at a certain degree of rarefaction. By raising the temperature of the tube by the introduction of a Leyden jar, or other means of intensifying the electric discharge, an increase of the width of the line HY towards both ends of the spectrum is first apparent. Then a widening of the line HSSY remains almost unchanged till HY has passed into an undefined broad violet band, and HSS has, with diminished intensity, become extended in both directions. With a pressure of 2 inches, the spectrum of lines has already passed into a continuous spectrum, and under a pressure of 14 inches, the intensity of the spectrum has so much increased that the red line HEI, now widened into a band, is scarcely distinguishable from the rest of the spectrum. When the gas is highly rarefied, the line HEBA is the first to disappear, while HACS is still distinctly visible. These observations upon pressure have been confirmed by Wöllner as follows. Under a pressure of S of an inch, the spectrum of hydrogen consists of the 3 lines. With a pressure of JL inch, the line HY is considerably increased in width, SS less, so while HUDA remains unchanged. When the pressure is increased to 18 inches, the lines Y and HSS have so far expanded that continuous bands of color appear in their places, and HA is visible only as a wide diffused line. Until at the great pressure of 22 inches, the spectrum is perfectly continuous, and Ha is no longer to be recognized as a line, but is changed into a broad red space. It was found by Secchi by employing tubes of varying caliber, section 31, that with a diminution of the tension and temperature of the electric spark, the width of the hydrogen lines decreased, till with the same width of slit they disappeared, or else became very fine and scarcely to be seen, in the parts of the tubes of greatest diameter, while they continued visible in the capillary portions. It therefore follows that with the same pressure on the gas, a diminution of temperature is accompanied by a narrowing of the hydrogen line. And it seems that with a given density, there is a limit of temperature at which the 3 bright ions of this gas disappear. Were it possible to estimate this temperature, the amount of pressure to which the gas was subjected could be inferred. This question is involved in considerable difficulty, but is at the same time of such great importance in the investigations of the solar atmosphere, that it will no doubt soon engage the attention of those physicists who have the requisite apparatus at their command. Chapter 33. Influence of temperature on the delicacy of spectrum reactions Bunsen and Kirchhoff discovered in their first labors on this subject that the spectra of alkalis and alkaline earths increased in intensity as the temperature to which they were subjected increased, but it remained uncertain whether the increased brightness resulted merely from the increased volatilization of these metals or from the consequent increased delicacy of the spectrum reactions. Capel has therefore lately renewed these investigations. Solutions of the metallic salts were volatilized between the poles of a small induction machine, giving a spark half of an inch long, and by the use of Mitscherlich glass tubes. Provided with platinum wicks, figure 62, the spectrum made permanent for some time. A series of solutions, each half the strength of the preceding one, were prepared from a number of metallic chlorides. The spectrum of the metal, which was in connection with the positive pole, was continuously observed, while increasingly concentrated solutions were brought in succession into the electric current till the lines of the substance, the position of which had previously been accurately determined for that particular spectroscope, were clearly visible. No result of these observations is given in the TIG table. Susceptibility the Sukin, 1 mg's name of the metal investigated. By the use of the induction spark, by the use of the Bunsen burner, cesium 425, 0 rubidium, 1070 potassium, 30 sodium, lithium 600 barium, 900 strontium, 30 calcium, 50 magnesium, 500 chromium, manganese 200, zinc J 600, 0 indium, 90 2, 0 thallium, 50 cadmium, 18 lead, 20 bismuth, 70 copper, 20 silver, 10 gold, 4 around 10 17 second. Column contains the monema of metallic substance needed to produce the principal characteristic line, therefore the most sensitive line of the metal. It shows that by the use of this minimum of metallic substance, the spectrum consists of only one single line, with the exception of copper, the spectrum of which, even with the smallest perceptible mixture, is composed of 3 lines. The third column is compiled from earlier observations, so modified that the weight of the mixtures has reference to the amount of metal contained in the compound. From this table, it appears that, with the exception of the alkalis, the susceptibility of the spectrum reactions in the metals, inclusive of lithium, is from 40 to 30 times greater in the heat of the electric spark than in the temperature of the non-luminous gas flame. Many new lines make their appearance in the spectrum of the induction spark, which are not visible at a lower temperature, as a practical result of these investigations by Capel. It seems to be established that the spectrum analysis of alkalis is best conducted by the temperature of the oxyhydrogen flame, and that of other metals by the electric spark. It seems probable that by the use of still higher tension, such as may be obtained by the introduction of condensers, figure 65s, the sensibility of the spectrum reactions in a great number of metals may, in consequence of the higher temperature, be raised above the foregoing limits. The importance of the choice of a suitable temperature in investigations with spectrum analysis is shown by the behavior of strontium. If, for example, of a milligram of this metal be taken, a quantity that can be detected by the ordinary mode of analysis, L part of this small quantity will be shown by its spectrum analysis in the Bunsen burner. But if the electric spark be employed, G part of this last small particle may be distinguished with the greatest certainty. Capel, therefore, rightly maintains that in searching for new metals, the employment of high temperatures is very important, and that the use of very powerful induction machines, with the addition of condensers, would very probably lead to the discovery of new elements. Chapter 34. The colors of natural objects besides the colors of the spectrum, which are the simple elements composing white light. There is another class of colors apparent in every substance, which are therefore known as the colors of natural objects. When we see that a picture is formed by covering the canvas with various pigments, and that leaves and flowers are bright with the most beautiful tints, while white cloth becomes red-green or blue according to the color of the liquid into which it is dipped, we are easily led to believe that every substance carries in itself its own color, which is peculiar to it alone, and is inherent in the substance. At most, we might admit that light was requisite to render the color visible, and yet this is not so. Were colors really something inherent in the object, every colored substance would manifestly appear always of the same color by whatever light it was illuminated. But this, as everyone knows, is not the case. The beautiful violet dress, which in daylight appears of the purest color, seems dull and gloomy by gaslight, Materials which in daylight are a bright blue are tinged with green in candle or lamplight. And what if the landscape or a colored object be viewed through a tinted glass? All colors then seem changed, without the objects in themselves being altered. If the color of the glass be intense, the various colors of the objects immediately disappear, and everything seems shaded in the color of the glass. The same thing happens if some common salt be rubbed into the wick of a spirit lamp, and surrounding objects viewed by the yellow light of such a flame. The colors disappear or lose much of their brilliancy, and everything seems either in mere light and shade or else of a dull gray. These facts clearly prove that colors are not inherent in objects, that they have no independent existence, but that they are called forth by some extraneous cause. On the other hand, these considerations show that there must be something in the objects themselves to help in the formation of color, for they in no way assume the color of the light illuminating them, but appear, as a rule, of quite a different hue. The natural color of an object is that in which it appears when illuminated by the pure white light of the sun or by daylight. It is called red or blue when it so appears by daylight. Now, if an object be illuminated by white light and yet appear of another color, the cause of the change must be looked for in the influence which the surface of the body exercises on the ether, waves constituting white light. The effects of this influence are very different according to the nature of the coloring matter with which the object is provided, but they may mostly be reduced to one of two cases, either that a portion of the ether motion is entirely stopped, or so considerably diminished in its passage over the ponderable atoms of the substance as that heat instead of light is evolved, or else that the ether waves are irregularly reflected from the surface of the object. As sometimes occurs with the waves of sound, in the first case the rays of light are said to be absorbed, in the latter scattered. When the surface of a body has the property of absorbing all the colors of the solar spectrum with the exception of one, the red, for example, that body appears red to us by daylight because this color alone is reflected to the eye. When, on the contrary, it has the power of absorbing some of the rays, the red and orange, for instance, and of reflecting the others, namely, the yellow, green, and blue. The color of the object will then be that produced by the mixture of the unabsorbed, the reflected colors. Now, as white light contains the eye, so whole range of colors visible in the spectrum. It can easily be understood why so many different colored objects should be seen in nature with such an infinite variety of tints. When all the colors of white light are reflected from an object in the same proportions as they occur in the solar spectrum, the object appears white by daylight and brilliant in proportion to the quantity of light it reflects. In proportion, however, as it reflects fewer rays of all kinds, the white loses in intensity. The object appears first gray, then dark, and at last black when all the rays falling upon it are absorbed, and none reflected. Those objects are therefore black, the surfaces of which are so constituted as to absorb all the colored rays of white light. Those are white which reflect all the rays which fall upon the surface, and those are colored which reflect some of the rays and absorb others. A white object may therefore appear of all colors. If red light falls upon it, it reflects it to the eye, and appears red. In blue light, it appears blue. In green light, green, etc. Whereas a black object always appears black, whatever may be the color of the light by which it is illuminated. We may here further remark that a colored substance assumes a different tint when illuminated by colored light, and then appears of another than its natural, that is to say, daylight color. Vermilion, for example, when placed in red light, becomes of a more fiery red. In orange or yellow light, it appears orange or yellow, but deeper in tone. Green rays impart to it something of their own tint, but at A, the red substance can reflect only a few of the green rays. It appears pale and dull by their light. It seems still duller and darker in blue light, and with indigo and violet, it is almost black. These phenomena are explained by the supposition that the surfaces of colored bodies possess the property of reflecting the rays of one particular color in far greater proportion than those of the other colors. They do not therefore appear black when illuminated by a light differing from their own natural color. Take, for example, a piece of paper half of which is colored a deep blue and half red. The colored rays, other than the blue and red, are not all absorbed. It is true that the blue piece reflects the blue rays preeminently and in greatest number, as the red part does the red rays. But the red has also the capability of reflecting other rays to a small amount. If the pure yellow light of a spirit flame impregnated with salt be allowed to fall on the paper in a completely dark room, the paper must appear black if the coloring matter reflect only the red and blue rays, because the yellow rays of the burning sodium will be absorbed, and no other light falls upon the paper. But this is not the case. The paper only appears black on the blue part. The red half is still visibly colored, though of a decidedly yellow shade. We therefore conclude that the blue of the paper does not reflect the yellow rays, but that the red has that power in a small degree. Almost all colored objects act like the red paper. They reflect preeminently one particular color, namely, that one of which they appear by daylight, but they are able also to reflect in small quantities all other, or at least some other colors, and so they vary in tint according to the kind of light in which they are seen. The colors of objects are very rarely pure and simple like those of the spectrum. Most of them are composed of several colors, and can be decomposed into their original elements by a prism. As without prismatic decomposition, we are unable merely from the color of an object to say positively which colors are absorbed and which reflected. So, it is equally impossible for us to decide from the color of a flame what the composition of its light may be without investigation. The light of the sun, the limelight, the magnesium light, the light of coal gas, petroleum, and oil all appear to us more or less white, and yet the spectra of the various lights differ considerably. It is true they all contain the whole range of the colors of the spectrum from red to violet, but each color is present in very different proportions. The light from gas, oil, and candles has less blue than that of the sun and the limelight, and very much less violet. A blue material will therefore reflect less blue by lamp, gas, or candlelight than by daylight. The color will not only be flat and dull, but will have a touch of green in it on account of the preponderance of yellow light. Blue and violet especially receive a green tinge by candlelight, in which these colors appear much duller than in daylight, and indeed sometimes according to the nature of the coloring matter employed. This tint is so decided that in artificial light, many kinds of green cannot be distinguished from blue. Chapter 35. Absorption of light by solid bodies. By the term absorption, we have already designated that action by which light in its passage through certain media, or by its reflection from the surface of bodies, is weakened, partially retained, or entirely stopped. We found that those substances called black absorbed rays of every color and reflected no light from their surfaces, and that most substances absorbed with great avidity rays of certain colors, while they were insensitive to others. The cause of this absorption is probably due to the vibrations of the ether being communicated to the ponderable molecular particles of the substance. Similar phenomena are noticed when light is transmitted through colored glass. When all of the objects in a landscape appear red through a red glass, it is because the glass allows only the red rays to pass through and absorbs every other colored ray. Such a glass is transparent only to red light and is opaque to every other color. But it is rarely the case that colored glass is transparent for one color only. Most kinds of glass absorb rays of certain colors and allow the others to pass through in very different proportions. The naked eye is unable to decide which of the colored rays are transmitted through a colored glass. This can only be accurately determined by analyzing the transmitted light by a spectroscope or simple prism. If we examine by a spectroscope the transmitted light of the colored glass that we before made use of Section 17, for obtaining red, green, and blue light, it will at once be seen that the ruby red glass transmits some orange, and even some yellow rays, as well as the red, but that it entirely absorbs the green, blue, and violet rays. The cobalt blue glass transmits some violet and green rays, besides the blue, but absorbs all the red rays. If both glasses be laid one over the other and a gas flame looked at through them, it seems as if scarcely a single ray was transmitted, the red glass absorbing the green, blue, and violet rays, and the blue glass absorbing the red rays. There pass through only traces of such light as has not been entirely absorbed, and this causes the gas flame to appear a dull yellow. A combination of several glasses, or indeed any single glass which absorbs all the colored rays composing white light, is opaque. That is to say, black, glass of perfect transparency, absorbing absolutely none of the transmitted light, does not exist. Chapter 36. Absorption of light by liquids. The absorptive power of colored liquids is in general much more decided and marked than that of colored glass. No coloring matter has yet been found which will absorb or transmit only one kind of colored rays. The colors of liquids, therefore, as seen by white light, are mixed colors, and their absorption varies exceedingly, according to the refrangibility of the light which falls upon them and the degree of concentration possessed by the solution. Sorby, Schellen, Hoppe, and Valentin, besides Gladstone and Huggins, have delineated a great number of well-known coloring matters and other liquids in the course of their investigations, and have ascertained to what extent their various degrees of concentration affect the individual parts of the continuous spectrum. If these absorption phenomena are to be exhibited before a large audience by the use of the electric or Drummond's light, it is desirable to take those colored liquids which show their absorption in a very characteristic manner, as for instance, a solution in ether of chlorophyll, the green coloring matter of leaves, a solution in water of the coloring matter of human blood, or a thin layer of potassium permanganate solution. If a continuous spectrum of white light about 6 feet long be projected in the usual way, and a glass vessel, figure 70, composed of flat plates containing the chlorophyll solution introduced into the path of the rays, the spectrum on the screen will be seen immediately to change. Dark bands, figure 71, number 2, frontispiece number 10, appear in the red as well as in the yellow, green, and violet portions, and the blue shades give place to a faint red hue. The green chlorophyll solution does not therefore absorb the whole of the red and yellow rays, but only those which possess a peculiar refrangibility or wavelength. It exerts the same influence on most of the blue and violet rays, while it transmits unchanged all the other colors of white light. If a greatly diluted solution of fresh arterial blood be substituted for the leaf green, the red in the spectrum will be intensified, while the blue and the violet will be nearly extinguished. Figure 71, number 3, show in the yellow commencement of the green 2 dark blood bands with a faint green stripe interposed. These phenomena appear in a much more striking manner if they are observed through a spectroscope instead of being projected on a screen. The colored liquid is then placed immediately in front of the slit, and the spectra viewed directly by the eye. It is needful for this purpose to have small glass troughs with parallel sides, similar to the one drawn in figure 70, but Stokes recommends carefully selected test glasses, any of which may be filled with the requisite liquid and placed, as shown in porting ring fastened to the end of the spectroscope. If the instrument, with the slit not too contracted, be directed towards a luminous cloud, or when this is not available, towards a bright light placed immediately in front, there will appear a brilliant spectrum crossed by dark bands produced by the absorption of the liquid. In many cases, small changes produced in these coloring matters by dilution, by chemical action, or by the increase or diminution of the thickness of the stratum of liquid, are accompanied by changes in the absorption bands, so that a conclusion may be formed from the position, width, and intensity of these dark bands as to the nature of the coloring matter and the circumstances by which it has suffered alteration. The 2 dark blood bands are seen in the yellow-green of a spectrum formed by either daylight or lamplight from water infused with but a trace of blood, and which exhibits to the naked eye scarcely a perceptible tinge of yellow. On this account, spectrum analysis has been called into the service of physiology and pathology, and is fitted to render valuable aid in medico-legal investigations, since it is not improbable that the spectroscope, when in connection with the microscope, will be able to detect the presence of blood or poison in many cases where the microscope alone can furnish no results, or only those of an untrustworthy character. Chapter 37. The Sorby-Browning microspectroscope. The object of this instrument is to facilitate the accurate observation of the absorptive phenomena of the smallest solid and liquid bodies, such as are prepared for microscopic examination, a corpuscle of blood, for instance, Sorby, with the assistance of Browning, has so arranged the spectroscopic part of the instrument that it can be applied to any microscope by fixing it in the place of the ordinary eyepiece so that the spectroscopic investigation of an object can be pursued without any change in the manner of using the instrument. In a complete instrument, a contrivance is attached to the side by means of which the substances to be investigated may be compared with the spectra of known substances. This apparatus consists of a small stage, a prism for comparison, section 38, and a movable scale for measuring accurately the places of the absorption bands. Instrument as fitted to slide into the upper tube of the microscope and plates of the eyepiece. Figure gives a section showing the internal construction, and figure 75 gives a section through the plane of the two screws C and H, exhibiting the slit with its contrivances for adjustment and the prism for commencement. The tube A encloses a second tube carrying a direct vision system of 5 prisms R, and an achromatic lens, figure 74. By means of a milled head B with screw motion, this inner tube can be moved up and down, so that the slit situated in the plane of the screws, C and H, may be in the focus of the lens. Consequently, the rays from the slit, after passing through the lens, fall parallel onto the prisms. DDL is the stage on which the objects for comparison, liquids between plates of glass or in small tubes, are secured within notched edges by means of metal springs, which hold the small glasses in such a position that the light falling on them from the side, after its passage through the liquid, reaches a square opening in the middle of the stage, whence, as figure 74 shows, it passes through a side opening 0 into the inside of the principal tube, and falls upon the reflecting prism R, which acts as a prism for comparison. When the apparatus for comparison is not required, the square opening in the stage DD is closed by a sliding plate by means of the screw E, so that the side light may be shut out of the instrument. Slip between the screws C and H. The piece N is fixed, while M is movable by means of the screw H, and an opposing steel spring which serves to widen or narrow the slit. Close over the slit is a covering plate, which is moved backwards and forwards by the screw C and a spring acting against it, thus enabling the slit to be lengthened or shortened. The reflecting prism R covers a part of the slit. If this slit be open, and the light from the object for comparison fall from the side upon the prism R, it will be reflected back and be thrown upon the system of prisms C, together with the light coming through the open part of the slit from below, figure 74. In this way, 2 spectra are received in juxtaposition, one produced by the light passing through the tube G, the other by the light which has been transmitted through the known liquid upon the stage D. In order to use the microspectroscope, the tube A with the prisms must be removed and the tube G inserted into the eyepiece tube, so that the slit at the eye end shall be parallel to the inner slit. The object glass required is then screwed into the lower part of the microscope. The object, the spectrum of which is to be investigated laid upon the stage, and illuminated according as it is transparent or opaque with a mirror from below, or by means of an achromatic condenser from above, and the focus adjusted in the same manner as for an ordinary microscopic investigation, so that the enlarged image may be distinctly seen. For this purpose, it is requisite that the slit, by means of the screw H, should be opened wide. The tube A, with the compound prism, is then replaced, its position regulated with regard to the slit by the screw B, and the width of the slit adjusted until a well-defined spectrum is obtained. As each portion of the spectrum possesses a refrangibility peculiar to itself, the prisms must, for the delicate absorption lines, be specially adjusted for each dark line. It need scarcely be remarked that in these investigations, the lowest possible powers are employed. When the substance to be investigated is to be compared with the spectrum of a known substance, the stage D is employed in the manner described. If it be used in daylight, the tube of the microscope must be directed to a bright part of the sky, figure 73. For a better illumination of the liquids on the stage DDD, especially by lamplight, the mirror eye is employed, and is so supported as to allow of its being placed in any position with respect to the opening in the stage. For the accurate determination of the position of the absorption lines, the upper cover of the tube A is removed and replaced by another, which, as represented in Figure 76, is provided with a lateral tube AAA. In this tube, the lensing can be adjusted by means of the screw B, while in front is a contrivance by which an opaque glass plate D, on which a fine transparent line or cross has been photographed, may be moved backwards and forwards by the micrometer screw M, compare Figure 51, and the amount of motion measured. In front of the opening of the tube, is placed a movable mirrors, which reflects the light it receives, whether daylight or lamplight, onto the glass plate D. By turning the micrometer screw M, the light transmitted through the glass plate is thrown into the tube AA in the form of a bright line, and the lens pound adjusted to such a position as to direct the image of this line upon the upper surface of the range of prism C, presenting an angle of 450 whence it is reflected in the direction of the principal tube and reaches the eye at the same time as the spectrum. A bright line or cross is thus seen upon the spectrum, and it is not only easy, by turning the micrometer screw M, to place the bright line precisely upon any absorption line, but also to measure accurately the relative distances between any dark lines in the spectrum by means of the divisions of the micrometer. In order, however, that the results given by various instruments may be compared, these divisions must not be arbitrary. It has already been mentioned, p. 87, and will be more fully entered into in Part 3, that the solar spectrum, and consequently the spectrum of daylight, is not continuous, but is everywhere crossed by numerous dark lines of varying intensity. These dark lines always occupy the same place in the scale of color in the spectrum. That is to say, each line is produced by the absorption of one and the same color, or by light of the same refrangibility. Whatever may be the composition or angle of the prism, it is most advantageous to select the darkest lines in the solar spectrum to form a scale for dividing the screwhead M of the microspectroscope. For this purpose, Browning divides the screwhead M into 100 equal parts, and determines the divisions of the scale for every instrument by a previous trial in which bright daylight is admitted from below through the slit and the tube G, Figure 72. And these divisions are successively marked off by the indicator on the screwhead whenever the bright line of light, Figure 76, is coincident with the individual dark lines of the solar spectrum. The dark lines are then drawn in accordance with these numbers upon a spectrum about 5 inches long, which is divided into an arbitrary number of equal divisions as represented in the upper half of Figure 77. By means of such a spectrum, the position of the absorption bands of any liquid may be determined without difficulty, care only being taken that artificial light be employed for the formation of the spectrum. Since daylight always produces the dark lines of the solar spectrum, and these might easily be confused with the absorption lines. In fact, it is only necessary when dark bands are observed in the spectrum of a substance to bring the line of light in the micrometer upon the spectrum, Figure 76, and place it, by means of the screw M, in coincidence with the absorption lines to be measured, and then read off the number upon the divided screw head. The numbers read off for the various lines need only be compared with the divisions of the scale of the normal spectrum, in order to determine at once the position of these lines in the spectrum for all similar investigations. Should a more complete representation of the absorption spectrum be required, it is only necessary, as shown in the lower half of Figure 77, to draw the lines according to the numbers read off on the micrometer screwhead upon a spectrum furnished with the scale of the normal spectrum. The bright line seen at the number 96 in this lower spectrum ought to indicate that an absorption line was seen at this spot in the instrument. If, instead of the line of light, a bright cross be used, the point formed by the intersection of the lines is placed in the middle of the absorption line, or if it be a band upon each edge in succession. Those who wish to enter more minutely into investigations of this kind will do well to begin with BI absorption bands of human blood, various solutions of blood with madder aniline red, fresh solution of permanganate of potash, or with other similar substances of highly absorptive power. In Figure 78 are shown the absorption bands of human blood as given by Stokes. It will be seen how greatly they vary in the same substance AC, according as it is subjected to changes or mixed with other bodies. All four spectra are the absorption spectra of human blood. Number 1 is that of fresh scarlet blood. Number 2, that of deoxidized blood, chlorine. By the action of an acid on blood, the chlorine is converted into hematin, which gives a spectrum showing an entirely different set of bands, and hematin can again be oxidized and reduced until it exhibits the dark bands shown in nocispheron. While Hopseler and Valentine are already actively engaged with the absorption spectra of those substances which play an important part in physiology and pathology, Sorby has devoted himself to the investigation of articles of commerce, such as dyes and wine, to ascertain its age, as well as to detect the adulteration in food, such as beer and wine, mustard, cheese, butter, etc. Spectrum analysis has thus opened a wide field of investigation to the physiologist, the physician, the botanist, the zoologist, the chemist, and the technologist. And the labors undertaken in these various departments of science have already yielded valuable results. Chapter 38. Absorption of light by gases, while colorless gases only weaken the intensity of the light they transmit, and exert no selective absorptive power upon any particular rays, and while, on the contrary, colored solid and liquid bodies wholly absorb certain rays, and entirely transmit others, thus producing wide absorption bands that extend sometimes over whole groups of colors in the continuous spectrum, colored gases differing from both exhibit only narrow dark bands which, like black lines, traverse not unfrequently every color in the continuous spectrum. For the exhibition of these absorption phenomena, a glass globe, Figure 79, is employed, smoothly polished inside and capable of being closed at both ends by pieces of plate glass. The vapors for examination are introduced into the globe by a side opening. But if it be desirable that they should be formed during the investigation, the substances needed for their development can be placed in the vessel by removing the cover and vaporized by a careful application of heat. The globe must be placed immediately before the prism or close in front of the slit of the spectroscope, and in such a position in the path of the rays that they may pass through the inside of the sphere perpendicularly to the glass plates covering it, to exhibit the absorptive properties of nitrous acid gas on a large scale. The electric lamp or Drummond's light must be employed, and the continuous spectrum of white light thrown upon the screen, in the manner described in section 19, figure 34. If the globe filled with the red vapor of nitrous acid be placed in front of the prism in the position already described, the spectrum will appear crossed by a row of dark bands, the violet end having entirely disappeared. By increasing the heat of the vapor, these bands gradually become stronger, while new dark bands successively appear, until at last, when the temperature has reached a certain limit, all the colored portions of the spectrum are absorbed, and not a ray of the electric light is able any longer to penetrate the vapor. Brewster carried the process so far by a constant increase of temperature as to render the gas entirely opaque even to the power of the sun's rays. The absorption spectrum of this gas is shown in Figure 71, frontispiece number 9. If some pieces of iodine be placed in the globe and heated, a violet vapor is produced, through which the electric light may be made to pass. The phenomena which are then seen differ greatly from those before exhibited. By slightly widening the slit, a large piece of the spectrum, from the beginning of the yellow to the blue, appears to be cut out. And if the slit be contracted to obtain a purer spectrum, this broad dark belt resolves itself into numerous fine dark lines, which are seen to cross the whole of the spectrum from red to the beginning of blue. If the absorption spectrum of the vapor of iodine be examined in a test tube glass by means of a spectroscope, the whole of the orange and yellow will be seen crossed by a great number of fine black lines, which become so numerous in the green that they can scarcely be separated one from the other, and appear to form a shaded band, Figure 71, number 5. With instruments of high magnifying power, these dark bands are resolved into very fine lines, increasing in number and intensity towards the middle and darkest portions of the bands. Other colored gases yield similar absorption spectra, particularly the vapors of bromine, hydrochloric acid, perchloride of manganese, also according to Morin of chlorine, etc. While, on the contrary, there are other vapors, such as those of sulfur and selenium, which, although colored, do not occasion any absorption bands in the spectrum. Aqueous vapor also exercises an absorptive action upon light, and its absorption lines are very noticeable in the spectrum of the sun and that of diffuse daylight. On account of the connection of these lines with the spectrum of the heavenly bodies, the consideration of the details of their appearance must be left till we come to the discussion of the solar spectrum in Part 22. Chapter 39, Relation between the emission and absorption of light, when it is remembered that solid bodies in a state of incandescence emit a much greater body of light than gases emit in a similar condition, and that they are able to absorb a much greater quantity of the light falling on them, in certain circumstances even the whole of it, through the transfer of the ether vibrations to their ponderable atoms, when, further, it is remembered that just those substances that give out heat with the greatest facility, and in the fullest quantity, are also the most capable of receiving heat from without or absorbing it. The thought is suggested that there must be an intimate connection, a certain reciprocity between the power of a body to emit light, emission, and to absorb it, absorption. That the temperature of the substance has an influence on this relation between its emissive and absorptive powers is proved by the phenomena of the gas spectra of the first, second, and third order, section 31, as well as by the variety of absorption spectra exhibited at different temperatures by the same substance. A century ago, the eminent mathematician and physicist Euler, in his Theoria Lucis et Calores, enunciated the principle that every substance absorbs light of such a wavelength as coincides with the vibrations of its smallest part. Foucault mentioned in his work on the spectrum of the electric light, published in 1849, that owing to the impurity of the carbon points, the intense yellow sodium line appeared, and was changed into a black line when sunlight was transmitted through the electric arc. Ångström gave expression as early as the year 1853 to the general law that a gas, when luminous, emits rays of light of the same ref tangibility as those which it has power to absorb. Or, in other words, that the rays which a substance absorbs are precisely those which it emits when made self-luminous. But all these facts remained isolated, and there was yet wanting the comprehensive grasp of a general physical law under which the individual phenomena could be arranged. It was reserved to Kirchhoff to discover this law and to establish triumphantly its truth, not only by mathematical proof, but also in many striking instances by experiment. In the year 860, he published his memoir on the relation between the emissive and absorptive powers of bodies for heat, as well as for light, in which occurs the celebrated sentence: "The relation between the power of emission and the power of absorption of one and the same class of rays is the same for all bodies at the same temperature, which will ever be distinguished as announcing one of the most important laws of nature, and which, on account of its extensive influence and universal application, will render immortal the name of its illustrious discoverer." Chapter 40, Reversal of the spectra of gases from Kirchhoff's law. It follows as a necessary consequence that gases and vapors in transmitting light absorb or impair precisely those rays, colors, which they themselves emit when rendered luminous, while they remain perfectly of refrangibility of the double line. Hence the presence of sodium in a source of light must tend to originate light of that quality. On the other hand, vapor of sodium in an atmosphere around a source must have a great tendency to retain on itself, that is, to absorb and to have its temperature raised by light from the source of the precise quality in question. In the atmosphere around the sun, therefore, there must be present vapor of sodium, which, according to mechanical explanation thus suggested, being particularly opaque for light of that quality, prevents such of it as is emitted from the sun from penetrating to any considerable distance through the surrounding atmosphere. The test of this theory must be had in ascertaining whether or not vapor of sodium has the special absorbing power anticipated. In the same connection must also be considered the experiments on the properties of radiant light communicated in by Professor Balfour 206 spectrum analysis, transparent to all other colored rays. Luminous sodium vapor, for example, gives under ordinary circumstances a spectrum of one bright yellow double line. It emits, therefore, this yellow light only. If the white light of the sun, the electric arc, or the oxyhydrogen lamp be allowed to pass through the vapor of sodium, the vapor will abstract or extinguish from the white light just those yellow rays which it emitted when in a luminous state. While the greater part of these yellow rays are absorbed by the sodium vapor, all reversal of the sodium line seen with the spectroscope. The other rays, the red, orange, green, blue, and violet, pass through unimpaired. The mode in which Kirchhoff conducted his experiments, which admit of certain and easy repetition by means of a direct vision spectroscope, is shown in Figure 80, where the apparatus is arranged in the same way as for the exhibition of the absorption spectra. L as an oil lamp, the white light from which is decomposed into a continuous spectrum of every shade of color by the prism of the spectroscope SP 118. After the eyepiece of the telescope and the slit have been so adjusted as to exhibit a distinct spectrum, there is placed close in front of the slit 5 a glass tube end, from which the oxygen of the air has been expelled by the introduction of hydrogen gas, and in which are laid some pieces of metallic sodium. The glass tube is heated by means of the spirit lamp or gas flame G, and part of the sodium is converted into vapor. A dark line soon makes its appearance in the bright yellow of the continuous spectrum of the oil lamp, precisely in the place where the sodium vapor, when rendered luminous by heat, shows its yellow line. For proof of this, it is only necessary to replace the sodium tube, and by a spirit flame, in the wick of which some common salt, chloride of sodium, has been rubbed, and to screen the light of the lamp, the luminous sodium vapor produces the yellow line precisely in the same place in which the yellow light was before absorbed from the continuous spectrum and the dark line formed. The optician lad furnishes strong glass tubes half an inch in width, closed at both ends, and filled with hydrogen gas and a small quantity of sodium. On being slowly and gradually heated, the sodium becomes vaporized. If such a tube be held vertically close in front of the slit 5 and the white light of a lamp, or what is preferable, the light from incandescent lime, be allowed to pass through the tube containing sodium vapor before 2K entering the slits up, a dark line is visible precisely in the place of the bright sodium line. By the use of a spectroscope of strong dispersive power, the bright sodium line does not appear as a single but as a double line. Accordingly, in such an instrument, the dark absorption line of sodium vapor appears double, and both these dark lines occur precisely in the place where the two bright sodium lines are found when the light from sodium alone falls into in the same way by employing the vapors of lithium, potassium, strontium, and barium. Kirchhoff and Bunsen extinguished from a continuous spectrum precisely the same bright colors which these vapors emit when luminous. Luminous lithium vapor, frontispiece number 3, gives a spectrum of one intense red line and a fainter orange one. Lithium vapor absorbs also just those same colors from white light sent through it. If Kirchhoff's experiment be repeated with lithium in the same manner, Figure 80, as already described with sodium, two unequally dark lines will appear in the continuous spectrum of the lamplight, precisely in the same places where the luminous lithium vapor showed the two bright lines. The important result of these investigations is therefore that the characteristic bright lines of sodium, lithium, etc., are changed into dark lines when the intense white light of incandescent solid or liquid bodies passes through the vapor of these metals. The spectrum of luminous sodium vapor is a bright yellow double line, the rest of the field in the spectroscope remaining dark. The spectrum of an incandescent solid or liquid body, after it has passed through sodium vapor at a lower temperature than itself, occupies, on the contrary, the whole field with its brilliant colors, excepting only that one place in which the dark sodium line is found. As therefore the bright lines of gas spectra are converted in these experiments into dark lines, while the dark parts of the spectrum are changed into brilliant colors by the continuous spectrum of the white light, the entire gas spectrum seems to be reversed in respect of its illumination. For this reason, the phenomenon has been called, after Kirchhoff, the reversal of the spectrum. It has been fully proved by Kirchhoff that the difference between the temperature of the incandescent solid or liquid body, giving the continuous spectrum, and that of the absorptive vapor through which its white light passes, exercises a great influence upon the reversal of the spectrum, and that the whole phenomenon rests upon the relation existing between the emissive and absorptive powers of the vapor, which relation is determined by the difference of temperature. The reversal experiments, therefore, succeed only when there is a great difference of temperature between the incandescent solid body and the absorptive vapor, and they will succeed all the more certainly the higher the temperature is of the incandescent body, and the lower that of the reversing vapor. The light of the sun, the electric arc, Drummond's limelight, or a glowing platinum wire may be employed in place of the lamp, figure 80. If instead of the glass tube filled with hydrogen and sodium, etc., free sodium vapor be employed, such as can be obtained by heating metallic sodium in a flame, this flame must not be of a high temperature. The temperature of the Bunsen burner, or even of a spirit lamp, is too great as opposed to the heat of the oxyhydrogen limelight. For this purpose, the moderately hot flame produced by spirits of wine, diluted with as much water as it will bear, is sufficient, when with the addition of a little common salt, the sodium line in a good spectroscope, with a suitable opening of the slit, will appear black upon the colored ground of the continuous spectrum of the limelight. If the white light of the electric arc, with its far greater heat, be used to form the continuous spectrum, the reversal of the sodium and lithium lines may be produced by volatilizing these metals in the flame of the Bunsen burner. For the exhibition of the reversal of the sodium line on a screen, the glass tube above mentioned containing hydrogen gas and sodium is not well suited, as the sodium vapor is not dense enough and soon stains the sides of the glass. But if the electric arc be used for the white light, the sodium vapor may be produced by means of a gas flame. For this purpose, the carbon points should be previously moistened with a weak solution of salt and allowed to dry again. If a continuous spectrum, some 3 feet long, be formed by the electric lamp and prism in the usual way, the bright sodium line is seen passing through the yellow, the position of which may be noted by making a mark M at the side. The small amount of sodium adhering to the carbon points soon evaporates in the heat of the electric light, and the yellow line is extinguished. The gas burner G, figure 81, is now reversal of the sodium line, projected on a screen, placed before the slit of the electric lamp E, so that the rays of the incandescent carbon issuing from it must pass through the flame G before adding the sodium to this gas flame. A perforated screen of pasteboard is placed in front of the lens L, in order that the large screen on which the spectrum is formed shall be protected from the intense yellow light of the burning sodium. None of these preparations exert the slightest influence upon the continuous spectrum Rx on the screen. A piece of sodium the size of a pea is placed in a platinum spoon and brought into the gas flame. The sodium ignites and forms a dense cloud of vapor through which the rays of the electric light must pass. On the screen is seen a striped D of intense blackness precisely in the place marked M where the bright sodium line before appeared. The sodium vapor has, partially at least, absorbed or extinguished from the white light of the incandescent carbon the yellow light of the same degree of refrangibility as the sodium vapor emitted. If the sodium be withdrawn from the gas flame, the black line immediately disappears from the screen. If it be reintroduced, the black line again appears precisely in the same place. The sodium vapor therefore absorbs the same light, that is to say, the same colored rays, which it emits in a luminous state. The instructive experiment of the reversal of the sodium line may be made in another way, which is not less fitted than the preceding one to give a clear illustration of certain phenomena of the solar spectrum. For this purpose, the lower pole of the electric lamp is replaced by a cylinder of carbon half an inch thick, the upper surface of which, slightly hollowed out, figure 82, contains a piece of sodium the size of a pea. The Bunsen burner G and the pasteboard screen as are removed, while the lens L, the prism P, and the large screen remain undisturbed. To prevent the intense incandescence of the carbon and the consequent appearance of the white electric light, the two poles are separated after the first contact somewhat wider than is usual. Rather more than of an inch, only a faint continuous spectrum is formed, and the lamp emits only the intensely yellow light of the burning sodium. As soon as the electric current passes, the sodium begins to glow strongly, and a single band of brilliant yellow, about 2 inches wide, is seen upon the screen, which is the spectrum of the luminous sodium vapor. But in a few seconds, a sharply defined deep black line, about an inch wide, appears in the middle of this yellow band, while the remaining portion of the color fades away. The bright yellow sodium line has become changed into a dark line, which continues as long as the combustion of the sodium lasts. In this case, the reversal is easily explained in the following manner. The sodium becomes first intensely heated, and its vapor emits its yellow light. Immediately afterwards, a great portion of the sodium is converted into vapor by the great heat of the electric arc, and envelopes the small luminous portion about the sodium in a dense cloud of non-luminous sodium vapor. The yellow light of the small luminous portion of the sodium vapor must pass through this large cloud of sodium vapor of a lower temperature and is absorbed by it before reaching the slit of the lamp. We may repeat the conclusive inference. The vapor of sodium absorbs precisely the same light that luminous sodium vapor emits. Without employing either the electric or Drummond's light, this phenomenon may be exhibited by the following simple but ingenious contrivance of Bunsen's. It consists, figure 83, of two bottles, AB, containing zinc and common salt, and both nearly filled with a very diluted solution of hydrochloric acid. Each bottle is closed with an India rubber stopper pierced with two holes, one of which in each stopper serves for a gas burner of different construction. In one hole of the lamp, A is a bent glass tube B for the introduction of coal gas from a common gas pipe. In the other opening is the tube C, which is narrowed at the top, serving for the escape of the gas. The other lamp B is fitted up in the same manner as A, with the exception that the escape tube C is bent and terminates in a much smaller opening, Bunsen's apparatus for the absorption of the light of sodium. Over each of these glass tubes, C and C is a burner constructed of tin plate, which can be moved up and down. The burner D of the lamp A is cylindrical below, and spreads out above in the shape of a fan, so as to form a narrow and somewhat arched slit of about an inch in length. The burner E of the lamp B is cylindrical throughout, and is covered with a conical-shaped chimney A, which slides up and down the tube B as the top of the chimney has an opening only an inch in diameter, which can be still further diminished by the addition of another cover with a yet smaller aperture. The gas, when ignited, forms a conical-shaped pointed flame jet, which can be reduced by means of the stopcock of the gas tube to about an inch in length. The flame G of the lamp A, on the contrary, is very large and broad, owing to the size of the emission tube C and the compression of the wide burner DF, and presents a luminous surface of some extent. The bottles are used for the purpose of mixing a little common salt, chloride of sodium, with the hydrogen gas formed by the action of the diluted hydrochloric acid on the zinc. The hydrogen gas, as it rises, mixes with the coal gas, and carries the chloride of sodium into both flames, producing in this way the brilliant yellow light of sodium vapor. Both lamps are placed very near to each other, so near indeed that, as shown in figure 84, the flame G of the lamp serves as a background to the lamp B. In this position, the small flame D, notwithstanding the brilliant light of the flame G immediately behind it, appears quite dark and smoky, indeed almost black, when all conditions are favorable. The burner and chimney rightly placed, and the supply of gas suitably adjusted, the heat flame G emits with intense brightness the light of sodium. The small sodium flame D in front of it absorbs these rays as they pass through it, and as it is much less luminous than the flame G, It appears dark by contrast with the bright background. De Zaga of Heidelberg, the constructor of this apparatus, has lately much simplified it by uniting the two burners and fixing the common supply tube by means of a single stopper onto a larger bottle. The experiment of reversal may be easily shown by the use of a spectroscope in the following manner. The instrument is so directed onto a spirit lamp that when a grain of salt is dropped into the flame, a well-defined spectrum consisting of the well-known yellow sodium line is formed. The flame is then brought close in front of the slit, and a piece of newly cut metallic sodium, the size of a pea, is placed over the flame in a wire netting. The flame cannot pass the wire, yet the sodium begins at once to burn, and the brilliant yellow sodium line is seen in the spectroscope. Very soon, however, a black line appears in the same place, very sharply defined against the bright background. Here also, the brilliant luminous vapor of the burning sodium is enveloped in a dense cloud of feebly luminous sodium vapor, which completely absorbs the greater part of the yellow sodium light. We can now readily predict what appearance will be presented in the spectroscope if the light of an incandescent solid or liquid body, before entering the slit of the instrument, passed through a less highly heated atmosphere of any kind of vapor, such as that of sodium, lithium, iron, etc. The incandescent body would have produced a continuous spectrum if its light had sustained no change on the way, but in the vaporous atmosphere through which its rays must pass. Each vapor absorbs just those rays which it would have emitted if luminous, thereby extinguishing these particular colors, and substituting for them dark bands in those places of the continuous spectrum where it would have produced bright lines. The spectroscope shows therefore a continuous spectrum extending through the whole range of colors from red to violet, but intersected by dark lines. The sodium line, the two lithium lines, the numerous iron lines, etc., appear on the colored ground of the continuous spectrum as so many dark lines. Spectra of this kind are evidently absorption spectra. They are also called reversed or compound spectra. If a complete coincidence can be established in such a spectrum by means of either a prism of comparison, section 2.8, or a scale section 25, between the characteristic bright lines of the gas spectrum of a certain substance with the same number of dark lines, the conclusion may be admitted that in the absorptive atmosphere which has produced the dark lines, the same substance is contained in a condition of vapor. The wide influence which this result of Kirchhoff's discovery has on the investigation of the physical constitution of the heavenly bodies is shown by the consideration that as the various substances of this earth can be recognized by their simple gas spectra, so the reversed gas spectra afford the key to the recognition of the matter of which the heavenly bodies are composed. And, indeed, so important is the part which they play in the analysis of the stellar world, that we may well be excused if we linger a while longer on this subject. The question will occur to everyone on reflection, why, if the weak sodium flame absorbed the yellow rays from the intense white light that passes through it, do not the yellow ray of the flame itself again replace the yellow sodium light? A somewhat closer investigation of all the influences at work will not only give materials for fully answering this inquiry, but afford the means also of clearly explaining the cause and true nature of the dark lights. Let I designate the intensity of the white light of the incandescent solid or liquid body, taking the electric light as an example, that of the absorptive flame, which for the sake of simplicity we will suppose to be a sodium flame, and the proportion between the absorptive and the emissive powers of this flame, that is to say, is lost by absorption from the total intensity. If then the white light I pass through the sodium flame, and suffer a loss in intensity by absorption of heat, there will be in the place of the spectrum where the sodium line appears, which we will call D. An amount of light equal to L, the amount of I absorption, diminishes the intensity of the spectrum at the spot D, but the intensity of the sodium flame will to a greater or less degree supply the deficiency. If the amount of the absorption were precisely equal to the intensity I, the intensity of the spectrum at the spot D would be just as great as that of the neighboring parts, and there would therefore be no interruption of the spectrum. There would neither be a dark line nor a bright line visible. If the intensity I of the sodium flame be greater than the absorption, the brightness of the spot D in the spectrum would be greater on either side of it, and there would appear at this place a bright yellow sodium line, although the white light had passed through the absorptive flame. The reverse will be the case if the intensity I of this flame be less than the whole absorption. The brightness of the spectrum at the spot D will then be less than that of the surrounding parts. In the last case, however, this want of light will appear as a shadow by contrast with the brightness of the neighboring places, and the usual bright yellow sodium line will seem to be a dark line. It will be seen further from this investigation that in the places where the dark absorption lines appear, there is by no means a total absence of light. Therefore, these lines should not be described as quite black, but in contrast with the surrounding brilliancy produced by the full undiminished light of the incandescent solid or liquid body, these lines appear quite black even when their brightness exceeds that of the absorbing vapor. The whole action of the reversal of a bright spectrum line into a dark one rests on the proportion between the absorptive power and the compensating emissive power in the absorbing vapor. The greater the absorptive power, and the less the emissive power further, the greater the light of the incandescent body, so much the darker will the reverse lines appear to be. The following table will serve to elucidate the foregoing remarks. By giving 4 examples for the sodium line, John O. The intensity of the white light is called the intensity of the sodium flame, is the absorptive power of the sodium vapor, is the intensity of the spectrum before. In J, behind the sodium line, is then. The sodium line appears therefore bright. It dark, darker, very dark. In the first case, the place D is E brighter than the surrounding parts of the spectrum. Therefore, it appears as a bright sodium line. In number 2, the brightness of the place D is only equal to 8 dB, while that of either side is 10. It is therefore not so bright at D as at the side of D, and in consequence D appears dark against the surrounding parts of the spectrum. In number 3, the contrast is still greater between the light at D51 and that at the side 100. Finally, in number 4, where the absorptive power of the flame is assumed to be the contrast between the strength of light, 126, is so great that the line seems almost black. The intensity with which the yellow line of sodium and the red line of lithium appear when these substances are heated in a Bunsen burner warrants the conclusion that these metals would also absorb with great power rays of the same refrangibility, and therefore the assumed absorptive power, given in the last example, is considerably below the truth. Chapter 41. The solar spectrum and the Fraunhofer lines, a most brilliant example of a reversed spectrum, that is to say, a continuous spectrum crossed by dark absorption lines, is afforded by the sun. If an ordinary spectroscope, armed with a telescope of low power, be directed to a bright sky with a rather wide opening of the slit, a magnificent continuous spectrum will be seen, exhibiting the most beautiful and brilliant colors without either bright or dark lines. But if the slit be narrowed so as to obtain the purest possible spectrum, section 21, and the focus of the telescope be very accurately adjusted, the spectrum, now much fainter, will be seen to be crossed by a number of dark lines and cloudy bands. If, by the use of several prisms, section 19, the spectrum be lengthened and a higher magnifying power employed, these thick lines and bands will become resolved into separate fine lines and groups of lines, which are so sharply defined and so characteristically grouped that by the help of a scale they are easily impressed upon the memory and distinguished one from another. As early as 1802, these dark lines in the solar spectrum had been observed and described by Wollaston. Later, in 1814, they were more carefully examined and mapped by Fraunhofer of Munich, and later still by Becquerel, Zantedeschi, Matthiessen, Brewster, Gladstone, and others, but their origin and nature remained a mystery, notwithstanding the acutest reasoning and most painstaking researches of many able physicists. Until Kirchhoff made his splendid discovery in 1859, Fraunhofer was able to distinguish with certainty about 600 lines. He found also that with the same prism and telescope, they always kept the same relative order and position, and were therefore peculiarly adapted to serve as marks for denoting the place of any single set of colored rays, and for determining the refrangibility of any particular color. To facilitate reference to any of the innumerable colors of the solar spectrum, frontispiece number 1-1, Fraunhofer, whose drawing is accurately represented in figure 85, selected out of the great number, he observed 8 characteristic lines situated in the most important places of the spectrum, which he designated by the letters A, B, C, D, E, F, G, H of these lines. A and B lie in the red, C in the red near the orange, D in the orange, forming a double line with a high power, E in the yellow, F on the borders of the green and blue, G in the dark blue or indigo, and H in the violet. Besides these lines, there is a noticeable group A of fine lines between A and B, and also a group B, consisting of 3 fine lines between E and F. It was remarked even by Fraunhofer that the position of the 2 dark lines in the solar spectrum, designated by him D, were coincident with the 2 bright lines shown by the light of a lamp, now known as the double sodium light. These dark lines of the solar spectrum have been called, after their discoverer, the Fraunhofer lines. After Fraunhofer, Zanedeschi, professor of physics in the University of Padua, devoted himself to the investigation of the dark lines in the solar spectrum, upon which work he had already entered. In the year 1846, he deviated from Fraunhofer's method of observation by introducing the prism between 2 condensing lenses. The slit was placed in the focus of one lens, while the other served to project the spectrum onto a screen. By this means he constructed an apparatus which in all essential points differed little from the spectroscope now in use. The important sphere destined to prismatic analysis did not escape the penetration of this physicist, since, in his work Research Exico Chimici Archeologiche sulla Luce, he thus expresses himself in speaking of the significance of the spectrum. 44. The solar spectrum is the most perfect photoscope that in the present state of science can be imagined. Light itself exhibits and registers with wonderful minuteness the changes occurring in the constitution of a luminous body, or in the medium through which the light passes. I therefore recommend to the scientific investigator a camera obscura specially adapted to these photoscopic observations. I am convinced that such investigations will prove of the highest value, not only in the study of light, but also in the departments of meteorology and ephenesia. 1846, T.P.G. Antonelli, Astronomy, Light, which in these days is commissioned to be the painter of nature, may also become its own delineator, since it is ever disclosing new wonders out of the mystery of its being, and revealing those constant changes which are taking place, not only in our planetary system, but throughout the whole universe. By a careful investigation of the spectra formed by prisms of different substances, it is found that the same colors do not occupy the same proportionate space in each spectrum. With a prism of flint glass, for instance, there is proportionately less red and more blue and violet than with a prism of crown glass. The greater the difference between the refractive powers of a substance for the red and the violet rays, the greater will be the distance over which the colors are spread. In other words, the greater will be the dispersive power. The length of the spectrum depends essentially upon this dispersion, and it is therefore not a matter of indifference whether a prism of flint glass, of crown glass, of water, of bisulfite of carbon be employed for producing the solar spectrum. Powers of the different substances, flint glass, crown glass, and water. The spectrum obtained by a flint glass prism is about twice the length of that given by a similar-sized crown glass prism, and nearly 3 times the length of that from a hollow glass prism of the same form filled with water. The spectrum produced by a prism of bisulfide of carbon is very much longer than that given by a flint glass prism, and this even is surpassed by one obtained from oil of cassia. As the length of the spectrum is increased, the separation between the Fraunhofer lines increases also, but by no means in equal proportions. If, for example, the spectrum of the flint glass prism were exactly twice the length of that of the crown glass prism, the distance between any 2 dark lines, solar spectrum with prisms of flint glass, crown glass, and water. F and B, for instance, will not be exactly twice as great in the one spectrum as in the other. In the water spectrum, FB equals FH. The crown glass spectrum is longer, but the various divisions formed by the Fraunhofer lines have not increased in equal proportions. In the water spectrum, FB equals FH, while in the crown glass spectrum, FB is somewhat smaller than FH. By this latter prism, therefore, the blue and violet end is rather further extended in comparison with the red and yellow end than by the water prism. This difference is still more obvious in comparing the two spectra of the water and the flint glass prisms with an equal deviation of the light corresponding to the line B. The difference in the proportion of FB to FH is smaller in the flint glass spectrum than in the water spectrum, and this difference is more apparent than in the crown glass spectrum. It would therefore be an error to take for granted, as some have done, that the distances between individual dark lines in the spectrum change in the same proportion as the entire length of the spectrum, even if the dispersive power of any substance be known for the outside rays. Or for the lines B and H, the amount of separation between the intervening lines of the spectrum cannot be deduced from this. The relative position of these lines must be specially ascertained for each refracting substance. An accurate knowledge of the peculiar conditions of the spectrum apparatus employed must therefore be acquired by every observer before he can venture to direct attention to the results of the observations made with it. He must become familiar with the precise places of all the chief lines and groups of lines seen in the solar spectrum, so that in the examination of any particular line, whether in the spectrum of a terrestrial substance or of a heavenly body, he may know at once, at least approximately, to which of the Fraunhofer lines it lies nearest. The instrument used by Kirchhoff in his investigations on the solar spectrum is represented in Figure 53, in connection with which it was stated that the amount of dispersion, or the length of the spectrum, increases with the number of prisms employed. By the use of such a powerful instrument, a number of dark lines that appear to be single in smaller spectroscopes become resolved into several individual lines. The D line, even with a moderate power, is separated into two fine lines, and shows besides a cloudy band of still further resolvability. It is self-evident that with a great dispersion of the light, by which the spectrum is greatly lengthened, the intensity of each group of colors will be considerably diminished. By the use of a sufficient number of prisms, the brilliant solar spectrum may be reduced almost to invisibility, and an excellent means is herewith provided, as will be seen later on, for reducing the excessive brilliancy of the solar light to the requisite amount when observing phenomena on the sun's limb. Chapter 42. Kirchhoff's scale of the solar spectrum to facilitate the observation and recognition of the numerous dark lines in the solar spectrum, and to determine accurately their position and relative distances one from another. The mapping of all the visible lines must be made according to a given scale, or else in accordance with a certain scale adopted once for all, and this scale taken as a basis for measuring or estimating the place of any particular line. Kirchhoff, with an e.g. expenditure of time and trouble truly admirable, was the first and to undertake these measures for certain portions of the spectrum. The instrument which he employed, consisting of 4 C prisms, has been already shown in Figure 53. From this drawing, it will be seen that he made use of a divided circle fixed to the head of the micrometer screw Crone R, by which the cross wires of the telescope B could be brought to coincide with each of the dark lines of the spectrum. The eyepiece was so placed that the threads of the cross wires formed angles of 450 with the dark lines. The point of intersection of the wires was, by means of the micrometer screw R, placed in succession over every one of these lines, and the division on the screw head, Figure 51, read off. An estimation of the degree of intensity and breadth of the lines was recorded at the same time. In tabulating these measures, Kirchhoff employed as a 3,400 to 3,500 J 3,600 bases, a scale divided into millimeters as starting point. Each millimeter corresponded to a division on the micrometer screw head. The drawings published by Kirchhoff embrace a portion of the spectrum extending from the line D to a little beyond F, and occupy a length of 4 feet, The remaining portions from A to D and from F to G have been observed and measured by Hoffman, a pupil of Kirchhoff S, with the same instrument and according to the same method as the first portion, and they occupy a similar length, so that the whole of the solar spectrum is exhibited in a very accurate drawing of about 8 feet in length. Scale, with the principal Fraunhofer lines, plates to cite, and 3 for permission to publish, which we are indebted to the kindness of Professor Kirchhoff, and to which we shall again refer in section 44, give the lines measured by Kirchhoff and Hoffman according to their width and intensity. These maps are about half the size of the original drawings. The principal Fraunhofer lines are numbered on this scale as follows. H 3371 IU33 4 1648 to 3H2 is according BSJ 1655 degrees to Kirchhoff I28 uncertain. D2 to F 10/6 Monatsbericht der Berliner Akademie der Wissenschaften ARB ZIL PBPLM Innermer NRFL 2L J BLED KIJA 29 under 111 LL MRTI as CHL DYY SBHRBS beat by. Chapter 43 Angstrom's Normal Solar Spectrum. It is a grave objection to the plan of mapping the solar spectrum according to the positions and relative distances of the dark lines, their indices of refraction P69. That the position of these lines is considerably affected by the number and composition of the prisms employed, and therefore the appearance of the spectrum and the drawings made from it vary according to the construction of the instrument. Fraunhofer was the first to undertake the determination of the wavelengths of those colors, the places of which are occupied by the principal dark lines of the solar spectrum. The subsequent labors of de Chiner, van der Willigen, Mascart, and Gibbs perfected this method and applied it to a greater number of lines, until at length the task was completed, with the aid of the best instruments, by Angstrom of Uppsala, whose work is characterized by such accuracy and completeness as to render it worthy of the highest admiration. To be regarded as a pattern to all investigators, the number of dark lines measured by Angstrom, with the aid and cooperation of Thalin, amount to I0, and the wavelengths of the colors corresponding to these lines are accurately determined in units of a 10/millionth of a millimeter. In the original maps, plates before VV fixed, the whole solar spectrum from A to H2 is represented in 11 parts, which when joined together form a length of about 11 feet. The upper edge of each part is provided with a scale divided into millimeters. Each millimeter of the scale represents a difference of wavelength equal to the 10/millionth of a millimeter, and as the 10th of a millimeter may be estimated with sufficient accuracy, the scale used by Angstrom will show, with approximate correctness, the wavelengths of lines to the 100 millionth of a millimeter. As the red rays ADC have a greater wavelength than the blue, G, or the violet, H, the numbers denoting the divisions of the scale decrease in succession from red to violet, in the reverse order of Kirchhoff's uniform scale. An eighth part of the original drawing, in which the line F is included, is given in figure 88. This line is situated close to the division of the scale marked 4,860, whence its distances of the Fraunhofer lines correspond precisely with the differences of wavelength of the light in the parts of the spectrum where they occur. Angstrom's normal solar spectrum portion with the line F may be concluded that the wavelength of the greenish-blue color corresponding to the F line amounts to 4,000. The lines to the right of F possessing a greater wavelength are towards the red, while those to the left are in the direction of the violet. The line marked M in the figure corresponds to a color possessing a wavelength of 49,565 of a millimeter, that marked M1 to a wavelength of 50,064 of a millimeter, that marked M2 to a wavelength of 48,481 of a millimeter, etc. Angstrom determined the wavelengths of the principal lines in the solar spectrum to be as follows. Chapter 44. Coincidence of the dark Fraunhofer lines with the bright spectrum lines of terrestrial elements, Kirchhoff's maps. From the coincidence previously observed by Fraunhofer of the two dark lines in the solar spec, Ure-Angstrom's and Thalen's maps of the solar spectrum from G to H, the brilliant line of Pli Aurora Borealistrum, designated by him D. With the two bright lines which Kirchhoff and Bunsen discovered to be those of sodium, Kirchhoff was induced to put this coincidence to the most direct test by obtaining a tolerably bright solar spectrum, and then bringing a sodium flame in front of the slit of the spectroscope. "I saw," says Kirchhoff, "the dark lines D change into bright ones. The flame of a Bunsen lamp showed the sodium lines on the solar spectrum with an unexpected brilliancy. In order to find out how far the intensity of the solar spectrum might be increased without impairing the distinctness of the sodium lines, I allowed direct sunlight to fall upon the slit through the sodium flame, and saw to my astonishment the dark lines D standing out with extraordinary clearness. I replaced the light of the sun by Drummond's light, the spectrum of which, like that of every other incandescent solid or liquid body, contains no dark lines. When this light was allowed to pass through a flame in which salt was burning, dark lines appeared in the spectrum in the position of the sodium lines. The same thing occurred when, instead of a cylinder of incandescent lime, a platinum wire was used, which, after being made to glow in a flame, was brought nearly to its melting point by the electric current. Kirchhoff could no longer doubt, from these observations, that the existence of the dark lines D in the solar spectrum was due to the presence of vapor of sodium in the sun, and that they must be produced in the sun by reversion, absorption, in a manner similar to that shown in the experiments already described with terrestrial sodium. After the existence of sodium had been thus suspected in the sun with so great an amount of probability, Kirchhoff commenced the arduous undertaking of comparing the spectra of a variety of terrestrial substances with the spectrum of the sun, to determine whether any of the spectrum lines of these substances, and if so, which of them, coincided with the Fraunhofer lines, that is to say, if they appeared in the spectroscope in the same place, and were of similar breadth and intensity. We have already made acquaintance with the method by which such a comparison may be made by means of two spectra in the same instrument, section 28. Kirchhoff allowed the light of the sun to fall directly into the spectroscope, and onto the first large prism through the lower half of the slit, while the upper half was covered by the small prism for comparison. The rays from an artificial source of light placed at the side were so reflected by the prism into the instrument that, while the solar spectrum with the Fraunhofer lines was seen in the upper half of the field of view in the inverting telescope, there appeared below, and in immediate contact with it, the spectrum of the artificial light. In this way, the position of the bright lines of this spectrum could be compared with great accuracy with that of the dark lines of the solar spectrum. The artificial light employed by Kirchhoff was almost exclusively that of the induction spark from a powerful Jlummkorff coil, with electrodes of small pieces of such metals as he wished to volatilize, in order to obtain their spectra. By the comparison of these spectra with the dark lines of the solar spectrum, Kirchhoff arrived at the coincidence of the Fraunhofer D lines with the lines of sodium. Surprising result that the bright lines of several metals were entirely coincident with the same number of lines in the solar spectrum. The coincidence of the two sodium lines D is shown in figure 89. The upper part represents that portion of the solar spectrum with the two dark D lines, which is situated in the yellow, between 110 1 millimeters of Kirchhoff's scale. The lower part shows the bright lines given by sodium vapor rendered luminous either by the electric spark or the flame of a lamp. And both pairs of lines occupy so precisely the same position in the spectrum that one forms the exact prolongation of the other. In a very perfect instrument, another fine line, corresponding to a bright line given by nickel, appears between the two dark lines. Two portions of the spectrum, the one situated in the yellow between 120 and 125 of Kirchhoff's scale, and the other in the green between 150 and 154, are represented in figure 90. The lower 13 bright lines, designated Fe, equals ferrum, iron, are lines in the spectrum of iron. They fall in exact accordance with an equal number of dark lines in the coincidence of the Fraunhofer lines with the lines of iron and calcium. Solar spectrum. The remaining 12 bright lines indicated by dots belong to the spectrum of calcium and are coincident with as many dark lines in the solar spectrum. Between these dark lines in Kirchhoff's drawing are several other lines, some of which coincide with the bright lines of terrestrial substances, while others are due to some other effects of absorption. Plates 2 and 3 contain all the dark lines measured by Kirchhoff in the spectrum of the Sun, and below the solar spectrum are marked in black the lines of those terrestrial elements with which he had compared them in the usual manner. These substances are designated by their chemical symbols. Thus, C equals ferrum, iron, Ca equals calcium, Pb equals plumbum, lead, Hg equals hydrogen, mercury. Na equals barium, Mg equals magnesium, Al equals barium, Mg equals magnesium, equals aurum, gold, H equals hydrogenium, hydrogen gas, etc. The horizontal lines by which the lower ends of the vertical spectrum lines grow up together indicate that all lines thus bracketed belong to the same substance, the chemical symbol of which is placed below. The wavelengths of the bright spectrum lines of terrestrial substances have in the same manner been determined by Ångström and Thalen, the latter of whom has devoted himself especially to this subject. The coincidence of these lines with the dark lines of the solar spectrum has been proved by these observers and recorded in their maps by inserting them beneath the solar spectrum, vide figure 88, plates 5 here. Vixt. Even in the portion of the spectrum published by Kirchhoff, there are some 60 bright lines of iron, all of which coincide with as many of the dark Fraunhofer lines. The continuation made by Hoffmann contains 13 additional very striking coincidences, and Ångström and Thalen, who volatilized iron, the electric arc, found a coincidence of more than 460 bright lines of figure 91. Iron, with an equal number of the Fraunhofer lines. The complete coincidence of so many bright lines in one and the same substance with the same number of dark lines of the solar spectrum shows conclusively that it cannot be the effect of chance. A glance at figure 9.1, in which the coincidence is shown of more than 60 of Kirchhoff's observed lines of iron, with as many dark lines in various parts of the solar spectrum between C and S, justifies the conclusion that those dark lines are to be ascribed to the absorptive effect of the vapor of iron present in the atmosphere of the Sun. The likelihood that such a coincidence of 60 lines is a mere chance bears a proportion to the supposition that these lines really make known the presence of iron in the Sun's atmosphere, according to the doctrine of probabilities of I to 260. Or in other words, in the ratio of 1 to 1,152,930,000. The most striking coincidences between the spectrum lines of terrestrial elements and the dark lines of the solar spectrum are shown in iron, sodium, potassium, calcium, magnesium, manganese, chromium. The spectrum lines of these substances not only agree exactly with the dark lines in position and breadth, but proclaim their relationship to them by a similar degree of intensity. The brighter, for instance, a spectrum line appears, so much the darker will its corresponding line be in the solar spectrum. A partial coincidence only of the bright and dark lines is shown in the spectra of the metals zinc, barium, copper, cobalt, and gold, where the brightest lines only correspond with the dark lines of the solar spectrum. Thalen has lately discovered that the greater number of the 170 bright lines given by the metal titanium correspond with as many of the Fraunhofer lines. His investigations, which extend over 45 metals, fully confirm the observations of Kirchhoff. The spectra of the metals silver, mercury, antimony, arsenic, tin, lead, cadmium, strontium, and lithium show no coincidence with the Fraunhofer lines. And this is also the case with the two nonmetallic substances, silicon and oxygen. Chapter 45. Kirchhoff's theory of the physical constitution of the Sun. It had long been assumed that the gaps in the colors of the solar spectrum, which form the Fraunhofer dark lines, were due to an absorption of the corresponding colored rays in the atmosphere of the Sun, but no explanation could be given of this phenomenon. The cause of this absorption was ascertained by Kirchhoff in his discovery that a vapor absorbs from white light just those rays which it emits when luminous, section 40. and he proved the whole system of the Fraunhofer lines to be mainly produced by the overlying of the reverse spectra of such substances as are to be found in the Earth. He thus arrived at a new conception of the physical constitution of the sun, which is entirely opposed to the theories held by Wilson and Sir William Herschel in explanation of the solar spots. According to Kirchhoff, the sun consists of a solid or partially liquid nucleus in the highest state of incandescence, which emits, like all incandescent solid or liquid bodies, every possible kind of light, and therefore would of itself give a continuous spectrum without any dark lines. This incandescent central nucleus is surrounded by an atmosphere of lower temperature, containing, on account of the extreme heat of the nucleus, the vapors of many of the substances of which this body is composed. The rays of light, therefore emitted by the nucleus, must pass through this atmosphere before reaching the Earth, and each vapor extinguishes from the white light those rays which it would itself emit in a glowing state. Now it is found when the sun's light is analyzed by a prism that a multitude of rays are extinguished, and just those rays which would be emitted by the vapors of sodium, iron, calcium, magnesium, etc., were they made self-luminous. Consequently, the vapors of the following substances, sodium, iron, potassium, calcium, barium, magnesium, manganese, titanium, chromium, nickel, cobalt, hydrogen, and probably also zinc, copper, and gold, must exist in the solar atmosphere, and these metals therefore must also be present to a considerable extent in the body of the sun. According to the investigations of Ångström, the number of the bright lines of the following substances, coincident with an equal number of the Fraunhofer dark lines, is as follows: sodium 9, iron 450, calcium 75, barium 11, magnesium 4, manganese 57, titanium 118, chromium 18, nickel 33, cobalt 19, hydrogen 4, aluminum 2, zinc 2, copper 7. It appears therefore indubitable that the substances composing the body of the sun are similar to those of which the Earth is formed. For though there may be between F and G some conspicuous dark lines, the origin of which is as yet unknown, it would be premature to say that they were occasioned by substances foreign to this Earth. Could the light from the sun's nucleus in any way be set aside, and only that of the incandescent vapors of the sun's atmosphere be received through the slit of the spectroscope, a spectrum would then be obtained composed of the actual spectra of these substances. That is to say, the same system of bright-colored lines which now appear as the dark Fraunhofer lines. The occurrence of a total solar eclipse affords an opportunity of applying such a test for Kirchhoff's theory. For as the sun's disk is then completely covered by the moon, and all light from the body of the sun is intercepted, no light can be received except from the solar atmosphere and the glowing vapors by which the nucleus is surrounded. The results of the observations of the solar eclipses of 1868 and 1869 did not fulfill the expectations that had been entertained. For though the Fraunhofer lines ceased to be visible the moment when, with the disappearance of the last rays of the sun, total darkness commenced, the system of bright lines did not appear in their stead, which, as the spectra of the glowing vapors of the solar atmosphere are still in view, was to be expected. With the slit of his spectroscope placed longitudinally at the moment of obscuration, and for 1 or 2 seconds later, the field of the instrument was filled with bright lines. As far as could be judged during this brief interval, every non-atmospheric line of the solar spectrum showed bright. An interesting observation confirmed by Mr. Pye, a young gentleman whose voluntary aid proved of much service. From the concurrence of these independent observations, we seem to be justified in assuming the probable existence of an envelope surrounding the photosphere, and beneath the chromosphere, usually so called, whose thickness must be limited to 2 or 3 seconds of arc, and which gives a discontinuous spectrum consisting of all, or nearly all, the Fraunhofer lines showing them, that is, bright on a dark ground. It would, however, be premature to form a conclusion against Kirchhoff's theory from these negative results, for it may easily be presumed that the vapors of the solar atmosphere do not possess that degree of heat which would be necessary to produce a light sufficiently intense for creating gas spectra at such an enormous distance, 92 million miles. Indeed, the great darkness and even blackness of many of the Fraunhofer lines justifies the conclusion that the difference of temperature must be very considerable between the sun's nucleus and the atmosphere vapor by which, according to Kirchhoff's theory, it is surrounded, and if on other grounds, to which reference will be made hereafter, it were admitted that the supposition of the sun's nucleus being an incandescent solid or liquid body were untenable. Yet, Kirchhoff's explanation of the Fraunhofer lines and his proof of the presence of elements in the sun similar to those found in the earth would still remain unaffected, even if the nucleus of the sun were the French astronomer Faye supposes. Neither solid nor liquid, but in a condition of vapor or gas, there is still no doubt that either the ball of gas itself, in consequence of the extreme heat, is incandescent, and would therefore emit rays of every shade of color, proof of which has been furnished by the experiments of Frankland, Deville, and Wilner, p. 165, in accordance with the views of De La Rue, Stewart, and Louis, of which rays those corresponding to the Fraunhofer lines would be absorbed by the cooler outside strata, or else the ball of gas, if non-luminous, is surrounded by a stratum of vapor partially condensed, forming a cloud in a condition of extreme heat called the photosphere, whence emanates the white solar light, and in which the absorption of the vapors composing it takes place in the same way as occurs in the direct volatilization of sodium by the electric light, P212. We shall enter upon these theories more in detail hereafter, but this much may be said here, that every explanation of the physical constitution of the sun must always be based upon the discoveries of Kirchhoff, and the various details of any theory and explanation of the solar spots, the facles, the prominences, etc., must be in strict accordance with the phenomena established by Kirchhoff of the absorption of the colored rays and the reversal of the spectrum. Chapter 46. The atmospheric lines in the solar spectrum, as observed by Brewster and Gladstone, the Italian physicist Zanedeschi, of whom we have already spoken, was the first to remark that the dark lines in the solar spectrum are not all invariable, and that the changes occurring in number, position, intensity, and breadth in some of them are due to the varying condition of the Earth's atmosphere. This subject has since occupied the attention of Brewster and Gladstone, Piazzi, Smythe, Secchi, and preeminently the French physicist Janssen, but their investigations have not as yet led to any satisfactory result. Brewster and Gladstone, 860, found that new dark lines and bands made their appearance in the solar spectrum when the sun approached the horizon, and that certain dark bands were more strongly marked in the morning and evening than at noon when the sun stood high in the heavens. As the sun, when near the horizon, must transmit its rays through a stratum of air nearly 15 times as thick as when at a high altitude at noon, the idea was suggested that the atmospheric air, though colorless, might exercise an absorptive influence upon the light and obstruct the rays as vapors do. Section 38. In proportion as the stratum increases in thickness and density through which the solar rays have to pass. The solar spectrum, published by Brewster and Gladstone in I-860, nearly 5 feet in length, contains more than 2 zero-visible dark lines or bands, easily distinguishable one from another. The violet end extends as far as in Fraunhofer's map, while in the direction of the red it is of considerably greater length. The Fraunhofer lines retain their original designations A and B, etc., while the lines and bands interspersed between them, and clearly separable one from the other, are marked by figures after the letters A, B, C, etc., in succession towards the violet, always commencing with I. Thus, between A and A there lie 3 bands, marked AI, at A3. Between A and B, there are 8 lines, or bands, marked only nat 2, 8. There are 7 lines between B and C, 16 between C and D, 20 between Lord Paul, 30 between B and F, 50 between F and G, 53 between G and H, 4 between H and K, and 10 between K and I, each line marked by a number, beginning always with I. Besides these prominent lines, there are many very fine lines interspersed among them, which are not enumerated. Those lines and bands which are preeminently influenced by atmospheric conditions and are therefore more or less prominent according to the altitude of the sun are designated by the letters of the Greek alphabet. The solar spectrum given in Figure 92 is taken from a reduced drawing by Brewster and represents not only the Fraunhofer lines, but also all the variable lines and bands of any importance which are easily discernible, and which are here marked by the Greek letters. The numbers are omitted. The drawing shows the spectrum as it appears when the sun is near the horizon. All of the lines and bands marked by the Greek letters disappear from the spectrum, or become more or less pale as the sun attains a meridian altitude. These bands were named by Brewster and Gladstone atmospheric lines to indicate that they were formed by the absorptive power of the Earth's atmosphere. These observers did not succeed, however, in ascertaining to what elements in the atmospheric air this selective absorption was to be ascribed. In the least refrangible portion of the spectrum, two intensely dark bands appear at sunrise in front of a bordered on both sides by a fine line, YZ. A increases much in breadth and preserves this width even when the sun has a considerable altitude. When A is observed at noon, it appears as a double line, or like two dark spaces separated by a narrow band of light. When the sun is setting, this bright stripe disappears, and the line is seen as one band of uniform width and intensity. The group YOA increases in intensity toward sunset, but the individual lines do not subside into one band. The strongest absorption takes place close to B, C, and most of the lines between C and CX become darker, and Cheeks in the orange is especially remarkable as it deepens in intensity while the sun is yet high in the heavens. In England, this line is visible during the whole day in winter, but not in summer. At sunrise and sunset, it is one of the darkest and best defined lines in the whole spectrum. C5 increases towards evening to a black band, and the double line D becomes at the same time very prominent. Behind D2 a band marked 3 begins, which is especially characteristic of the spectrum of light that has passed through a thick stratum of air. Even in a small spectroscope, this band may be readily seen at any hour of a dull day in the diffuse light, but it is particularly dark and well-defined during heavy rain or a thunderstorm, and at sunset it becomes almost black. The same is noticed in the bands E and Z, as also in the line 17, which is very distinct at evening, and from its proximity to E, which remains unaffected by the atmosphere, may easily be mistaken for it. On the further side of B are several other remarkable atmospheric bands. Particularly I and X-Theft loses its sharpness at sunset, and 7 bands from A to C become visible between F and G. At G, the only change is a loss of brightness towards evening, but a still greater amount of absorption takes place beyond, in the violet rays. The western sky immediately after sunset affords the best opportunity for observing these dark atmospheric lines, especially the bands dollar and pound in the bright parts of the spectrum. If at that time the sky be red, the lines C, C, D dollar appear generally as 4 very dark bands, but when the sky is yellow, they are much less distinctly marked. Chapter 47. The telluric lines in the solar spectrum and the spectrum of aqueous vapor, as observed by Janssen, and the spectrum of aqueous vapor, as the investigations of Brewster and Gladstone, were resumed by the French physicist Janssen in 1864 for the purpose of discovering what substance in the atmosphere produced the selective absorption of the solar spectrum. With an instrument of his own construction, composed of 5 prisms, he succeeded at once in resolving the dark bands noticed by the English observers into very fine lines, and in ascertaining that their intensity was perpetually varying. He found them to be darkest at sunrise and sunset, and less intense in the middle of the day, but they were never entirely absent from the spectrum, a periodicity of change which at once proves their atmospheric origin. To procure still more decisive evidence on this point, Janssen resolved to pursue his observations on the solar spectrum from the top of a high mountain, whence the absorptive influence of the lower and denser stratum of the atmosphere would be excluded, and the effects of absorption consequently would be manifested in a more moderate degree than on the plain. For this purpose, In the year 1864, Janssen remained for a week at the summit of the Faulhorn, at position of Mussoorie, has sent in a first report of his observations, together with a chart of the atmospheric lines as seen by him at sunset. This map has been printed in the proceedings of those who are studying these lines, a height of 30 meters, about 90 feet above the sea, and convinced himself that the variable dark lines in the solar spectrum were in reality much fainter there than in the plane. But in order to discover the real origin of this absorption, and to obtain proof that these lines were produced only by the Earth's atmosphere, he devoted himself to the examination of artificial light. Since the light of the sun in traveling to the Earth has to pass for millions of miles through foreign media. In October 1864, he caused a large pile of pine wood to be set on fire at Geneva. At a distance of 210 meters, about 13 miles from his place of observation, and observed the flame in the spectroscope. When viewed near, the fire gave a continuous spectrum without dark lines. But at the full distance, some of the dark lines appeared, which Brewster had observed in the spectrum of the setting sun. It remained now for Janssen to determine with yet greater certainty whether this atmospheric absorption was to be ascribed to the air or to the aqueous vapor contained in the air, an investigation beset with unusual difficulties, which could only at last be accomplished when in 1866 the Gas Company of Paris placed their apparatus at his disposal. An iron cylinder, 1/8 feet long after being exhausted of air by forcing steam through it under a pressure of 7 atmospheres, was filled with steam and closed at both ends by pieces of strong plate glass. The cylinder was surrounded with sawdust to prevent radiation, and additional contrivances were also adopted to preserve the steam from condensation, and so to maintain its transparency. A very bright flame, produced by 16 united gas burners, was placed at one end of the cylinder and the spectroscope at the other, so that the rays from the flame had to pass through a stratum of aqueous vapor 118 feet thick before reaching the slit of the instrument. The spectrum of the light in the air was entirely free from absorption lines. But seen through the cylinder of steam there at once appeared groups of dark lines between the extreme red and the line D, similar to those seen in the spectrum of the setting sun. By this means not only was the proof furnished that a large number of the variable lines in the solar spectrum are due to the presence of aqueous vapor in the Earth's atmosphere, but also a method secured for detecting the presence of aqueous vapor in the heavenly bodies. Lines C and D as drawn by Janssen. The upper half is the spectrum of the sun in the meridian, the lower half that of the sun at the horizon, Vide P254. Those lines which present the same appearance in both halves belong exclusively to the sun, while those which are darker in the lower than in the upper half are telluric lines. It has been further shown by Janssen that almost all telluric lines are produced by the aqueous vapor of the Earth's atmosphere. That an absorptive and 6O fluence is also exerted by this vapor on the invisible portion of the solar spectrum, beyond the red, that is to say, in the heat spectrum, where it produces absorption lines, and finally, that it affects the whole of the violet portion of the spectrum in a manner more nearly uniform than selective. The absorption spectrum of aqueous vapor consists therefore of all the lines introduced into the continuous spectrum by the aqueous vapor of the Earth's atmosphere. It is an absorption spectrum which may be easily constructed for the portion between C and D, by leaving out all those lines from the lower part of figure 93 with those in the upper half. It has been proved that the groups marked CSS as ND arise from the aqueous vapor in the atmosphere. The telluric character of the central group C7 has been also established by Janssen beyond a doubt. But as yet it remains uncertain whether they are likewise to be attributed to aqueous vapor. The investigations of Janssen were not confined merely to that portion of the solar spectrum included between C and D. He continued the spectrum in another map, where it reaches below the line B and beyond D. In this spectrum are included also the 3 groups marked by Brewster ASS7, figure 92. Janssen has extended his observations to the light of the moon and fixed stars, with the view of ascertaining if the stellar light, which differs from that of the sun, be subject to similar changes in its passage through the Earth's atmosphere. With this object, Janssen attached a small direct vision spectroscope to a powerful astronomical telescope, in the manner described more in detail in the section on stellar spectroscopes, and examined the spectrum of Sirius as the star appeared above the horizon. In its very bright spectrum were several dark bands, which when measured were found to occupy precisely the same position as the dark bands that appeared in the solar spectrum at sunrise and sunset. In proportion as Sirius gained in altitude, the intensity of these telluric bands gradually diminished, until as the star passed the meridian, they entirely disappeared. 5G 94 gives the spectrum of the Sun, D, and the spectrum of Sirius, I, as they appeared in a small spectroscope when observed in the meridian and at the horizon. The telluric bands will be recognized at once on comparing the two spectra of the same object. The dark bands marked I2, 3 are evidently telluric absorption bands common to both the Sun and Sirius when near the horizon. Secchi has also been occupied for many years in observing the telluric lines of the solar spectrum. From the first he expressed an opinion that the existence of these dark lines, which vary with the place of the Sun, the position of the observer, and the amount of humidity in the air, were to be ascribed to the absorptive action of the aqueous vapor contained in the atmosphere. The influence of the weather was apparent in the fact that some of these lines were invisible in clear meridian. Horizon. Weather with a north wind, while they were strongly marked on dull days with the wind in the south. Secchi has also observed and measured the dark absorption lines during rainy weather in the spectrum of a flame distant 20 meters. Ångström of Uppsala has also instituted careful investigations of the telluric lines in the solar spectrum, and has introduced these lines into his maps, section 43, plate 6, measured according to the wavelengths of the colors they absorbed. In scale, the lines and bands there shown are all atmospheric lines, with the exception of the Fraunhofer line CDEBFE. The order of the phenomena produced by the absorptive power of the atmosphere as the Sun approaches the horizon is thus described by Ångström. The violet portion of the spectrum disappears as far as G. The absorption then keeps advancing towards the red and intensifies the dark bands near F and D. At the same time, the lines A, B, and yellow, which are always visible in the red part of the spectrum, become much darker, and the lines of aqueous vapor both at C and D continually augment. At last, the only parts remaining bright lie between B and A, between A and 3, and in the greater portion of the greenish-yellow in the vicinity, and to the right of dollar, while the portion between B and dollar is more or less shaded by dark bands. The part of the spectrum least affected by the telluric absorption lies between D and Ångström, concurs with Brewster, that nearly all the changes of color observed in the red glow of sunrise and sunset find a simple explanation in phenomena. JF of atmospheric absorption, whereby all the ingenious and elaborate explanations hitherto attempted are completely and set aside. Ångström is of opinion aids that the bands ABA and $W are not produced by the A aqueous vapor of the atmo-J sphere, since they are very H constant and are not affected 0 H, apparently by changes of B temperature, whether other D gases contained in the atmospheric air, as for instance, carbonic acid gas, exercise an influence upon them, has yet to be investigated. It is fully admitted that other heavenly bodies besides the Earth may be surrounded by an atmosphere. Janssen's discovery of the spectrum of aqueous vapor furnishes the means of ascertaining whether this vapor, indispensable to the maintenance of all the living organisms of our planet, is also present in the other celestial bodies. Repeated observations undertaken by Janssen on the high mountains of Italy and Greece have already furnished proof that aqueous vapor is present in the atmospheres of the planets Mars and Saturn. Chapter 48. The solar spots, the facular and their spectra. It would lead us too far from our subject were we to dwell upon the phenomena of the solar spots. Important as they are for acquiring a knowledge of the physical constitution of the Sun, or enter upon a full description of their form, their mode of formation and disappearance, their motion, their connection with the sun's rotation upon its axis, their periodic occurrence, and the various hypotheses that have been formed as to their nature. But on the other hand, we must still less be silent on the subject, since spectrum analysis has investigated these wonderful appearances with a success which has added much to our knowledge of the constitution of the sun. A number of excellent photographs and drawings have been made by Secchi Nasmyth, Warren de la Rue, and others of remarkable spots, showing very clearly the characteristic forms they assume and the phenomena which accompany them. By means of a magnifying lantern and an intense light, these photographs may be thrown upon a screen and exhibited to a large audience. Spots similar to those shown in Figure 96 and following figures consist principally of a dark, almost black, central portion, the umbra, surrounded by a space somewhat less solar spot, seen through a large telescope by Secchi at Rome, April 3, 1858. Dark called the penumbra. The umbra has generally an irregular form, while the penumbra exhibits a structure radiating towards the center. If the sun be observed with a high power, the surface presents by no means a uniform appearance. A multitude of bright and dark stripes cross each other in all directions, and the luminous surface appears like a net of bright meshes interwoven with dark threads and small dark pores. The brightest portions, Figure 97, show a more or less elongated form. Compare Figure 101, which suggested to Nasmyth the name of willow leaves, while Dawes compares them to bits of straw, and Huggins calls them merely granules. On this uneven and ever-varying bright background, the spots make their appearance in the greatest variety of form and size. The penumbra not unfrequently stretches across the black central portion in various places, Figure 98, and generally appears much darker at the outer edges, where the spot touches the bright part of the sun's surface, than in other places. Very often, the penumbra is traversed by fewer, more bright curved bands, stretching from the outer edge towards the nucleus, generally at right angles to the confines of the nucleus and penumbra, Figure 99, which give the spot the appearance as if a number of streams of solar spots after capoxy. Furrows in the penumbra. Some luminous matter had broken through the dam formed by the penumbra to fall into the abyss of the umbra. Even the umbra itself is often crossed by one or more broad luminous bands, called bridges, by which it is divided into several portions, figures besides the dark spots, and chiefly in their immediate neighborhood, bright places make their appearance on the sun's surface, which have been called facles. They are generally the attendants of solar spots and are especially to be seen at the extreme edge of the penumbra when the spot has reached the sun's limb. That they are not the effective contrast between the dark spot and the neighboring brightness is proved by the circumstance that every spot is not accompanied by facube, and that very frequently isolated falum are to be seen which are almost always the precursor of a coming spot. The facube, like the spots, vary considerably in form. Generally, they are round and concentrated, but often they have the appearance of long stripes of light, Figure IIO, disposed like veins, converging from all sides towards a spot. The wreathed faculae are almost always followed in a few days by the appearance of a group of spots, among the vein-like waves of light visible in many places, more especially towards the sun's limb. There is first developed a dull, scar-like place out of which the spots are formed, sometimes singly, sometimes in groups. And not unfrequently, the formation of a spot may be predicted from the increased intensity of light at that place on the sun's disk, when a spot is observed near the sun's limb in the midst of the surrounding faculae. It is difficult to avoid the impression that the spot lies in a hollow between bright overhanging mountains, and it was observed by Secchi on the 5th of August, 1865, that the faculae, when they reached the western limb of the sun, appeared like small projections and irregularities upon the sharply defined limb of the sun, although the real connection between the faculae and the spots is not yet fully understood. It may be safely concluded from these observations that the spots lie deeper in the solar surface than do the faculae, and that these faculae are mountainous elevations of the luminous matter forming the photosphere, by which the spot is surrounded in a wide circuit as by a wall. A representation of a group of solar spots observed and drawn by Nasmyth on the 5th of June, 1864, is given in Figure 101, in which all the details characteristic of a spot are to be recognized. Black umbra, the penumbra in a variety of forms, composed of the leaves directed towards the umbra and the surrounding luminous surface of the sun, presenting group of solar spots observed and drawn by Nasmyth, 5th June, 1864. Its usual granulated appearance. This surface is called the photosphere, a name given without reference to any particular theory as to its physical constitution or structure. The photosphere is entirely covered with pores, or small spots, less luminous than the other parts. Where they congregate and become conspicuous by forming a black umbra and shaded penumbra, they constitute the ordinary solar spot. Where the portions of greater brilliancy than the surrounding parts of the photosphere congregate, they form the facles, and these generally accompany the spots or precede their formation. If a solar spot be watched in the telescope from day to day, or from hour to hour, it will soon be seen to change in form. It increases or diminishes or completely vanishes away while new spots make their appearance. In the process of disappearing, the dark umbra first gradually contracts until it becomes invisible, leaving the dusky penumbra perceptible for some time longer. Not unfrequently, a spot breaks up into several spots, and occasionally a group unites to form one, and sometimes even as was observed by Weiss on the 12th of March, 1864, and by Haag on the 13th, 15th, and 16th of April, 1869. One spot is seen to pass over another, partially covering it, and then withdrawing from it. In all these changes, the spots exhibit an amount of mobility displayed in general only by liquid or vaporous masses. The great changes which sometimes occur in a solar spot are shown in Figure 102, representing 4 drawings of the large spot, more than 46, 0 square miles in area, that appeared in 1865. The drawings are numbered in order of date. Number 1 shows Omachi Oru. From 7th October to 16th October, the form of the spot on the 7th of October, when it was first visible on the eastern left limb of the sun, dosed 2 and 3 as it appeared on the 10th and 14th of October, central view, when a bridge had been already formed across the nucleus. And number 4 as it was seen on the 16th of October. The formation and changes in the configuration of a spot may often be watched during the course of observation. And it not unfrequently happens that the appearance of a group of spots is so entirely changed from one day to another that it can no longer be recognized in the new form it has assumed. An example of this is given in Figures Solar Spot of 30th July, 1869, and 104, consisting of drawings of the same group of spots observed by Secchi at noon on the 30th and 3th of July, 1869. On the other hand, there are spots presenting scarcely any change, which preserve nearly the same form for many days together. Spots of this kind are of the highest value to the astronomer, as they afford the only means of ascertaining the time of solar spot of 31st July, 1869. The revolution of the sun upon its axis, the position of this axis, and its inclination to the Earth's orbit. If a spot be observed even for a short time, it will soon be remarked that it apparently advances on the sun's disk from east to west, that is to say, from the left to the right limb of the sun. In an inverting astronomical telescope, the motion will appear to be in the opposite direction, namely from right to left. The form of a spot on its first appearance on the eastern limb of the sun is that of a small dark streak, the length of which is much greater than the breadth. For the first few days, it appears to move but slowly towards the middle of the sun's disk. Its speed afterwards increases from day to day, till it has accomplished half the journey across the disk. The motion then slowly diminishes until the spot again assumes the form of a narrow streak, and disappears at the opposite western limb of the sun. It not unfrequently happens that the same spot which has been observed to disappear on the western limb has in the course of about 14 days been seen to reappear on the eastern limb, and in the lapse of another 14 days has disappeared a second time on the western limb, a phenomenon that proves beyond a doubt that the spots are connected with the surface of the sun, and that the sun itself has a revolution upon its axis. If the time required for the Earth's motion round the sun be allowed for in this revolution of the spot, The result will show, according to Spurrier, a mean time of rotation for the sun amounting to 25 days, 5 hours, 38 minutes. Kirchhoff, whose views Professor Spurrier, one of the most industrious observers of solar spots, has in the course of his investigations adopted with increasing confidence, considers these forms to be cloud-like condensations in the sun's atmosphere, which are produced by the loss of the solar heat by radiation, in the same way as the aqueous vapors of the Earth's atmosphere are formed into mist and cloud. When such clouds arise over the bright and glowing surface of the sun, they obscure the light of the sun at that spot, and it is but natural that these cloudy masses, so irregularly formed, should also become further condensed or be dispersed with the same amount of irregularity, according as they come in contact with cooler or warmer streams of gas. Those physicists who differ from Kirchhoff in their views of the physical constitution of the sun, and consider with Fay that the actual nucleus of the sun is a non-luminous ball of gas, entertain a different theory of the nature of the solar spots, regarding them as rents or openings in the bright photosphere surrounding the dark ball of gas through which this dark nucleus is seen. The elder and younger Herschel have both recorded observations of a depression or notch in the sun's limb when a spot has been disappearing round the edge of the sun. J.F. The idea has been once entertained that a solar spot is a cavity or funnel-like depression in the luminous photosphere. It is difficult to resist the optical illusion arising from the fact that a dark spot on a bright background always conveys the impression of a hole. Secchi at Rome on the 5th of May, 1857, which resembles a gigantic whirlpool or a funnel, into the interior of which the substance of the photosphere appears to be rushing with an eddying motion. Warren de la Rue has taken 2 photographic pictures of the same spot at an interval of 2 clays, and if these pictures be placed together and looked at through a stereoscope, the spot exhibits the form of a funnel with remarkable exactness. Other photographic pictures taken of similar spots when at the extreme edge of the sun also convey the idea of the existence of real depressions in the photosphere. The opinion that the solar spots are funnel-shaped depressions in the outer stratum of the sun's envelope, or photosphere, finds support not so much from observations of this kind as from the different appearances they present in their apparent motion across the sun's disk, without any actual change occurring in their form, size, or grouping. Were a spot to make its appearance upon the surface of the sun and become visible on the eastern limb, the preceding or western part of the penumbra would first come into view owing to the sun's rotation from east to west. Then the western portion of the umbra would appear, and the umbra itself would gradually increase from west to east. Finally, the most eastern portion of the penumbra, that which was furthest from the line of sight, would be revealed. In the same way, on disappearing round the western limb of the sun, the preceding or western part of the penumbra would first become invisible. The western penumbra would then gradually decrease, after which the umbra would diminish in the direction of west to east, and finally the following or western part of the penumbra would entirely disappear from view. In reality, however, the exact contrary is observed. On the appearance of a spot at the eastern limb, the eastern portion of the penumbra is first visible, then follows the umbra in the form of a dark streak, which gradually widens in the direction of east to west, till at length, when the umbra is wholly visible, the western side of the penumbra begins to appear. On the disappearance of the spot at the western limb of the sun, the eastern portion of the penumbra, that which is turned towards the center of the sun's disk, first diminishes, and the umbra again contracts into a narrow streak, while the western side of the penumbra has scarcely at all decreased. Only when the umbra is entirely lost to sight does the western penumbra begin to diminish and finally disappear. The changes in the appearance of a spot caused by the rotation of the sun. In figure 106, the drawings marked, I represent the varying phases through which a spot surrounded by a penumbra usually passes from the moment of its first appearance on the eastern limb of the sun until it disappears again at the western limb. They show that the theory of the spot being above the surface of the sun as a cloud in the solar atmosphere, or being on the surface itself, is untenable. The phenomena observed, however, can be at once explained by the supposition that the spot is a conical-shaped depression in the outer surface of the sun, the photosphere, which expands from the inside and contains in its deepest recesses the cause of the dark umbra, while its sloping sides are composed of what appears to us as penumbra. The drawings marked 2 represent such a conical-shaped cavity in a globe shown in perspective in the same postions as those occupied by the spot on the sun's disk in the first set of drawing. It is needless to remark that the size of the spot in reality bears no such proportion to the size of the sun as, for the sake of clearness, has been adopted in the drawings. We cannot any further follow the reasons for or against these hypotheses concerning the cloud-like or funnel-formed appearance presented by the solar spots, without first becoming acquainted with the results which spectrum analysis has already furnished in connection with these mysterious phenomena. William Huggen, whose invaluable labors in the province of stellar spectrum analysis will be discussed hereafter, made an examination of the spectrum of a solar spot on the 15th of April, 1868, and then found, in accordance with the previous observations of Secchi and Lockyer, that notwithstanding the darkness of the spot, the continuous solar spectrum did not disappear, but that several dark lines increased in breadth and intensity. As shown in figure for the double D line, new lines did not appear in the spectrum formed by the light of the umbra of a spot, but no single line was missing from the normal solar spectrum. Bright lines were scarcely ever to be seen. These phenomena cannot well be reconciled with Faye's hypothesis that a spot is formed by the eruption of streams of gas from the interior of the sun, by which the bright photosphere is pushed on one side, and the dark ball of gas composing the nucleus of the sun exposed to view. For how can the persistence of the continuous spectrum be explained if by the rending of the photosphere a dark body be exposed, which can yield no light for the formation of the spectrum? According to Faye's theory, a solar spot must either show no spectrum, or if the inner gaseous portion of the sun emit any light, it must yield a spectrum composed of bright lines, neither of which is the case. The continuous spectrum, crossed by the Fraunhofer lines, proves that the umbra allows a considerable portion of the sun's ordinary light to pass through it. And the widening of the dark lines shows indisputably that the spot occasions an increased absorption of the light, arising from the condensation of the same vaporous substance which produces the dark absorption bands in the ordinary solar spectrum. More significant are the recent investigations of Secchi. In examining with his great spectroscope the neighborhood of a large spot, he saw groups of 3, 4, or 6 cloudy bands equally distant from each other appear in the red and orange of the spectrum. These bands usually disappeared when the slit of the instrument was directed away from the spot on to the clear disk of the sun. Their appearance in the spectrum was always a sure sign of the proximity of a spot, even when it was not itself within the field of the instrument. On the 6th of January, 1869, Secchi was surprised to observe the same bands on the clear disk of the sun, the cause of which was soon apparent by the passage of a cirrus cloud over the sun. And on a closer examination, these bands were seen to show themselves in all parts of the disk. As the cloud passed away, the bands disappeared from the spectrum. It was thus proved that aqueous vapor had some share in producing the phenomena of the cloudy bands, and this was demonstrated still more unequivocally by another observation made in the beginning of February, when Secchi, observing the sun through a tolerably thick fog, noticed that these bands were visible on every part of the disk, but decidedly more prominent in the vicinity of the spot. Secchi concludes, therefore, that the absorptive power in the sun producing these bands is intensified by the absorptive action of the aqueous vapor contained in the Earth's atmosphere. Where the Earth's mist and the solar spot coincide, this action is increased. The cause of the absorption in the sun in the neighborhood of the solar spots is therefore the same as that which is present in a fog, namely, aqueous vapor. Consequently, it seems proved that aqueous vapor exists in the atmosphere of the sim in the vicinity of large spots. Secchi also carefully analyzed the fine group of solar spots, which appeared in the middle of March, 1869. With a spectrum apparatus consisting of a powerful telescope and 3 very widely dispersive prisms, and arrived at the following results. 1. Several dark lines, which were very narrow and well defined on those parts of the sun free from spots, appeared swollen and widened in the spectrum of the spot. Other lines were fainter and not so sharply defined at the edges, as in the spectrum of other parts of the sun. 2. Most of the exceedingly fine dark lines, scarcely visible in the solar spectrum, appeared very dark and broad in the spectrum of the spot. 3. The relative intensity of the bright portions was considerably altered in the spot. While some lost much in brilliancy, others retained their full intensity. 4. The apparent loss of brilliancy in the bright portions was produced more by the increased width of the dark lines than by an actual diminution in the light. The widening of the two lines D and D2 forming the sodium line D, for example, was so great that the space between them seemed to have almost quite disappeared, while in places away from the spot, these two lines were widely separated. Similar observations were made on a spot visible from the nth to the 13th of April. The spot had a double oval umbra and a large penumbra and was surrounded by a number of smaller spots. The two principal portions of the umbra were separated by a very narrow and very bright bridge, which, dividing the spot into two parts, extended through the whole of the penumbra from one end to the other. The interior of the umbra appeared as if filled with rose-colored veils, twisted confusedly and spread about in every possible way. Under very favorable atmospheric circumstances, Secchi was able to confirm all the foregoing spectrum observations of a spot, both with regard to the widening of the dark lines and the conversion of the fine lines into cloudy bands. The lines most affected were those numbered 7,195 and 864 in Kirchhoff's spectrum. They were at least 3 times as black and broad on the spot as in other places. Though the edges were still sharply defined when the slit of the spectroscope was placed at right angles to the bridge of the spot, so that the light of the bridge, the umbra, and the penumbra fell simultaneously upon the prism. Secchi saw in the field of the instrument 3 kinds of spectra at the same moment, each sharply separated from the other, as shown in figure 108, where they are represented with the Fraunhofer lines and Kirchhoff's numbers. Number 1. The ordinary solar spectrum given by the luminous bridge, except that the hydrogen lines HA equals C, HSS equals F, fly near to G, were bright instead of dark. The spectrum of the umbra with the dark lines widened and intensified, some new striped bands, and some bright double lines in the green. The bright hydrogen line of the adjoining spectrum of the bridge number 1 projected for some distance into the spectrum of the umbra, a phenomenon which was observed also in the C line by Pivet on the 12th of April, 1870. Number 3. The spectrum of the penumbra, in which the hydrogen lines were not visible. They did not appear either as dark lines or as bright lines, but were altogether wanting. Besides the thickening of the dark lines, several absorption bands made their appearance also in the M1523 and 2854, time to time from the interior of the incandescent solar nucleus. Owing to its extreme lightness, this gas would rise in enormous pillars of flame, prominences, over the absorptive vaporous stratum of the photosphere, and, in consequence of the coating ensuing from expansion, would enter into a variety of chemical combinations, especially with oxygen. The uncombined part would then flow to the side, while that, in combination with oxygen, steam, and the other solar substances would form gaseous or vaporous masses, which, from their nature, as well as from their continued cooling, would be heavier than the hydrogen gas and would sink down from their greater gravity. It is to be expected that the stream of gas on rising would carry up with it a quantity of those substances that exist in the sun's nucleus and the surrounding stratum of absorptive vapor, the photosphere. If these substances, themselves incandescent, were present in sufficient quantities in the luminous hydrogen gas, their characteristic lines would be seen as bright lines in the spectrum of the pillars of flame. During the recent total eclipses, many such lines were in fact observed, together with the bright hydrogen lines in the prominences, a description of which will be given further on. They can now be observed daily, sometimes in great numbers, upon the sun's disk. When the force of the gas eruption has somewhat subsided and the chemical combinations ensue, producing vaporous precipitations of many kinds, the formation of the spot begins. The heavier portions of these precipitations sink down and form the umbra of a spot at the place of greatest condensation, while the parts which are less dense constitute the penumbra. The vaporous umbra, however, though apparently quite black, is yet able to transmit a considerable amount of sunlight. Indeed, according to Zollner's measurements, the black umbra of a spot emits 4,000 times as much light as that derived from an equal area of the full moon. This statement is fully confirmed by the results of spectrum analysis, for even the blackest umbra yields a spectrum exhibiting all the details of full sunlight. Where the spot is broken through by the overflowing masses of the photosphere, a bright band is formed, called a bridge, which extends across the whole of the penumbra. The rays of light emitted by the luminous hydrogen as it flows to the edges of the spot from the neighboring parts of the bridge and breaks over the absorptive stratum of the bridge are not further absorbed, and illuminate the dark Fraunhofer lines, CF and 1 near G. These lines, therefore, in the spectrum of the bridge, number 1, are reversed from dark to bright. In the umbra of the spot, the free hydrogen is no longer present in sufficient quantity or at a sufficiently high temperature for its lines H, S, S, Y to overpower the dark Fraunhofer lines CF and the 1 near G, or even to weaken them perceptibly. On the other hand, the intensity of the light and the temperature of the hydrogen in the parts belonging to the penumbra are sufficient to cause its 3 bright lines coincident with the dark lines CF and the 1 near G to be of the same intensity as the neighboring parts of the spectrum, and therefore they become invisible. In the spectrum of the bridge, these lines are generally bright. In that of the umbra, they remain dark, while they are frequently entirely white in the spectrum of the penumbra, the various remarkable changes which the lines of hydrogen, magnesium, sodium, calcium, and iron suffer in the spectrum of the umbra seem to show that in the cloud-like and vaporous substances constituting the spot, the new combinations are disposed in layers according to their specific gravity. Thus, hydrogen gas occupies the highest stratum. Aqueous vapor, magnesium, and sodium follow in thinner layers below, and the heavier vapors of calcium, titanium, and iron form the lowest and densest stratum, the base of the spot. The formation of a spot will accordingly immediately follow an eruption of hydrogen. The spot itself is a dense, cloudy, luminous mass, probably of a semi-fluid consistency, composed of many constituents, according to Zollner. A kind of scoria, which sinks by its gravity a certain depth into the photosphere, or outer portion of the sun, and partially intercepts the light from the lower stratum of the photosphere, therefore presenting to us the appearance of a dark mass projected upon the disk of the sun, in the same way as the exceedingly intense light of the oxyhydrogen limelight appears black when seen against the sun. The enormous dimensions of these dense masses of vapor, which extend sometimes in all directions, account for the length of time the spots continue visible, not unfrequently remaining during several rotations of the sun. Their disappearance is to be explained partly by the substance of the photosphere flowing into the cavity of the spot, partly by the complete subsidence of the vapors into the nucleus of the sun, where, in consequence of the enormous heat, the compound substances which may exist in them are broken up into their original elements. These conjectures are by no means intended to afford a complete explanation of all the phenomena of a solar spot, though it certainly is of the highest interest for us to acquire a knowledge of the physical nature of that heavenly body whence we derive light, heat, motion, and life. We must yet be cautious of receiving for truth what is only the result of speculation, especially as the theories on this subject rest on isolated observations which are too unconnected to point to any certain conclusion. The suggestions here thrown out are only intended, therefore, to throw some light upon the results hitherto obtained by the spectrum observations of Secchi, Huggins, Lockyer, and Young, and by affording an unconstrained interpretation of them to bring them into harmony with the phenomena observed during the total solar eclipses of